Life Science Bhubaneswar, and it will be chaired by Dr. C.R. Mishra. Dr. Chittaranjan Mishra is an eminent chemical scientist and technologist, columnist, television anchor, author, orator, and national science communicator of repute. Dr. Mishra had a highly distinguished career in the Navaratna Public Sector Company of Government of India, NALCO, in the field of research and development for more than 25 years. Dr. Mishra was the Deputy General Manager and Head Research and Development, NALCO. Dr. Mishra is a prolific science writer, orator, and columnist of repute in Odia language and has significantly contributed to the public outreach of science. Dr. Mishra has published more than 70 research papers in various national and international journals, seminar, conferences, symposia, etc. Besides, Dr. Mishra has 12 number of national and international patents to his credit. Dr. Mishra has received large number of national, international, state level awards for his outstanding contributions in the field of aluminum science and technology and popularization of science. So, I now request Dr. Chittaranjan Mishra to please chair the session. So I now invite Professor Naran Pradhan to deliver the talk on seeing the atomic arrangements at the interface of two materials in nanoscale under electron microscope.
So OCS is always a special for all of us, including me. Whenever it was, I am volunteers to be there. And also, so today's in the last OCS, not the last year, previous year, it was in Bhubaneswar. So the talk I started somehow could not complete it because of lack of time, because of last before. So I will go back there and take it out from this talk here. So so we are more than 15 years in cultivation of science, and basically my MSc is in organic chemistry in the Orissa College. But soon, in the course of time, never have any intention, but it changed to on the material chemistry, and now I became a like no training, nothing. A crystallographer looks like. You will see me as different. But this is the way you enjoy. The way you enjoy, you feel it does not matter because for the science, anything you deep inside, you can get something different. So what I will talk here, I just put it out. The title looks more on materials.
At the outset, I would like to tell you that I am a product of ISC.
Oh.
I was the first Odia man who got PhD from that building in the year 1977. So we are from the same building.
Okay,
Same institution. Long back, 77 is how many years? PhD in 77.
Okay.
Thank you so much. Professor Datta, you know? Professor P.C. Datta?
Yes, yes.
Giant organic chemist of the country. He was my guy. Professor Narayan Pradhan is currently the school chair and senior professor for School of Material Sciences, ISCS Kolkata. Professor Pradhan received his PhD degree from IIT Kharagpur. He was a postdoctoral fellow of the University of Arkansas, USA, and then Gordon University. He was also a recipient of various prestigious awards such as Jagdish Chandra Bose Fellowship and Swarno Jayanti Award and many more. His research focuses on creating and manipulating nanoscale materials to push the boundaries of technology and material science. Synthesis of chalcodeniate, nanoparticles, exploring their unique electronic, optical and catalytic properties, developing novel methods for producing these materials and investigating their applications in energy storage, environmental sensing, etc. He has authored more than 120 publications with around 9,000 citations, H index 60. Thank you so much. You are welcome to OCS platform. Now the time is yours, the platform is yours.
Thank you, sir. Sorry for the apology for the miscommunication because of the organizers who wanted me to talk. So as I was talking, maybe my time started from now. So the way being an organic chemistry, try to do in organic, but came out with somewhere else, and so far. But as I showed that the way you do science, you enjoy. So I was thinking to go this talk, but then later because of the chemistry platform, I changed something where you might like it. So you could see here the two stuffs. One is the benzoyl bromide, another is the penicillin bromide, which is only one CH2 group. And how this link completely to the materials what we are doing it out, I will say it out. So currently we work on the perovskites nanocrystals, which is very hot in the front line. And what you see the highest solar cell efficiency, this is also this material. But you see the highest luminescence efficiency of the inorganic or even the organics, these are the materials. So what it does, these are nothing but the structures are like this. So I will talk about one point, CSPBr3. CSPBr3 is one material. Why it is famous? It's a little stable. The structure is right. Don't forget about it. If you have a chemist, don't understand, you forget about that. That's the structure it is. So a paper came out somehow in 2015 November. 2015 November, this paper came out in Nanoletter, which was rejected drastically with a request from the author also in JAX. The editor rejected 2 times without sending out the report. But this one paper, Maxim Kovalenko, who visited me in the last year, he was telling this story. 258K downloads, and from 2015 November till today, the most downloaded in the ICS, in the most downloaded, most viewed, number 1, this paper. But close to, this is little old, close to 8,500 citations in the span of 5 or 6 years. So this is the paper when it came out. I was in US. I also didn't like it. I thought there might be some trap something. How can you have, they told that you take cesium, bromine and cesium source, bromine source and lead source mix in a test tube. And you get 100% quantum melt, 99 point plus. Just an unbelievable for a material chemistry. It is so easy to get such a bright materials. And they changed the chloride bromide update because these are ionic crystal, like a sodium chloride salt. You put it out, it goes in the moisture, they are unstable to moisture if you expose it. But how can the RGB colors, you get it out of your unity quantum efficiency? And it does not matter you have a quantum confinement good or nothing. Whatever you see, take their mixtures, check it out, 1:1:3 ratio, you get 3 colors. The background of this LED is what you see it out. The white color is a mixture of these 3 colors. Each LED is a mixture of white LED, is a mixture of 3 colors. And you see all RGB you get from this stuff, what in the those steps is your unity quantum efficiency. That's the beauty of this material. But then 3 or 4 years it has been gone. So we wanted, what are these inside? They are somehow, they are all cubes. When you see the electron microscope, they are looking the cubes. So these cubes are started from 2015 to 2020, 5 years. You do whatever you do, you come out with this tiny cubes. Whatever you want to change. You want to change temperature, ligands, X, Y, Z, you come out of this one. So then what happens, we understood that this is a crystals where the surface is, if you have a nanocrystals of crystals, where you have organics on the surface. And the organics are typically negatively charged ligands or something like a CO minus group or lone pair, because it is coordinate to the metal. But this is just contrary. This is something ionic part are there on the surfaces. They replaced by ammonium ion. Positive charged ligands or positively charged ions should be on the surface. That is what It's not following the classical mechanism which has been established by Bhubaneswar group and got the Nobel Prize last year. Okay, that the entire chemistry does not fit here. So this is what is a simple. You go hit out the organic ligands play. The ligands you take, you can have a shape, the structure exactly same on the surface format. So you choose, you change the ligands, you change it. So then what happens? I wrote in 2021, 6 years after this first came out. Then why do the entire community cannot go beyond a 6 facets cubes? That's the chemistry we wanted. Then we found that different facet has a different surfaces. On the different surface might fit for a different ligands on it. So we are, as a chemist, we need the ligands on it. So again you see here, 2018 also the paper came out which used the benzoyl chloride in the synthesis. Okay, that is coming out in the 2018. So then what happens? There is a Professor B.C. Ranu, known in ISS. He was working some nanocatalysis. So my students went there, can you give this benzoyl chloride, benzoyl bromide? So then they didn't found there at all. They found what happened, penicillin 1CH2 extra, which is giving here, as I was talking last year, SN2 reacts and then directly to bromine eject out. So then he came out with this one, fully accidentally, no way intention. So then what happens, when we do this is what? This is again 2020 we came up. This is just simple SN2 reaction, and this I had left in the OCS in the last previous year talk. So then it gives a ligands rather than the primary, the B is a tertiary ammonium. So two phenacyl site and one is the olein ammonium. That's by NMR and Marshall group. So then when they put exactly same what the thousands of paper, 4,000 paper came out, the same protocol by Maxim Koval by Shodan and later, we added just that which we got accidentally from Bisilam. So we got the module has been changed. It's a 12 faceted crystals. So basically it's a completely changed, accidentally we got it, and how this changed the field I will tell you out. So that's the size you could change it out when first because these are nothing much here. And see the assembly beautiful. These are not a lattice, this is a 1-1 particle. You see 1-1 particle here again. And the quantum efficiency is also 0.9. So the size does not matter. The quantum confinement is something where you go beyond 5 nanometer, you lose the quantum efficiency. That's what the Nobel Prize paper says. But these materials, you go 100, 200 nanometer, does not make any sense. Will reduce the quantum efficiency. So this is 12. I cut down this one. When you annul this one, all the vertex will be going out. That's going to be 26 facets. So exactly these structures came out like this. So now what happens when Q was limited, we moved it out 12 as well as 28 because this aspect ratio is a little bit different on the screen. So this picture goes up. You could see it out. So now what happens? You can have it, also the sign changes with the temperatures. So then go to the same slide I also told in the previous. So if you see the XRD pattern, see 0.5 is orthonomic phase, 0.5 beta 2. Total number is 6, that's what it is giving 6. That's what the one ligands previously done. But once we go this 0.41 nanometer despacing, then the total planes is coming 12. That's what we loved it. So that's why we got this structure. If you take this one, which is only one, total 8, it should be tetrahedron or octahedron. If you combine these two, it should be 14 faceted. If you combine again, these are the facets. These facets, you can have an 18 number of facets. This is simple mathematics. You calculate, you play with the. So you have to choose a ligands, or you can play the entire crystal structures. So that's the way exactly what happens. It was going on in the community. We used just this, which we got a CH2 extra, just one CH2 extra. So we got these ligands, and we found it out. We concluded who is the surfaces that determines the shape of the structures. Okay. But then what happens? What happens to the second one if you put excess of A, which does not lie to the B side, it is going out. Let's see it out. Can we change this one by adding the ligands? So we took A and B both are. From B we added. This is the B part. You could see it out. I've written A side. There are all the facets. A is connected that side because I don't have a laser. B is connected with the other side. In this case, you can say if I put too much A, it does not like the B side. It will cut down like this. So you are supposed to remove this. Okay, we use the diamond software to do it. You see the exactly what it is come out, the exactly prediction structures is coming out for being the 6 receptors. That you see that this is the hexapod structures. Again you go out. See, these are the images down are not done by us in ISS. It's done somewhere else that I'm talking about. This is good to see the structures here. And also you can have a restricted way of the change over. You can also coming out like this structures. So again, if you go for the 12 one also excess of A, then down the cut down the, because B lies, A lies in the different surfaces and B lies in the different surfaces. So similarly, if you go for 1D and 2D structures, you see it out here. I put a structure where is the only the completely going on in the Z direction. Showing out this structure. These have A side ligands. So if I put too much A, no change going on. On the other hand, if I took another rod, the synthesis is not here, but these are the rods where A and B both are there. See, these are the A side and this is the B side. Then I am putting too much A on it, or B side will be changing. Too much A I put, then B side are changing. And you see the structures here exactly. So basically, on the laboratory, we developed 2 ligands. One was traditional, another ligands we put a tertiary monomer. So the entire nanostructures has been changed. So now what happens here? When we are a couple of more slides before I move to the others, you could see it out exactly several ways is going it out. And the field was pretty hot that time. So before I go there, I will tell you the field was very hot on that time. So anything you do this structure, so it's going to be Harvard journals. Definitely it was going. But then there was a break on it. People are telling, why don't you take a second step on it? Why don't you do a different structures to combination? Why don't you see the atoms which are placement there? Why don't you see the chlorine atoms, bromine atoms? Why don't you see the cesium atom? Why don't you identify this atom? But you know that identifying each atom in the crystal, what is each atom, previous one, see I'm talking about here the HRTMC to do it out. So these atoms, they are telling here no bromine visible. Here is no hydrogen, oxygen, carbon not visible. All what you see in the TM are the heavy metals. So that is what the electron beam pass out of, all are C are the lead. What you see the atoms on the right side are lead. But it is a cesium, lead, bromine. For its bromine you find it out. So that part has, you need an atomic resolution microscope. That time India has only one atomic resolution microscope. This title was established in IISc Bangalore. And that was down in many times, we have to collaborate. So what happens, this time Professor V.K. Singh was their chairman. So I just put a proposal of 28 crores. They sent it to DSC, then I talked someone in DSC, they told they will have helping out. So then what happens? So then the project rejected by the director for 3 rounds. 3 councils got out, they didn't pass it out. So then there was a council meeting inside, I was standing outside. I said, in fact, I need to share in this platform. So then I sought an appointment to the council chairman and told that, let it be finished. I told, I don't have the time, I'm sitting here to give me a call. So then after some time, V.K. Singh called me inside. Then I told to director, put my proposal here. And director got furious that time, the person was there. And the put that he wants 28 crores money. I didn't want 28 crores. I want you pass the project. I just wanted you pass the project. I didn't ask from your 150 crores budget you give me. So anyhow, then many people ask questions. So many questions asked that. Then I told, you wait, you give us the money, you wait after 5 years, then you are going to ask me what's the value of this money, because people are asking. I have several papers or comments, show the atomic resolution, show us the bromine, hydrogen, oxygen, show the particular atom, point what is that. So you need even a much more bigger microscope analysis. So then what happens, I told you pass it, I am standing outside. So the meeting is completed, then somebody told that Narayan Pradhan locked the room. You have to pass it. So honestly speaking, I obliged to ISS passed, and completely ISS get the money, which is 28 crores. Facilities built up is done, and the final status we have not handed over yet, but so anyone wants to do it, obviously welcome. So we have the atomic resolution by GeoMat. So one of the best facilities in this country is already established in ISS. So probably this month, sometimes for January, they will hand it over to us. I'll show you some images. So that's why we took it out another road, which is going to be another direction. Suppose you have a cube. Cube can have go through a facet, can go through edges, can go through a vertex. So first one I saw through the sides, second one through the edges, and this one through the vertex. The directions of what? Vertex of the cube. So this is what it is going it out. If the vertex of the cube going on, forget about 201 something, that's what crystallographic way it is going on. But see the chemistry here. I put A on it, then what happens, you know? These rod getting spiral. The rod getting spiral, okay, on these gases. But because this is a corner way it is going it out. So you pull it out, again the spiral rods. This is what I got done because the A does not like B side facet. So I created B transport to A, nothing else. Every materials I am changing that using what we put it up. So we use that initial bromide. Now the sale of sigma is increased so that they have double the price nowadays. So you see the structure so beautiful. They are cube connected. All are cube connected through the vertex going on completely. Simple chemistry. So as we are focusing, so that means in the first one gradient effect, that is one direction. Second one is edge and third is the vertex. So again I wrote a perspective telling them this honey crystal perovskite, which is hot in the energy materials now, does not have any identity. For example, you have a zinc sulfide, woodgite, always give rods. If you have a spherical particle zinc sulfide, you say it's woodgite, is wrong. You cannot make a spherical particle of zinc sulfide which is a woodgite phase. Because the ZX is elongated very quickly, it drives you to a rods and wires. But then what happens here? I have time? So what happens here? This material is so soft, like a lata. Anywhere you can put it out. Can attend the same. It can have any direction it can go. That's why a preparer it does not prepare any specific direction like a zinc sulfide woodgite. It can go any direction. It can fall written any direction. That's the view in this. So after this one, there are the collaborative papers came out because I have focused on synthesis. I don't do anything beyond that. The first one is the synthesis. Second one was the single electron spectroscopy study by George Thomas. The third one is rods are showing chirality by Samabrata Acharya, who is my colleagues. So there are three and there are few more samples of this has been given to different groups in India. So exactly you see it outside platelet. I talk about cube, that's called isotropic. Then I saw rod, that's called anisotropic. I to go for the platelet. So platelet can be two types. One platelet you have cube cut down, that platelet is this. It is also A type. But another one, which is hexagonal, it's a different platelet. That's why simple I put it out, two directions, 001, 100. That is based on my crystallographic orientation, you don't have to worry about it. But then what happens here? Here we give A, no change, because surface is A. But the other one, if we give A, see how it happens. This is the original one, then we put A, this cut down on the facet. Because that surface does not like A. It does not like A. So that is what it changed itself. Look the structures. Applic acid is going out to be changing the structures. Okay. So now see how you can choose this where you can change it out. That distance you can change. That depth you can change out. Putting more phenyl bromide. Nothing else. So that's what it is going it out. That's also 2023 what's going on. So then what happens? So these are the 6 set of we put it out. That are the published 6 papers with ligand A access. Everything has been structured. Simple to go message is simple. A organic, tiny organic mighty having only CH2 extra than the traditional gave us this drastic change in the structure and in these new properties. That's it. So if you go for that heterostructure formation, that the main title was there. 2 structure combination. Heterostructures are there, but 2 materials combine. When the 2 materials combine, it's very difficult. Very difficult means they should have a lattice continuity, epitaxial continuity. So that means one is ionic crystal. You want to make a stable like cell on it, which should be covalent. Otherwise, it cannot be sustain water. So if you want a covalent, then covalent materials leak a ligands which is a negatively charged. Ionic crystals needs a ligand which is a positively charged. The bigger question with chemists in designing the materials. How can you make positively negatively charged in the one reaction solvent which will have a specific, the negative charge is covalent part, positive charge going to be a ionic part, two materials to be combined. It's a big issue, but how it is resolved, you see it out. We have resolved this. We could succeed. This Rakesh was working this 5 years, 700 reaction failed. Wanted to try to gold on it because gold is a plasma. To having a plasma semiconductor structure is failed. Completely 5 years. In the last one, he succeeded. Who is working with Hiren now, and also suffered a lot. Didn't have a paper to go for a postdoc from my group because of the completely failure of this project. But at the end, we go it out with a platinum on it. So platinum has been connected successfully. But now what you see it out, platinum, every corner it is connected. The corner is our phenyl bromide, not the benzoyl bromide. Corners are the phenyl bromide. So new facet, what we created, that broke the ice. That is what it is connected. So see here, it is the connected, epitaxially connected. Exactly the same principle. These are the structures again given in IC Bangalore, which we got now the system. Exactly if you put it out, it's going out. The same way as A we put it out, look at the structure has been changed. Exactly, structure has been changed. Again the structure has been changed and you see the effect. But here you see again the heavy metals, not the anion. Then you put silver, it's also Rakesh one, could not be published here because of, we don't know how, why it does not show the platinum. See again the corner, I want to show it out how the new facets we created, it is connected. See, all are in the corner which are coming out of the new. Go for bismuth also, the same on the corner, which is going it out. So the heterostructure which was a building, which was a blockage, is now solved going on. But there is a negative part I am talking. See, all those corners are going it out. Then we go for semiconductor. This is the last month we have published. Again with Rakesh, with the Hiren Ghosh. They exactly know nothing we did. We did the same literature protocol and put our seeds to extract. And you get it out the new structure connected, and this is the hexagon what you show, that is our 12 faceted new one. Exactly going on. I'm not going to. This is again taken it out from IIT Kharagpur, and here also you see the two structures are coming it out. This is the way we model how it is coming out. This is the latest one. So all those things in the left side we have done. The blue one has not been published, and the right side has no report yet. But then what happens, the bad part, everything equates the PL of neuroimmunity. That part is unsolved yet. I didn't show that part yet. We are trying to solve retaining. Then the last one is going out to be homojunction. I don't have much time. So synthesis I am not showing. I am showing a rod of same material. Then what it goes, I saw some material, somewhere we synthesize, there is a junction. But PL quantum efficiency didn't change, still remain neuroimmunity. So that means these are no defects are here. The effective forget, that is our crystallography analysis. This is the model we put it out, and the right side just I have to see there is a 1990 7110 where it came out. Okay. That's why this is a lead octahedron that is well known in chemistry. If it is a facet way, if it is a corner wise connected, that's the lead halide perovskites I am talking about. But there is other way it can connect like facet wise, but we saw it here. Circular facet they are connected like this. That's what it is coming out. And this is also giving a new kind of this perovskites materials without compromising the quality. You could see it out here, the structures. These are done in Titan Science Bangalore, and now we have established. You could see it out here, the atoms. Now you see here the bromine atom is inside. Exactly they are going out, goes by here. See here the materials are going out. The exactly prediction of the structures. And each atom you can identify, you can knock and find it out by EDS, telling what the individual atom is. They have a 400 square, there is 200 square feet EDS, but we took a 400 square mm EDS inside the kernel. And the last one, and immediately I got a perspective again. What is the two differences in the one CH2 PB versus BB? Benzoyl bromide and benzoyl bromide change the entire scenario. And this is the last piece work. It's also in a heterostructure. But I'm not going details, but I want to see something. It's a perovskites and bismuth heterostructure. But you go it out, I'm not showing this is one. It's the structures of collaboration, extensive reproducibility. But I want to show, because I may be out of time. The heterostructure showing it out, it is showing out in the intermediate how it is forming. This is the same structure. Look at this one. The middle one heterostructures we just deconvoluted going on. You could see it on the bottom, on the left and bottom of the right. I just said it myself. So what is the beauty is here? Look out how one single plane is divided into two. Look out the crystal at the junction where in the upper part has 1, 2, 3, 4, 5, 6, 7, 8 and below is 1, 2, 3, 4, 5, 6. You could see that how changes. One is divided. That's what that defect of the junction of the triplex damage it out. There is no defect overall, but there is a local defect. That's what the compensate. And we say it's an accidental plane matching. That gave us two materials to assemble in one platform. Again, every cases you go, this is the example, same way it is going it out. This is under-communicated. So we are all, and how if you want to form it out, there is a couple of slides remaining. See, this is what the nucleated that goes. This is what you see Haraf images. Then what happens, this is a solid type of catalysis going on the bismuth dissolved and it's going on. This is what it is going on the surfaces. You know, I'm not going much on this. Intention was to show the junction. This is what a metal is deposited on the surfaces, then catalytically it will grow and form like this. In summary, what I said here, that such a beautiful materials cannot be restricted as an ionic, blaming us if they need only limited. But we can make it heterostructures. We can make the surfaces variable, different facets going out. And today we failed to stabilize making a cell on it, but I believe with the coming days, these materials will be coming up with a stable RGB colors. And thank you.
Thank you, Dr. Pradhan, for nice presentation. Any questions from the audience, please? At least one question.
Okay, the very good orientation and the sense of the structure you are getting. My question is that you are getting the structure or you can customize the structure?
I'm sorry, but as I said, that it's an accident. Just like nature we observe, we never try, what we plan now does not go that way. We got something and try to investigate. So we searched for benzoyl bromide, but we got some phenyl bromide. Then we say let us try on it. Then that accidental was completely changed the standard on the surface.
But after the accidental discovery, all these are designed. Yes.
All these are designed, yes.
That's the.
And also not only this one, the sigma is in the thermal, all the chemicals linked to this we have searched and purchased. But till now something has not replaced this.
So what are you what you are predicting or what you are designing the same way you are getting or you are predicting something?
No. First of all, we understood how it is going. The second part we predicted. The first part, but then the materials property changes, na? And materials properties I don't touch. I just focus in one. So I find out the collaborator who can give them the materials and their
Different applications.
Yes.
Sir, about photoluminous decay, it was reported 1 to 29 nanoseconds. Sir, I wanted to know how this stability can be engaged in what direction actually can plan for the
This is the
material.
question where I was intentionally suppressed. See, all those high intense emission, the photoluminescence decay lifetime should be less than 10 nanoseconds. Less than 10 nanosecond, 5, 4, 5, that's the expectation. But where there is a junctions coming out, like homo junctions, then we found that there is a state which is remaining to the conduction band. So which is not reported yet, some theoretical we are calculating. That is the reason it increases the lifetime to 100 of nanoseconds. So thank you for noting that. That part I intentionally skipped it because we don't know much. It is not expected to be 100 nanoseconds. It should be 5 to 10 nanoseconds. Otherwise, you should not give it such a high quantum.
Any other questions, please? Our young students, question from our young students sitting over there.
See, I still work. I still work at least from my lab. from 6 o'clock to 12 o'clock. That is my time in the experiment when we were doing that. All the images I had taken myself, no student, no operator. And also we bought the new system that is designed for that I will be the operator. So that's what for the students I'm talking about, just have to work hard to make it. There will be finding it. We are also giving this, I was here in Niger 5 days before for 1 week. Again came here just 1 week. We are also visiting, but we are able to manage time.
Okay. Thank you so much, Professor Pradhan. Let us give a big hand.
Sir, I request the chairman to felicitate Professor Pradhan.
Second speaker will detail that again.
Now we have another speaker. Let us welcome Dr. Sanjay Kumar Sahu, the Institute of Life Science, Bhubaneswar. I am privileged to introduce Dr. Sanjay Kumar Sahu. He is a scientist at the Institute of Life Sciences, Bhubaneswar, since 2005. He received his PhD in the year 1999 from the University of Delhi. His scientific contributions include over more than 100 peer-reviewed research papers, including review articles and book chapters in leading scientific journals of utmost utility of quality in the field of biomaterials. Dr. Sahu has been granted 4 US patents, 1 European Union patent on nanotechnology based targeted drugs and gene delivery. Recently, one of the patented technology have been transferred to a pharmaceutical company in India for commercialization. Let us give a big hand for technology commercialization, which is my pet subject. Dr. Sahu is having high index 64 and ITER index 128. Total citations 26,581 through Google Scholar. Dr. Sahu's name has figured in the list of influential researchers of the world released by US-based firm Clarified Analysis on the basis of citations in 2018. Dr. Sahu has been featured as one of the top 2% scientists in the world in the field of pharmacology and toxicology year 2020, 2021, 2022 and 2023. Let us give a big hand to Dr. Sahu. It is studied by prestigious Stanford University, USA. His scientific and professional activities include editorial board member of Current Nanomedicines, Clinical Experimental Pharmacology, Nanomedicines, Fusion Medicines, serving section editor of Current Pharmaceutical Biotechnology and members of different scientific organizations of the country, of the world. Thank you so much, Dr. Sahu, being one of the great scientists of Orissa, 2% scientist by Stanford University. Thank you so much. Kindly proceed ahead with the.
Okay, thank you, sir. Actually, I am a chemist from Orissa. I did my BSc in Bhadra College. My teacher, direct teacher, Professor Sasabra Samal, Professor Yagin Das, Professor Ajay Kumar Patnaik, and Professor. But by virtue, I moved to Delhi. Then I did my master's and PhD. Again, the same way. I changed my field, by virtue. So because I did my postdoc in a cancer biology lab, and by the time I became a cancer biologist. Sorry for that, but again, my best advice, I think yesterday we discussed many things. So again, chemistry is the mother. Where you can move, you can move. That's why. Then I, so since basically I'm a physical chemist, but right now, if you can tell, I can maybe it will be difficult for me to speak 30 minutes in physical chemistry, but I can say speak for one day in cancer biology. So anyway, so the advice is, so chemistry is the best subject, move from any disciplinary subject. So what I will talk maybe next 5 minutes, So this is a nanomaterials for cancer theranostics. This is the hot field, I think these days, if anyone is going to die, either it is a heart attack or maybe cancer. That's why you see, cancer patients number is increasing meaningfully. So let me little bit explain, what is the theme and how we are working. So best thing is, if you look in 1960 and 2025, the percentage more or less same. The means, the diagnosed and the death. Why this is happening, we are spending a lot of money. Many, big research institutes are coming up. Very nice formulations are coming with very good chemotherapy. So what is happening? The happening is, the diagnosis. So again, I can say, maybe, you don't have much knowledge on that. Cancer is, when a pathologist is looking for, there are 4 stages. Stage 1, stage 2, stage 3, stage 4. So stage 1, stage 2, we call it is a early diagnosis. So if you are becoming the stage 3 and stage 4, that is late. So when that is late, so no one can help you. So because the cancer cells, they develop something, by secretion of some pro-inflammatory cytokines, many things, this is not the time to discuss. But they are ready to move from one place to others. So we call this is metastasis. So once there is a metastasis, no one can help you. So that's why doctor is telling, you may die in 6 months, 1 year, maybe 2 months and all. So next question is, so how the doctor is telling. So that means due to the conventional diagnosis method what we are using, so it is not enough to detect in the preliminary stage. So that's why the term comes nanotheranostics. So nanotheranostics, again, it is a combination of nanomaterials, therapy and diagnosis. So basically I will discuss, and more or less I will discuss what we do, because I am a therapy person, but by virtue, again, I can say, I attended a seminar in Nepal where in 2007 or 8, so where we want to discuss, can you develop some of the materials, functionalized materials for diagnosis. So I had a collaboration with the All India Institute of Medical Science. That's why we did. So again, these are some of the cartoons. I don't want to go in details. So what I mean, early detection is the best. So if you want to go for early detection, so then I can explain what are the, how we are, doctor is detecting you are in the cancer. That's why I'm giving these are the, you can get it in the Google, So the percentage is increasing, the breast cancer is coming up. Then there is the TNBC, triple negative breast cancer, what we work in our lab. Triple negative breast cancer again is, so simple way I can tell you, So breast cancer 5-year survival, it's more than 85%. Think of it. So because this is the external, anyone can find out if some lumps are there, then you are going for a mammography. So surgery is there and there is a very nice drugs. Doxorubicin or paclitaxel, you can go for a couple of chemo cycles and you will be cured. But the question again is when must be known there is a TNBC, triple negative breast cancer. There was no hormone receptors. So it's minus of your HER2, others, So then it is very difficult. And in the case of TNBC, the 5-year survival is only for 15%. That means how difficult it is, So that is the model what we want to do. Again, these are the detecting early detections, what we are going for. Again, this is what I wrote it, cancer diagnosis and its methods. So these are the techniques what we are using, and this is the cancer treatment. Yes, this is then again a little bit I can explain, how this nanomedicine is helping. So you I can go down. Yes. So then, So, nanomedicine, again, I can a little bit explain, So, what is happening? Think of what are the chemotherapy drugs we are using. More than 80% is not soluble in water. So, this is hydrophobic. So, once this is hydrophobic, just I am giving an example of paclitaxel, one of the best anti-cancer drugs used for all type of cancer. The question again is, if it is not water soluble, how the doctor will give, So that's why we are giving a, in the saline bottle they are giving, and they are using for ecremophore with absolute ethanol. It has a problem, So basically, if you can have a water soluble formulation, I think more or less 50% you can solve. So to make a water soluble formulation, so either you go for a pegylation, so PG, polyethylene glycol, these are God gift. Otherwise, you can develop some particulate system, nanoparticle, trap it inside the particulate system with some polymer chemistry, then make a water-based formulation for anti-cancer therapy. So, the second point is there is a EPR effect, enhanced permeability and retention effect. What happens? If you look at the tumor microenvironment, there is a leaky vasculature. The paper published from Hiroshima in 1986. And on that basis, there are 100 companies are working. I am very much fortunate, I did my first postdoc with Professor Hiroshi Maeda. So what happens? So if you have either it is a pegylated or nanoformulations. So then, the targeting ability in this like anything, it has a direct, you can target to the tumor site. So with this, these are the more or less what I expect, these are the arbitraries, yes. I have given a history, so this is the toxic. This is the doxorubicin based liposome formulations in 1995, FDA. And recently also there is a Abraxane. Abraxane again, this paclitaxel, developed by albumin nanoparticles to enhance the pharmacokinetics, PK and PKT. And also, it has a targeting ability, at the same time also reduce the toxicity. Coming to the nano, what I have explained, this is a therapy and imaging. So looking to this, I think the first talk what Professor Pavan gave, So again, transition metal of the properties, I am just going for one particular properties, So this is a T2 and T1 relaxation based on when you are going for a CT and MRI. So basically, what I will today cover part of my talk, synthesizing some iron-oxide functionalized nanoparticles for MRI application. So just again, my lab recently what we are working, so I can tell. I have already explained, this is happening in the metastasis. So these are the 4 factors. If you look, this is the cancer stem cells, cancer-associated fibroblast, and this is the TAM, tumor-associated macrophages, and drug resistance. These are the component in tumor microenvironment which is more or less inducing the metastasis. So all of my students are working on that in combination with some anti-cancer drugs like paclitaxel or doxorubicin. With this, these are the, I have given you a couple of papers what we published in the last 5 years. And I think what already the chairman given, so this is in 2018, it came up in Clarivet, and where I have shared with only 10 Indians on the list of almost 4,000 top scientists. Professor Shyamrao is the number 1, and I am the only one from life science part. These are the 2 products I have developed, and we have the US patent for this. This is a magnetic nanoparticles, and we have developed a magnetic kit for starting. I will explain, but I can explain here, So it is more or less, if you are a HIV patient, so there is a ELISA, they can, if you are going for a surgery or something, right now also the COVID is coming, So then they will go for a HIV test. So what they did a ELISA test to know real you have HIV or not. If you are HIV negative, then you are just going for a surgery. But now the question is, if you have a HIV patient, you are going for some drugs, antiviral drugs. heavily available, and it is subsidized by different Bill Gates and all. So now the question is, how you know you are a HIV patient? So that means if you are suffering from HIV, the T cells population, the T cells means the cells which fight for you. These are your so that percentage decreases. So how to know? So this is a diagnostic key. So T cells, more or less, this is the overexpress CD4. So this is a surface marker. So what we did, we had the next talk I will talk. So we have developed a water-based nanoformulation where I have conjugated CD4. So very simple, I can get your blood, mix it with our particulate system. So I will mix in front of you. Then I have a magnet, You see, this is a magnet. So I will pull it out by putting an external magnet. So this external magnet inside this, And this is we have designed, and this we have the patent for. This for the device also we have the patent. So then I can get it. What are the CD4 population? I will go for a fax, and I can say, you have this number of cells per T cells. So once you are giving, for treatment, so your HIV is decreasing or increasing. So this is the diagnostic kit what we have developed. The other one is, again, so this is we work in a curcumin. I have a couple of papers curcumin, This is healthy. Everyone is using, and more or less, in the traditional way, it has anti-inflammatory properties. So in the village, we have used, maybe when I had my mom give me the bath, they have also used in the home, this healthy paste and all. So then I developed a bandage. This is a Scotch bite. Very simple idea. We have developed a Scotch bite, but our novelty is, in the Scotch bite, I have developed some nanoparticulate system. I put that particulate system, so it will give a sustained release for a week. So you are getting some bandage from Johnson & Johnson. What you are doing, you are putting. There is no antibacterial, just protect your wound. So this gives a nice, healing properties, and you don't have to change every day. You just put a bandage, go home. Maybe after 7 days, it will come off. And the bandage is basically, it is a combination of chitosan and sodium alginate. So these are the FDA-approved biocompatible materials. So this technology we have. I have the US patent and European patent, and we have transferred this technology to a company in Rajasthan for mass production. So today, what I want to say little bit, magnetic nanoparticles, what we have synthesized in our lab for to make a theranostics purposes. So MLP can be stripped with a magnetic. I think I can show you. Yeah, you see. So a lot of work has been done in Europe to develop a magnetic nanoparticle based drug delivery. The beauty is, by putting an external magnet, so you can drag, because let you have a tumor in your breast, you are injecting some magnetic nanoparticles with the drug in the intravenous. So what happens? So then you put your magnet inside in external in your breast, it will drag the particles. So what happens, these particles, what we did, we put a hydrophobic materials. So a little bit we work in this. There is a concept of HLB, hydrophilic lipophilic balance. We put a macromolecule on the surface, because iron oxide nanoparticle is not soluble, not dispersed. This is a hard materials, inert materials. So we have a coat on the top, So where it has a cages, I can put a hydrophobic drug, I can put a hydrophilic drug, and at the same time, I can inject for a therapeutic purpose, and also I can go for a diagnostics with a MRI. So this is a T2 relaxation, So I can go for a MRI, and I can detect, your tumor is decreasing or increasing, whatever. Yeah. So this is just putting external magnet. How can I drag the particulate system to a particular to that box. Yeah, since Faima and she is now the professor in Sanchitan University, she really postdoc with me for, I think, for 12 years. And she is joining my lab, and now she is a research fellow at University of Illinois in Chicago. So they did all the work, and more or less, so developing a water dispersal MNP formulation. There are, if you look in the literature, there are 4 or 5 functionalized materials. This P3O4 is available. So there is a coating of PG, coating of dexter, coating of glucose. But if you go for the next, we have this. This is a GMO. This is a glycerol monoolate. This is we put on our particulate system and we develop. So, and the other point is we have used drug delivery, hyperthermia, imaging, stem cell tracking, and more or less cell sorting. Yes, this is, you see, this is a water disposal formulation what we have. This is the PM picture. And more or less the size is 7 to 8 nanometer. And you see, putting a in the down, putting a external magnet, how we drag on our particulate system. And also we have shown, it gets non-toxic at a particular dose. This paper we have published in Biomaterials. At the same time also we have the European patent and US patent having a water-based formulation of iron oxide nanoparticles. Next, in drug delivery again we have used a spheroid model. So it is an in vitro model. What happens, so in the tumor tissue, it is not a, the tumor, in the tumor is a 3D picture, the cells can go with the top, this side, that side, that side. So doing a cell culture, again what we have developed here, it is a sphere model. That means it is a protein sphere where, drug can go in couple of sides, from the top, from the bottom. So this paper we have published, and more or less, this is a European Journal of Pharmaceutical and Biopharmaceutics. Again, this is a delivery aspects. Next, already I have explained, when you have a tumor, you are going for a CT or MRI. MRI again, they are giving a contrast agent because to distinguish very nicely, you have to go for a contrast agent. I think gadolinium is highly used. This is a T1 relaxation properties. But if you are going for a P3O4, this will be a T2 relaxation. So with this, again, we collaborate with the All India Institute of Medical Science, and where we have basically this is a glioblastoma. Glioblastoma is glioblastoma is one of the toughest cancer. This is the what we call this is a brain tumor. Brain tumor again, the 5-year survival is only 5%. So that's why, if a person is suffering from brain tumor, a doctor know, I know, he or she is going to die very, very soon. And the other point again is also, initially if you go to ask a pathologist, it's very, very difficult to diagnose in the early stage. So that's why if you diagnose brain tumor, so by the time it is in the stage 3. So that's why it is very, very difficult, And the other point is, if you go to the Google, find out, there is a BBB. What is BBB? This is a blood-brain barrier. There is a, endothelial cells, there is a huge gap junctions, and, filled up with many things, they don't allow the drugs to cross to the BBB. So, we develop these things, there is a paper from Bhubaneswar group in Germany, they have coated with some PEO molecules. So these are the non-ionic, ionic, and these are the deuterionic surfactants, which have a hydrophilic group with some HLB value. So what we have found, since we have coated with a GMO with a HLB somewhere around 25-26, then we thought can it is going to the brain crossing the BBB. That what we have explained in this paper. Again, we published in this paper in Biomaterials in 2012. This is the other point. What I want to say. So when the cells are moving, so we call these are mesenchymal cells. So that means the tumor is in the stage 1, 2. Basically, these are the epithelial cells. This is a localized tumor. So what happened with time? They become mesenchymal properties, and they want to move. So we are using these mesenchymal properties, how to target to the tumor tissue. Again, this paper we have published in Advanced Materials. We have shown and we have developed a couple of animal model where we have proved, by leveling the stem cells, you can target to the tumor tissue. Again, coming to the hyperthermia, as you know, this magnetic particles is having a, it is a heat induction. What happened? This is a very nice story, So what happened, we are in the more or less our body temperature is 37. So if you increase the temperature up to 40 to 43, then also it kills the cells, they're lost on many things, So by using this hyperthermia again, we have proved, we have a, hyperthermia setup in our lab, and we have proved these magnetic nanoparticles also induce the heat and also kill the cancer cells synergetically. And that paper we published in this Material Science Engineering C. These are the couple of highly cited review articles we have published in DDT. This is one of the most vibrant journal. Again, what we have proved, these magnetic nanoparticles can be a good candidate for CNS delivery, including the cancer and all. This is what I have explained in my slide. This we have developed, and there is the only one company, Archnex or Imagenex in India, in Orissa. This is the only biotech company. We have a Professor Singh is the CEO. So we have a good relationship, and this already we have transferred, and this is available in their website, so you can go for. And this is we are ready for CD3, but again we are developing this for CD4, CD5, CD8, CD11, CD, and there are many. These are just cell setting to go for some disease markers. That all digital things. These are the whole 10 years. What I have worked. So this is a couple of papers, drug delivery, this biomaterials and pharmaceutical sciences, European, and drug delivery with hyperthermia, these are the papers, and drug delivery with imaging, we have a couple of papers we have published. And in cell sorting, these are the technique, the patented product we have commercialized. So summary, I can tell, advantage with a nanotheranostics is more or less what I have discussed. You have a targeted, you can target to the tumor musculature. Real-time monitoring, that is the same thing we are telling. This is personalized medicine. The concept is coming. So you inject at the same time. You can monitor or real-time monitoring. How it responds. So these are the future perspectives and advantages. Yeah, these are all my students, and more or less what I have shown today, the work done by Abha and Payne. So they did the whole work in magnetic nanoparticle based, nanotherapeutic approach. This is my lab, and I have many collaborators. I just put recent collaborators, Dr. Punit and Professor Santi and Rajiv. Rajiv is heading. We have a very nice zebrafish facilities, and very difficult these days, to use this xenograft mice. Very costly. One mice is 10,000. So it's very difficult. That's why we are using a zebrafish facility. The best way. For drug screening and whatever we are doing, to screen really it's working or not in the preliminary stage. Yes, thank you. Together of cancer overcome how we should find out. Please for a happy new year. Thanks.
Thank you so much, Professor Sahu. Any questions, please?
It's very nice. Nice means it's very good presentation. Not presentation, work. I just wanted to ask the magnetic nanoparticle, is it monomodal or it is monomodal? Particle is having like suppose 5 nanometer. You have only 5 nanometer.
Yeah. So no. This is what is a monodispersion or polydispersion. Yeah, this is highly monodispersion.
Highly monodispersion.
Yeah. So that's why I have shown a graph. So it is coming around 50% in 7 nanometer, and 20% in 6, then 4-5% is in 5. So it's 5, 6, 7, 8, 9, 10. So on an average, it's 7 to 8.
5 nanometers does not look too small.
Yeah. So if you look, silver nanoparticles, your Gold nanoparticles is 1 nanometer, 2 nanometer, 3
But
nanometer.
you need a high magnetic properties, no? For that reason, to increase the mass, no?
So our aim is again,
These are Fe3
yeah,
over.
so little bit I can explain it. So in drug delivery, two things is coming in mind. One thing is your particle size should become less, and the other point is, the surface will be hydrophilic. Many papers published, I think there is a 86 paper, in 1986 one paper published from from US in the journal Science. What they did, when they are putting a PG, that's why many papers are coming. So if you have a hydrophilic surface, it can inhibit, because what is happening when you are giving an injection, blood has a lot of hydrophobic proteins. So there is a hydrophobic interaction plays a big role, which gives the opsonization. That means it's allowed to go to the cells to the liver or opposites in the kidney, in the spleen. So to prevent these two things, you have to have a hydrophilic surface of your particles. At the same time, the particle size should be small. So basically, what I explained, since we had a discussion with the doctor from AIMS, so they want, that time they want, so if your size will be around 10 to 12 nanometer, so it will be a good candidate for CNS. So actually, on that basis, we develop these things. At the same time also, it depends how much coating you are giving. We have a just, we did that things published in this biometrics. We have a 3-layer of coating. Because we don't want much coating, then as per UV, again it prevents the magnetic properties. So that we have, standardized having a 3 coating. Yeah.
Excuse me. Yes.
Yes.
Excuse me. You're asking. So I was asking, what kind of metal organic framework you are using for this?
No,
You were showing some metal organic frameworks.
No.
MOF and transition.
No. This is I have shown the concept we are getting transition metals. So this is everything on that basis. But I never do on other things.
Sir, I have one question.
Yeah.
This slide
Excuse me.
was
Yes. Then how you are monitoring the toxicity of the dispersion of these nanomaterials?
So toxicity, we have many techniques. So first of all, we did what I have shown. I did a MTT assay, and also we did many markers. These immunological markers. So to confirm real it is non-toxic. At the same time, also in a long term there is no immune response from that. Yeah, we did it.
But I think, sir, the ITRS Lucknow CSR laboratory, they have worked on all nanomaterial toxicity. This is the lab of toxicity.
No, we have enough.
But in telling so must be, the data must be there also for the magnetic part.
No, we have I have shown only
One
so.
thing, just one. Anyway, it is a very good application. So
Yeah,
that
it is
basis you
basically
cannot actually
application.
think of anything. When in a body fluid and the nanoparticle goes, it has a hydrodynamic diameter.
Yeah.
Even if you put the coatings and other things, it actually doesn't work. It has an effect on the tumor and other things, but it doesn't actually
So
touch
that's
to
why,
the
ma'am,
tumor or something.
next to there I have shown a hydrodynamic diameter. It is 120.
Yes.
So because this when we are going for this is a zeta potential nano ZS. So what happens, so putting your hydrophilic macromolecules,
Yes.
whatever, the swells and it measures a
Body
hydrodynamic.
fluid, it has a
So,
hydrodynamic.
showing in TM it's only 10 nanometer, but going through a hydrodynamic diameter is coming around 120
But it
pounds.
has an effect on that.
Yeah.
Thank you.
I completely agree with you, ma'am.
Any more questions? With no questions, let us thank Dr. Sahu.
I now request Dr. Chitara Misra, the chair, to felicitate Dr. Sahu. Sir, get it. We need to felicitate. Now we have to move to technical session 6. Two talks are here, 3 talks. Professor Archita Patnaik, retired professor, Department of Chemistry, IIT Madras, currently visiting faculty IHR Barampur. Then Professor Asif Tripathi Memorial Award, Category 1, state government funded or state level colleges, universities or institute. It will be delivered by Dr. Ashish Kumar Jena. Third is Professor Ronald S. Patterson, Professor D.K. Jesti Award, and it will be delivered by Dr. Sabani Sotoswini Mishra from IIT Madras. And it will be chaired by Professor S.N. Mohanty sir, and Professor Surendranath Mohanty was a former reader and head of the Department of Chemistry, BJP Autonomous College, principal, retired BJP Junior College, Bhubaneswar. He was the former president of Orissa Chemical Society and very active social worker. Sir, I now request Professor Surendranath Mohanty sir to please chair the session.
So I will now request, good morning all of you, I will request Professor Archita Patnaik, the first speaker of these 3 talks. Let me say something about Professor Patnaik. Professor Archita Patnaik is currently a visiting professor at IHR Barampur. Professor Patnaik received her PhD from Banaras Hindu University after completing research tenure as an AVH fellow at NASA and NASA fellow and a Max Planck research fellow. She joined the Department of Chemistry, IIT Madras in 1992. Her primary research interests are molecular, self-assembly and functional materials. She has received many prestigious honors and recognitions such as Alexander von Humboldt Fellowship, National Aeronautics and Space Administration NASA Fellowship, Max Planck Research Fellowship, Third World Academy of Sciences Fellowship, Japan Society for Promotion of Science Fellowship, and Fulbright Nehru Scholar Fellowship, and many more. So I am in fact afraid of her. She has served as a member Subject Expert Committee for Chemical Sciences, Women Scientists Scheme, WOSA of Department of Science and Technology, India, and has been a SERB expert, SERB expert, I don't know the meaning of this one also, expert committee member in chemical sciences for early career research and national postdoctoral fellow schemes. In 2013, American Chemical Society has highlighted Professor Patnaik as one of the 30 Indian authors publishing high quality research in Asian journals. We should give a big hand for her. As an editorial advisory board member, she has served the Journal of Chemical Thermodynamics and Journal of Chemical Sciences. Let us hear to her. Professor Patnaik, please.
Very good morning to all of you. Thank you, sir, for a very, very kind introduction. I can see that he has gone through the web page very, very intensely. Thank you so much. So, at the outset, let me thank the organizers, Professor Das and Professor Achari, for having invited me to this wonderful gathering. Is catching? It's not catching. It's my breakthrough thanks to the organizers, Professor Achari and Professor Das, for having invited me to this wonderful gathering. Looks like Is it okay? touched me from yesterday for this particular gathering was the inauguration. The two compeers who have compared yesterday, it was spellbound to look at the kind of diction they had and the kind of verses they had really worded. For every single introductory remark, be it for the invocation, be it for a speaker, be it after a good talk, it was wonderful to really see the two young girls having worded beautiful lines. So thank you so much. Who are the two girls? I'm sure they are not there in the gathering. Kindly, okay, that was wonderful. Yes, thank you so much. So I think it is imperative on my part to say that I had not been really attending to Orissa Chemical Society's meetings, not by design. If I remember, in 1994, I think I had come for the first time just after joining IIT Madras in 1992. And today I'm standing in front of you. So with the bondage and burden that I'm carrying for the last 3 decades, I have too many things to say, too many things to converse, too many things to really reciprocate with you. And with the permission of the chair, I may exceed a few minutes. Kindly allow me, sir. So for today's talk, I've just chosen to talk to you on soft interactions at a restricted dimension. So we look at interfaces which are gas, liquid, solid, and liquid gas interfaces. Today's talk is mostly on the exclusivity of these soft interactions. Before I get into, I'm actually grateful to my students. They are the ones who became part of me, and this is where the life revolved around. And they are quite well placed in their own spheres of life and work, and I'm quite happy about the training that they got, the sanctity that IIT Madras gave them, and the sanctity that my lab gave them. So we have been focusing on structured interfaces, mostly looking at curvature control surface patterning by following molecular aggregation, wherein the molecular tilt became a very, very important facet. When I say it is the molecular tilt, I mean to really quantify the molecular order of a chemical bond. Is it possible to quantify the molecular order of a chemical bond, and if this happens to a particular single molecule which is restricted at a restricted interface, then probably the average orientation of an assembly will give you very concerted properties of the system. So this is where molecular tilt dependent electron transport has been very crucial to us, and we have had a good number of publications coming out from this. We tried out looking at interfacial polymerization at these 2D interfaces, and for this, if you see design amplifiers where donor breeds etc. diodes, they are either covalent or non-covalent. We've been looking at the lipids and supported lipid bilayers at interfaces and interfacial Janus clusters. These are bifunctional structures who have actually served as attofarad capacitors. And I will give you an example as to how the charging, that is addition of one electron or subtraction of one electron, is actually quantized. So such things can only happen at restricted interfaces, not at the bulk. And so are other choices were bio and photo-inspired surfactants. And we have dealt with the systems by making use of real-time polarized Fourier transform infrared reflection absorption spectroscopy. You are not seeing this. So this is FT-IRA spectroscopy that we have developed and we have established and fabricated in our lab, where you deal with SMP polarization of your systems. And following this particular spectroscopy, you can look at, essentially can look at the dichroic ratios, the 2D phase structures, and quantify the molecular orientation. So along with this, at the two-dimensional interfaces, we have brought in a very different electrokinetics by making use of microelectrons. So when the electro dimension diminishes, and specifically at these restricted interfaces, the kinetics and the dynamics of these electron processes, they change a lot. So following this microvoltammetry, we've been dealing with these attofarad capacitors, and various sensors have been developed at the two-dimensional interfaces. When you look at 2D, it's again imperative to really do a lot of electronic structure calculation. So we've been really intensely looking at and doing molecular modeling by actually doing the ground and excited state electronic structure calculation and restricted and unrestricted molecular dynamics, and all that. Believe me, I mean, for the students, I must say that I am not a theoretician, but you can develop yourself. So this is where and atomic level imaging has given us a lot of trust on the systems that we have chosen. Today I am going to speak to you essentially on the interfacial chiral recognition. Interfacial chiral recognition and the role of interfacial water in this chiral recognition is between a L lipid and a D amino acid. When you have a racemic mixture of D and L amino acids at the interfaces, how exactly the chiral recognition happens will be discussed by making use of this polarization modulated spectroscopy along with the ab initio molecular dynamics simulations. So before I get into that, I just thought of giving you a glimpse on what we have been doing over these last 3 decades. So we will be looking at the charge transfer in C60 based donor based acceptor diodes, which turned out to be excellent molecular rectifiers and molecular switches. Of course, their fundamental properties have been seen, and we will. So this is So is it clear? These pictures. I can see that there is a slight blurring. So if we look at the very first one, which is the molecular rectifier, so this is where the designing of this covalent diode was done by making use of a substituted fullerene and bringing in a carboxy bridge for a good electron transport medium, and taking a dialkoxybenzene, which worked as a donor. So in such a case, for the vectorial electron transport, you need to really follow. There are certain rules of thumb over there, which actually get into this geometrical asymmetry. So you need to bring in a geometrical asymmetry between the donor and the acceptor, and so that you need to really decouple the frontier molecular orbitals of these donors and acceptors, which ultimately tells us that we bring in reduced local electronic coupling, and there must be, of course, there is a finite voltage drop across this bridge. So this suffices as to what is designated as a covalent diode, and this covalent diode here is sandwiched between 2 electrodes, and we have been structure calculating. Ground state electronic structure calculation tells us very clearly about what should be the directional electron transfer in this. What is shown over here is the LUMO of the acceptor and the Fermi level of the N2 electron, they are resonant, whereas the LUMO of the donor and the Fermi level of the metal 1 are also resonant. So in such a case, we have tried looking at the electronic structure, directional transport, electron transport, effect of molecular geometry on the self-organization, which I shall be actually avoiding. The next part of the molecule that we have actually designed was again a fullerene C60 based structure. So this is N-methyl phyllorylidene, which has been coupled via an atom-based bridge with any dimethyl aniline. So in such a case, again, the charge transfer pathway has been explored out by doing spectroscopic experiments coupled with electronic structure calculation. And these are various routes that I have shown over there as to how the charge transfer happens. from an orbital context. To get back into the very first, so this is a depiction. So to get back into this, so the second structure is depicting the emissive H aggregates in optoelectronics. So our focus has been on molecular dimers, and these molecular dimers have been actually talked about intensely in the form of JH and oblique dimers. But if you look at their geometry intensely, then the geometry in the conformation actually affects their optical behavior. So what is shown here is the direction of the transition dipoles of two monomers. So direction of the transition dipoles of the two monomers, and these two monomers, so R is the distance between the molecular centers, theta is the molecular slippage angle which is subtended between the two monomeric transition dipoles, and alpha is the polarization angle. So depending on these three coordinates, the geometry of these dimers actually depend on very strictly. So one of those angles, if you see the coefficient stacking for the H aggregate is attributed to theta 9 between 54 to 90 degrees, whereas the head to tail stacking is always less than 54 degrees. Now if you look at this, so this is a little more details of what we just saw in the previous slide. So in here we are looking at both the angles, and for the H dimer, you see the H dimer, which is a cofacial stacking, your alpha is 0 and theta is 50. And in case of J dimer, alpha again is 0 and theta is 0 over here. So, and if you see the oblique, where it has a positive, it is finite alpha. So such things are reflected in your UV visible absorption spectrum as well as your photo emission spectrum. So now if you see, so J aggregates, mostly the J aggregates, they give us aggregation induced enhanced emission. That is because this is a symmetry allowed transition, and when you think of this monomer getting excited to S1, and this, if once it became a dimer, the energy levels split, and there are two different, I cannot show anything. So there are two different states in which in one of those conformations your resultant transition dipole is 0, in the other one the resultant transition dipole is finite. So for such a case, this transition is allowed, and so therefore for a J dimer, which we see very simplistically in the UV visible absorption spectrum with a redshift, for a dimer with respect to the monomer is seen as a redshift in the UV visible spectrum. And for H dimer, if you see for H dimer, this, if you look at this cofacial stacking, but this conformation, the transition dipole is 0, and that is finite, and hence this is a dipole forbidden transition, and for H aggregates we do not see the aggregation induced enhanced emission, and for this, but in this particular instance that we have had, I have just shown you in this slide, here, what we have observed by making use of these, bringing in this algebras and this particular covalent diode, we have seen that this forbidden transition was partially allowed. And so these structures and these chapters have been really studied very intensely by making single crystals. And if you look at the single crystal structure, this particular conformation over there is allowed. It is actually giving you a finite emission in this particular case. Whereas this is a dipole forbidden transition in this particular instance, this is making it. So the solvent polarity actually has controlled this particular transition. And so the third picture that you are seeing, I have denoted this as a CT active non-covalent diode. It's a very, very simple system. What attracted us was that you have a spherical electron cloud and you have a planar electron cloud. So what is that? This planar electron cloud is nothing but pyrene butyric acid. You've used a base and you have just extracted out that protein. So this pyrene butyrate And this fullerene C60, which is functionalized with N-methyl fullerene, has actually given us a very fantastic information and insight. Okay, I forgot to show you this, that we have had this unusual, I'll just go back one slide. As I showed you, one example of an unusual H aggregate where we saw finite emission. Similarly, we are seeing here unusual non-emissive behavior of blue-green J aggregates. This assumes we have dealt with. So those J aggregates have shown, they were non-emissive. In actual case, they are not to me. So in this particular instance, we have actually done very detailed work and have attributed this to high probability of singlet fission by computing these structures and looking at the energetics and then seeing what would be the probability of the triplet recombination. So coupling all this, we've concluded that these J aggregates that are coming out from the blue-green dimer, and these are dimeric aggregates, they are unusually non-emissive, very unusually non-emissive. And in between, so I just spoke to you about attofarad capacitors, where you can, in principle, do this capacitance tuning. That because you're doing these experiments at the interface, so what is actually synthesized at the interface is a Janus structure. What is synthesized at the interface is a Janus structure. The core is a gold nanostructure, and you do have two dielectrics. One is a liquid, the other one is an amino acid. So you have a small metal-like core with a dielectric. You can attribute this as a quantum capacitor. And this is what I was saying, that once you add one electron or take out one electron, this gives you a quantized property of this system. And what is shown over here, if you see this current, this is the differential pulse photometric behavior of this. So you can see the anodic and the cathodic parts showing you single electron addition or subtraction events as quantized events. And by making use of quantized double layer charging models for these quantum confined systems, one can calculate those capacitances, and so there is extremely low capacitances. And what is so specific about the bifunctional Janus clusters, you can see a degree of enhancement in the electron transfer rates. As we can see, this K apparent is actually 10 times higher than the normal clusters that we synthesize. And so this the other example that I was saying is as to how the through bond-induced interactions influence the through space interactions. So this was this typical example, and this is a non-covalent dyadic system. What we have actually observed here is significant deformation in the aromatic plane of the pyrene butanoid, and that indicated two interaction sites within the van der Waals interaction distance, and so it has brought in a fantastic overlap between a spherical electron cloud and a planar electron cloud. So this is these are all computed over there. So what you can see is the binding energies. These are all BSSC corrected binding energies. So it's a huge. The magnitude of this is quite huge compared to if you take a spherical structure like pure fullerene and you take just the pyrene and you look at these planar and these spherical structures, and there is absolutely not much of stability between this. So what you can anticipate over there is just the pi stacks. So this kind of binary structures which are non-covalent have been really computed, and we can do this energy decomposition analysis to look at and to quantify to what extent there is charge transfer. So ultimately, the inference that goes from this work is that the hydrogen bond-induced pi depletion has been made as a criterion for pi stack. So this pi stack actually follows, first of all, the through bond interaction between the two bifurcated hydrogen bonds that have been formed over there at that butanoid, pyrene butanoid with this N-methyl fluorophenoidine. And what was wonderful to see, because of this coupling between the spherical and the planar electron cloud, we have had these two-dimensional dyadic factors which were emissive in a big way, which were emissive structures. So this is a detailed calculational aspect that you can see what kind of interactions you can actually anticipate from these two simple systems when they interact. So you have charge transfer, polarization, frozen density, and so on, and the total interaction. And you can speak actually about the directionality of charge transfer, the extent to which, how much is the charge transfer, and so on. So these are just the reviews that I thought of giving. So these are in a way the preludes that we have actually done before switching over to the soft interactions at the interfaces. So there was a paper in 2015 in the Journal of Chemical Physics that was a special volume which was giving a lot of wonderful narration on supramolecular assembly at surfaces. And for any practical applications, you require long-range order and 2D specific pattern. So for two-dimensional pattern formation over a broad length scale, we require versatility in molecular synthesis, and the physics at the interface actually affects these synthesis and the characteristic of the systems that are formed. So these are all non-covalent interactions as we see, and so one can essentially tune the electronic structure and the transport behavior for this kind of system. So this is one such example that we did in collaboration with Nagoya University. So this is a macrocycle. Actually, this is a carbon-rich macrocycle which was synthesized at the Nagoya University, and we have done a bottom-up fabrication for the large-scale formation of carbon nanosheets. And these carbon nanosheets were formed without, because they are self-standing films, they, even after carbonization, they maintain their morphology over there, and they have been made without a carbon template. So what was so specific about them? So they retain the actual morphology at the interface as it was in the interface, and their conductivity was very, very large. If you look at the current and the voltage, the pristine films had huge current that was drawn from the system, and it was nitrogen doped, and that has enhanced this conductivity. What was our part in doing this experiment was to actually quantify the molecular order, finding out the average molecular tilts by making use of our FT era spectroscopy that I'll be just narrating very shortly. So why molecular orientation? Is it possible to really quantify the molecular order? And why is it necessary? We all know that electron transfer is highly a directional event. And in molecular electronics, we have seen that, again, the ultimate charge transfer resistances could be very, very different depending on what is the molecular architecture. So it becomes imperative on our part to really estimate these molecular tilt angles by making use of real-time spectroscopy. So I have actually forgone what I have forgone is a self-assembled monolayer which is taken on a substrate. So this is air-liquid interface and essentially air-water interface. And at that, what is shown over there is the orientation of a lipid, of a simple lipid whose alkyl chains are shown. And if you have to really quantify the molecular order, this is the tilt angle with respect to the director. And what are shown in this kind of amplifiers are, in essence, are asymmetric and symmetric. See its stretchings. So, then when you do this and acquire these reflectance observance, then this intensity of these reflectance observance conditions are actually proportional to the square the modulus of the transition dipole and the electrical vector of this. Theoretically, this is given as such. So what we, in essence, what we look at, therefore, is the cos square theta, is the molecular order. Experimentally, we just look at this in a KBR pellet and get this reduced observance of this particular, of one of the vibrations, and so that actually this ratio gives us cos square theta, which is the molecular order in a sense. So if you calculate such parameters, you would see that when a typical lipid is taken over water surface, its the alkyl tilt angle is 26 degrees. The moment you bring in here a typical amino acid, so the tilt angle changes by 20 degrees, imagine. So these, you have just few molecules over the water surface at the interface. So this 10 degree variation is a huge variation. And so when there are helices formed at the interface, you can study chiro-optical properties. So we have had chiral gels, chiral vesicles formed at the interfaces and studied. So this is the way you can, in a way, find out the molecular tilt angles by making use of polarization modulation. So today I decided actually to give you a detailed account of a piece of work that we published in Journal of Chemical Physics in 2015, and so this actually narrates the structural dynamics of water vis-a-vis phenylalanine recognition at a DPPC lipid interface. So characteristic hydrogen bond times and ADMP, atom center density matrix propagation. This is an ab initio molecular dynamics method which has been adopted over here in order to look at the critical interactions. So we have looked at preferential and enantioselective interactions of L and D phenylalanine with L-DPPC as host, and these were real-time tapped by the FTIR spectroscopy. And what we have found essentially is that the D enantiomer, the molecular recognition of the D enantiomer is driven by the DPPC head group by a hydrogen bonding. And we see the real-time FTIR's water bands were strictly conformation sensitive, and the effect of microsolvation on structure and stability of 1,1-diastereomeric lipid amino acid atoms were really discussed via the ADMP molecular dynamics approach. So we'll go one by one. So what we see here is the depiction of the L-DPPC lipid, which is a chiral center, as we all know. And so this is a butoxy peptide, phenylalanine. So we are, in short, we are calling this as DPA. So this is the D-phenylalanine on top, and that is the L-phenylalanine. Just the butoxy protection was brought in order to enhance the proton donor and proton acceptor sites in this case, and these are all deuteranic systems. We are not going to discuss about this. And so the optical coordinates of that interfacial monolayer. So we have at the interface this L-lipid which has been sprayed. And if you look at, because this is a non-linear spectroscopy, you are varying S2P polarization, you have different optical constants, and these are actually governed by the, when you acquire these reflectance observance, they are all taken up by the Fresnel's equations when we measure the reflectivities via the Fresnel's equations. So this is an experimental scheme. Just title this as FTIRS is an analytical spectroscopy for chiral recognition of amino acids. And these are all real-time experiments. So what you see here is you have the water phase, you have the air, you have the optical constants of air-filled water, and you have this amphiphile. This amphiphile, which is a lipid, is standing in a certain fashion. This is an idealistic view. This lipid might be has a finite molecular orientation. So what we measure here is the reflectance observance versus the desired angles of incidences and polarizations. So this was a setup which was actually built in the lab. You are seeing that the system mimics. The system actually mimics this air water carrier, and so you have the system, and you have attached with this is a normal FTR spectrometer. Original plan was to couple this with a microscope, but that did not happen at IIT Madras. And so what we have been really acquiring with a mercury cadmium telluride detector coupled to this, we have been acquiring these real-time reflectance observance signals. And so this is a macroscopic visualization of phenylalanine. From these are the experimentally measurable parameters, and from this we calculate the binding constants. As you can see, the binding constant is maximum for this L-DPPC and D-phenylalanine, which is a red trace over there. And so these binding constants are actually tabulated over there. So KD to KL ratios have been plotted, and this is peaking at a particular surface pressure. So since these molecular films are two-dimensional and are taken at the interface, so this KD by KL ratios are quite maximum at a surface pressure around 35-30 or so. So at this point, our experimental validation to this phenylalanine recognition went by bringing in the role of interfacial water. So interfacial water has been discussed by people who do second harmonic generation and all. So such things, in absence of such infra, so what we have actually done are these two-dimensional experiments. So how much does the interaction of water affects the interface or influence the water dynamics? Does the water dynamics influence the structure at the interface, and does the geometry of the interface matter at all? So to understand this, when you look at the ES spectra that have been acquired, so what is shown here is the only the OH stretching frequency region from 4000 to 2800 under two different polarizations. So if you look at these, the traces, the traces of L-DPPC with D-phenylalanine and L-DPPC with L-phenylalanine, you see that for the p-polarized spectrum on the right hand side, we simply have a baseline. Whereas you see finite structure, very fine structures for the S-polarized units. And if you deconvolute this in terms of the molecular structure, because the OH stretching frequency is a very wonderful representative of the local structure. So what has been done in this particular case is the deconvolution of this region. And so what you get is actually a conglomeration of 5 different categories of water structure. Water can be monomer, it can be a dimer, can be a trimer, can be a quadromer, can be a pentamer. So what is known in literature, the tetrahedral dice model of water is very beautifully talked about in literature. So if you look at this, the double donor, double acceptor model of water, and you do here an ab initio molecular dynamics, which we call as AIMP. So this particular dynamic simulation, it has been engraved in Gaussian line. Yeah, I'll take 5 more minutes. And thank you so much. So what we see here is in course of time, so almost 1.2 nanoseconds, when you see the hydrogen bonds, they reorganize. And this pentameric water actually breaks down into trimeric water. So what we see, that there is a trimeric water which is stable even at 1.2 nanoseconds. And these are the experimental data. So deconvolution gave a very large population of trimeric water over there. So therefore, we see in real-time spectroscopy, the trimeric water is heavily populated even at 300 degree Kelvin. So, and there is a beautiful map of the water structure. So you have just the liquid with the water, and that we have said that the population here is 54% for trimeric water. And similarly, if you see the DPPC, the L-DPPC with D and L-phenylalanine, the trimeric water population still remains very strong. And what we have seen also, at the same time, we have seen the IR frequencies for PO2, OH, because these are all hydrogen bonded. So you can see those respective ion frequencies to corroborate with the simulation. And so now, if we look at the lipid phosphate microsolvation by this trimeric water. So what I'm doing here is I'm just taking, this is the phosphate, this is the head group of this lipid, I'm bringing in a trimeric water, and I just look at the static evolution of this trimeric cluster still remains as a trimeric cluster. The trimeric water still remains as a trimeric water structure, whereas in 500 femtoseconds, what we are observing is that the phosphate group of the lipid is promoting formation of water pockets. And in these water pockets could be excellent carriers for the phenylalanine recognition. So time evolution of hydrogen bond formation suggests very pronounced clustering, so giving rise to a water pocket. Now just to have a look at the static model over here, we see the lipid, the energetics of lipid phosphate microsolvation. So in this case, we have 2 degrees of freedom. We have one single water molecule is being brought to the phosphate because this is the microsolvation at the phosphate site. So we get these energy landscapes, and from these energy landscapes with these 2 variables. One is the dihedral angle across OH, the other one is the distance between of the hydrogen bond that is being formed. So we get 2 different conformations. One is the symmetric double donor, the other one is the asymmetric single donor. So what we see is this particular case, this is a single donor, and in this case we have symmetric double donor. This water is behaving in relation to the phosphate of the lipid, is behaving as this. So this is typical calculations of the hydrogen bond. So now in this particular case, so I just 2-3 more slides and we'll be just winding up. But what we are looking at here is essentially the recognition. How this phenylalanine amino acid is being recognized by this DPPC lipid. So what we have here is this, the amino acid, and this is the lipid, and we do have, if you look at the dynamics, at this point the trimeric water is still retaining. So in this bimolecular association, this bimolecular association is driven by the formation of new hydrogen bonds. And these new hydrogen bonds have been tapped by doing this real-time spectroscopy exactly at the air-water interface. And they really they comply very wonderfully with what we see from the simulations for this typical hydrogen bonds. A similar case with the L-phenylalanine with the L-lipid was also seen with trimeric water, but this adduct is less stable by a few kilocalories per mole. And so what ultimately we conclude here is that these multiple hydrogen bonding networks, they stabilize this to a greater extent, but we did have a better affinity of the D-phenylalanine with the L-lipid rather than the L-phenylalanine, which has been evident from the populations of this trimeric water cluster and from the magnitudes of these hydrogen bond energies. So this, to conclude, dynamic and structural roles of water. What did water do? So there was no direct interaction between the lipid and the amino acid. First of all, the microsolvation happened at the phosphate site, and the conformation was made in such a way that the amino acid interacted with this primary water with the phosphate conformation to give rise to specific So water cluster around lipid amino acid make the secondary structure predicting evolution of possible vibrational bands. And so to conclude, that the most important observation from this task, from this experiment cum simulation, was that direct interaction of water with phenylalanine was not observed. By a cooperative mechanism, PO2 minus hydrogen bonded with water and initiated the hydrogen bonded interactions. So my grateful thanks to all these funding agencies, and I thank you very much for your attention. And the dear corridor of IIT Madras cannot be forgotten. In a way, I miss the dear corridor immensely, and I'm very grateful to the institution for having provided this site, for taking up these kind of complex experiments and trying to obtain something which is readable, something which is doable, something which gives us some insight onto unusual problems. And thank you very much.
Thank you, Professor Madam. Is there any question? Something of the kind from the audience? No. No question. Okay. Your presentation is very nice. Let's give a big hand in favor of Professor Patnaik. And I now request the come over here to there should be a felicitation program. Please.
Camera flash আছে সেই ক্যামেরা ফ্লাশ আছে
Okay, the next, we'll pass on to the next presentation. It is in fact a memorial lecture, R.C. Tripathi Memorial Lecture. The first one is Professor R.C. Tripathi Memorial Award, Category 1, State Government funded state level colleges, universities, institutes. And the person presenting this one is Dr. Ashish Kumar Jana. I request Professor Jana, Dr. Jana, to please be present over here, and his topic is synthesis of medicinally relevant nitrogen-rich heterocycles via oxidative carbon-nitrogen bond forms. And what is the timing, Professor Jana? 20 minutes, okay. 20 minutes, the whole timing. 15 minutes presentation, and any question? No. Memorial question? Memorial question? Question answer. Okay. So 15 minutes presentation and 5 minutes will be question. Okay.
This is the Professor R.C. Tripathi Memorial Award. So during my MSc, we are staying in his house on the right. So 5 years I stayed in his house, and after my MSc I pursued PhD. So he read the books, the current books in chemistry, Cotton Wilkinson, Bhubaneswar, all those books through the lens. And he underlined every line where he had some difficulty. Then instruction was you have to go ask Ravi for Ravi means Professor R.K.Nanda, Anadi for all these people, and give a write up. Then I have to read again. So at the age of 90, he go and thoroughly read all the chemistry books, and any questions then he write and give to all of their juniors. And at the age of 90, he is staying alone, and he is a man, a very practical person. Never go to any doctor. Never go to any doctor. and he has some eye problem, and he will come to our home, means his house, that only if I is there, then I will put a drop in his house. If any of the family member will drop, then he will not allow anybody to put eye drop in his house, because normally he give that since they are doing titration, they know how one drop is very important. So only chemistry people can know quantitatively how one drop is important. So very practical man. After 90, he is staying alone, cooking his own, without taking any help. He is very practical man. So my respect to Dr. Tripathi is that Upanishad and chemistry is a fashion till 92. He expired in 92. But chemistry book is with his bed. And in his room, he has 7 kids, those who are at the age of, say, he retired from 1954 from Ravenshaw College. And he stayed up to 1992. And there is a board in his house, room. So I told sir, why this board is a big blackboard? So that means his elder son will teach to the third one, second will teach to the fourth one. Like this, they have to give the training that if a teacher will teach, then he has to build the confidence. Means when his son, first the elder son was in the standard 7, he has to teach the third son who is in the standard 4. So pure teacher, and he trained all his children also in that line. So thank you.
Good morning, respected professors, my director, Professor Satyavan sir, distinguished scientists, and my dear participants. First of all, I thanks to Orissa Chemical Society for giving me a chance to present here. So I will discuss on nitrogen-rich heterocycles, sustainable synthesis to material applications. So my deep respect to Professor Archit Batsal, who is a experimentalist during his time at Ravenshaw College. So why we are interested for heterocycles? So nowadays, majority of tests acidity present, and if you go to your doctor may prescribe you a drug called reviprazole or pantoprazole, and if you closely observe the structure of reviprazole or pantoprazole, that contains 2 heterocyclic moieties like pyridine as well as dense imidazoles. Few years back, we faced the deadly attack by COVID-19, and during that time, many repurposing drugs were prescribed. One such drug is favipiravir, which is a pyrazine-based, small molecule-based drugs. Very recently, Food and Drug Administration prescribed an oral drug called Zuralons for the postpartum treatment. And that also contains a heterocyclic moiety like pyrazines. Apart from the applications of the N-heterocycles in medicines, the N-heterocycles also applied as materials like energetic materials, like sensor material, like disease detections. So due to the wide applications of N-heterocycles from medicines to materials, we are interested for the synthesis. And very recently, we are synthesizing few heterocycles like imidazopyridines, pyrazoles, pyrazines, and imidazothiazoles by a sustainable method from simple precursors. So today I will discuss how we can synthesize these pyrazines by using very simple precursors like ethylene diamines and acetophenone derivatives. Then we further apply these pyrazine derivatives as luminescent probe for sensing of iron as well as develop fluorescent ink. Also, I will discuss in a snapshot way the synthesis of pyrazoles as well as imidazopyridines. So the importance of the pyrazines can be visualized by the presence of number of drugs like favipiravir, pyrazinamide, allocastins, brotrazine A, etc. So due to the importance, a number of methods have been developed, but major of the methods have some limitations. Like if you observe this method, you can see these are the symmetrically substituted pyrazines, and that can be synthesized using some complex catalyst like manganese complex. And only one example is there. In the second case, they have used ruthenium nanoparticles, which is supported over xanthos, which is a very expensive one. And also they are using some temperature like 150 degrees centigrade. So how we can overcome these limitations? Then we go for electrosynthetic analysis, and we thought if we disconnect these carbon-nitrogen bonds, we may get a synthenes like phenyl glyoxyls, synthetic equivalents like phenyl glyoxyls and 1,2-diamine derivatives. But that phenyl diamine is not commercially available. So we further simplify it, and we thought we can prepare these pyrazines by reacting diamines with acetophenyls. But the problem is, although this condensation of amines with carbonyl compound is very easy, but the CN bond formations, particularly between the methyl group and this NH group, is difficult to us. If you ask oxidant for the oxidative CN bond formations, that may result in side products like reported by these 1,2-dicarbonyl amines. If you change the conditions, if you change the catalytic conditions from copper to irons and change the oxidant, that also resulted in beta-carbonyl amine derivatives. So for the last couple of years, we examined the catalytic activity of the nanocatalyst. Once we change the compositions or size or morphology, the reactivity completely changes, the selectivity changes. So we thought, so can we apply the nanocatalyst for such type of reactions so that the CN bond formation becomes easier? So we thought, if you add a nanocatalyst, that may attach at the nitrogen center, and that facilitates the attack of the terminal amines to the methylene moiety. So with that, first we prepare some supported metal nanocatalyst. Why we take supported metal nanocatalyst? Because nanocatalyst has a tendency of aggregations. If you prepare the 3 nanoparticles, so that will aggregate. That means the reactivity will decrease. So if you add a support, so definitely we can increase the reactivity. Second thing, if you add a magnetic support, we can easily recover the catalyst by using a simple magnets. And the next thing, if you add the support, so there may be a metal support interaction, so that may alter the reactivity, that may enhance the reactivity. So with that idea, by a simple method of co-precipitations followed by wet impregnations, we prepare copper decorated ferrite nanocatalyst. So then we go for the optimization reactions. We have students acetophenol and ethylene diamine as the model substrate, and carry out the reactions using different copper nanoparticles like copper 1 and copper 2. But initially when you apply copper 1 nanoparticles in different solvents, the yield is not that much enhanced. So we thought, why the yield is not enhanced? If you see, in my discussions of this work on storm flux, that is the byproduct using copper 1 as well as iron 2. So similar type of product we are observing. So that's why the yield is not enhanced. Then we're adding some additives like lithium chloride, zinc chloride, potassium bromide and potassium iodide. And interestingly, when we are adding this potassium iodide in presence of Fe3O4 corporation nanoparticles and DM as a solvent, we are observing around 92% yield of the products. So this iodine may help to overcome that oxidative decomposition product. So that's why we are getting the highest yield of around 92%. So these are the proton as well as carbon NMR product of the synthesized compounds. So after establishing the optimal reaction conditions, then we want to expand the scope of the reactions, and we carry out the reactions by reacting differently substituted acetophenons with ethylene diamines. And interestingly, we are observing good to excellent yield. Acetophenons bearing electron donating substituents like methyl, methoxy, 1,2-dimethoxy, as well as amine at different positions like ortho, meta, and para, the reaction proceeds well. Similarly, the spherical hinder substrate like ketones of naphthalines also related good to excellent yield from 72 to 92% yield. Similarly, when we react electron-weighted acetophenons, we are also observing satisfactory yield of the product. The reaction proceeds with heteroaromatic compounds like ketones of pyridine as well as thiophene. But in case of furans, we did not observe any product. Rather, we are observing some decomposed product. So after successful synthesis of these two RNA substituted pyrazines, our next target for the multi-substituted pyrazines. Because already I have discussed that the limitation is the synthesis of symmetrically substituted pyrazines. So that is the limitation. So we thought, can you synthesize different products other than this one? So for that we react cell-stupinone derivatives with 1,2-diaminoproteins. And in this case also, we are observing, in majority cases, we are observing a mixture of product because of the differential reactivity of the 3 amines as well as the amine attached to the methyl groups. And that is the single crystal XRD of the 5-methyl 2-phenyl pyrazines. So after successful synthesis of a number of pyrazines derivatives, then we want to investigate the reaction mechanism, how the reaction proceeds, in which way the reaction proceeds. So whether the reaction proceeds in a free radical manner or in an ionic intermediate one. To know that one, we have added different free radical scavengers like BHT and TEMPO. But when we add also the BHT and TEMPO, we are observing around 72 to 82% of A. That means the reaction did not proceed through free radical one. Then we thought, can a condensation reaction proceed between carbonyl compounds with amines? So to know that one, we react these phenyl glycols with ethylene diamines. But still, we are observing a minute amount of the product. That means this phenyl glycol may not be an intermediate. And what's the role of oxygen? So to find out that we carry out the reactions in argon atmosphere as well as using copper-1 nanoparticles. But also, we did not observe any product. So that means oxygen has some role. Oxygen has a critical role, I can say. Then we propose this mechanism where the first step proceeds by a simple condensation of amines with the carbonyl compounds to form this imine derivative, which we can detect by LCMS. Then this imine derivative transforms to another intermediate, that is enamine B, and at this stage, copper undergo associations to form the intermediate C, where the nucleophilic addition of the amine to the CH2 unit occurs to form the intermediate D, and there is release of copper-1. Again, this copper-1, in presence of oxygen, transforms to copper-2 and again enters into the catalytic cycles. The intermediate D, in presence of oxygen, undergo dehydrations as well as aromatizations to form 2-phenyl pyrazines. And this work was done by Dicker, who was already submitted her thesis. Also, we prepare in gram scales, and in this case we are observing slight decrease in yield. When we prepare the milligram scale, we are observing around 90% yield of the product, but here we are observing 82% yield of the product. Then since this magnetic catalyst we are using, we thought we can reuse the catalyst for repeated runs. After each cycle, we recover the catalyst very easily using a simple magnet, and we go for the next cycle. So after 3 consecutive cycles, the yield remains almost same, and we are also recovering the catalyst in quantitative manner. Then we thought how the reaction proceeds, whether any least catalyst has any role for the transformations. So to know that one, we perform a hot filtration test. At the middle of the reactions, we remove all the catalyst. We are doing 2 sets of experiments. After 6 hours, as well as after 10 hours, we remove all the catalyst and perform the reactions, and the reaction did not proceed. That means the least catalyst has no role at all. So the catalyst is truly heterogeneous in nature. So the high reactivity in repeated cycles is due to the similar pattern of TM as well as PXRD or FTR that we observe. So we take the PXRD or FTR or TM before reactions as well as after 3rd catalytic cycles, and almost no change in the pattern we observe. So that's the reason we are observing the similar catalytic activity of the 3rd catalytic cycles. Then we thought, can we use this catalytic, can we use these pyrazines for some material applications? So to know that, to go to the literature, and we found the large conjugated aromatic compounds show fluorescence. Similarly, the large conjugated heteroaromatic compounds also show fluorescence. But these small pyrazine molecules cannot be developed as a fluorophore, that is not reported. And this idea we borrow from the nature. If you go to in dark night, you can definitely visualize a greenish color emitting from a fire effect, and that is nothing due to oxyluciferin. And if you closely observe the structure of oxyluciferin, so there is a carbonyl moiety and electron within groups as well as a phenoxide ion. In between this donation and withdrawing groups, there are a number of conjugated double bonds. So we thought our synthesis compounds having some electron donating groups with phenyl and on the other sides the pyrazine moiety may act as a fluorophore. So to know that one, we perform the fluorescence spectroscopy measurement, and interestingly, a number of compounds shows fluorescence. And this is the fluorescence emission spectra that we record. Then we thought, can we further apply these molecules?
So I will request you to please conclude as soon as possible.
Then further apply these molecules for sensing applications, and interestingly, in terms of iron 3 plus the fluorescence quenched, and if you increase the concentration of iron, you can see there is decrease in intensity of the fluorescence intensity. Similarly, we can go for ink applications. We dissolve the compounds in acetonitrile and visualize in daylight, so there is no mark observed. But if you visualize in UV light, some mark is observed. Also, we prepare pyrazines in a laboratory, a number of pyrazines. Similarly, we also prepare imidazopyridines. So apart from this, so recently also we prepare some carbon nanoparticles, and that can act as a probes for sensing of different ions like catagens, food additives, nitrophenols, or some anti-cancer drugs. So we are able to synthesize a number of pyrazines by reacting ketones, by reacting methyl aryl heteroaryl ketones with the diamines in terms of the nanocatalyst, and the catalyst also shows good reactivity of 3 consecutive cycles. We also develop the pyrazines as luminophores for sensing of irons. Similarly, we prepare pyrazoles as well as imidazopyridines by oxidative CC and CN formation pathway. So these are some publications. This is a publication of Analyst, which is a supplementary cover page. So thanks to the funding units like DST Fist, as well as BRNS, my present employer, and the Orissa Chemical Society, as well as the organic team of AMC 2024. And these are the people who really hard work to develop all these things. Thank you.
Okay, thank you, Dr. Jana and Repi. Any question is there? You may ask from audience. So Jana asking Jana. Okay, and teacher asking student. Very good.
Ashish, I have a suggestion on your mechanism. See, you said that imine is phosphor and then nitrogen binds to copper. So that is how you predict. My suggestion will be, can you not do it without using of a nanoparticle?
Yes, sir.
See, what I suggest is, you put a sulfonyl aryl group. Sulfonyl aryl group. So nitrogen is attached to electron withdrawing group. So obviously the attack will be at the beta carbon, and that is a very good living group. So I am not a nanochemist, but applying the knowledge of organic chemistry, you can do it. So try this.
How to optimize your reaction? Suppose you are using nanoparticles. What size of nanoparticles you are using as catalyst?
Around 15-25 nanoparticles.
That is optimization. Then you can get maximum yield of the product.
Now we could change the different like copper 1, copper 2, supported copper 2, like that. Copper iodine nanoparticles, copper oxide nanoparticles, Fe3O for copper oxide nanoparticles. So in copper 2 nanoparticles, that process where, and that may be a synergistic effect of both iron and copper.
If you are using the nanoparticles, suppose, so what you tell me, that way it should be good. But if you are using the nanoparticles, you can see a dispersing agent for the Fe3O4 and copper oxide. Then you can actually see the size, S size particles also you can do, depending on the dispersing agent for the nanoparticles.
We are externally measuring the site by TMs. Our target is to measure the size.
just a particle size, you can actually modulate using the dispersion, because you are telling 15 nanometer. If you are coming to 5 or 6 nanometer, the reaction product maybe the yield will be
by varying the size.
yes. That you can do by using the dispersing agent for the specific nanoparticles. You can find it out.
The XRD you saw is for what?
Copper oxide.
But
But there is no mark of copper.
I don't think it is 15 nanometer, it should be more. The XRD is very narrow. Anyway, you check it out later. The XRD is narrow means it's a bigger than 15 nanometer. XRD is broad means it's a small.
It's a spice is small.
Big intensity.
Sir, actually, I will bring the help of others.
But the XRD is very sharp. That is a ball. It should be 100 nanometer plus.
तब एक्साइटर को खराब है रहेगा.
Okay, thank you, Dr. Janand. That's part
Yeah, if any more question you can discuss. Doctor, now I request the chair to please felicitate Dr. Jena. He is the recipient of Dr. Ashik Tripathi category award, category 1. So he will be given a certificate and also a cash prize of ₹1,000. Dr. Jena told that the ₹1,000 cash prize that is given for us Tripathi Memorial Award Category 1, it will be donated to some needy people. Okay, we can see if any student. Hello. Next talkie is Professor Donald S. Matheson and Professor P.K. JST Award, Dr. Shravani Swatosini Misra. I will request Dr. Misra to give her talk. Neighboring case participation for assisted construction of self-assembled multi-cavity co-joint cages and augmented case binding.
So your timing also again the same 20 minutes, 15 minutes presentation and 5 minutes will be for questions. I request Professor Sarat Chandra Das to talk something about Professor P.K. JST.
Professor P.K. JST is no more with us, but his memory, his activities, his galaxies of work, particularly for Orissa Chemical Society, will be ever remembered. I find in the audience, his family members are present, his son has come. I welcome him because Professor P.K. JST was my teacher, was my principal, was my director, was my mentor also. Even if on the day of his last breath, he called me and couldn't able to speak any words. And I remember he is the person who has become instrumental for starting regional conference, starting chemistry Olympiad. We started it from Swami Vivekananda Memorial College, Jagatsinghpur, when he was the principal there, and I was interned there. And we salute the person. Particularly, he has given 2 awards. Here is one award. Another award he has given in regional conference, regional meetings, regarding giving the student who has secured highest mark in chemistry in the concerned conference site. So with this brief introduction, I conclude. Thank you.
So you are the winner. So congratulations.
Thank you. Good afternoon, everyone. My esteemed teachers, all the OCS members, participants, and others. I am very thankful for the opportunity that I am able to deliver a talk on the work I have done. So, the title of my work is Neighboring Cage Participation for Assisted Construction of Self-Assembled Multi-Cavity Conjoint Cages and Augmented Guest Binding. To simplify the topic, I have prepared some multi-cavity coordination cages where I have observed the neighboring cage participated for their construction and enhancement of their guest binding. So, first we'll discuss what do we mean by multi-cavity coordination cage. So, when a cavity contains a cage contains a single cavity, it is called a monocavity cage. And my discussion will be restricted to palladium 2 based cages since I have worked on palladium cages. So a simple example of a monocavity cage is PD2L4, which can be prepared using palladium. This pink color ball represents palladium and this sheaf-shaped cartoon represents a non-chelating bidentate ligand. So combination of palladium and bidentate ligand can result a PD2L4 type monocavity cage. So there is a one cavity which can encapsulate guest molecule or catalysis or various other applications can be done. So multi-cavity means more than one cavity. If a cage contains more than one cavity, it can be 2, 3 or more, that is called a multi-cavity system. So why we are calling it conjoint? Because if you see the PD3L4, this cartoon diagram, we can see that it looks like 2 PD2L4 cavity are conjoined, sharing a palladium center. That's why we are calling it a conjoint multi-cavity cage. So the first report of the multi-cavity palladium-based cage was reported by our group in 2014, where a tripyridine kind of ligand was prepared and reacted with palladium nitrate to give a PD3L4 type of double cavity cage. We have seen here that the 2 nitrate molecules are encapsulated inside the cavity. The nitrate is acting as a template. Also, this nitrate template can be replaced by halides such as fluoride, chloride and bromide. Iodide will be too big for the cavity. So this is the first example of a multi-cavity cage. And inspired by this design, a few more linearly conjoined cages have been reported. However, and still it is a decade, but very handful number of reports are there. As these complexes are very challenging to design and prepare. So this is another unique type of laterally conjoined multi-cavity cage, where we can see that this PD3L6 cage is combined with a smaller PD2L4 with 1, 2 and 3 units to give this multi-cavity cages. So it can have 4 different compartments for various applications. So why we are discussing about the multi-cavity cages? Why these are important? So we have seen that this is 2 examples of naturally occurring multi-compartment system. Everyone knows about the cell. So cell consists of many compartments like nucleus, ribosome, mitochondria to perform different physiological processes. So they act cooperatively to perform the physiological biochemical processes. So similarly, this is another example of a liposome which contains 3 compartments to perform 3 types of catalysis reaction. So when multi-compartment systems are there, we can see cooperative binding, allosteric regulation. So this type of property we see in biology. So supramolecular chemists, we are inspired by these designs. We are trying to mimic some systems which can replicate or which can mimic those biological systems. So multi-cavity system can bind multiple number of different guest molecules, or it can be act as drug, two different type of drug molecule can be bound. So that's why multi-cavity cages are important. So in this work, which we have done in our lab, we have used these three ligands L1, L2 and L3. We have designed and synthesized these ligands to prepare multi-cavity cages. So the ligand L1 is a pyridine-based ligand, which the three pyridyl systems are connected via amide functionality and metaphenyl space. The ligand L2, which is a tripyridyl system or a tris monodentate ligand, seems like combination of ligand L1 and ligand L4. Seems like both are conjoined to design this L2 cage. So we have covalently prepared this cage, and the ligand L3 seems like it is a disubstituted version of the ligand L1. So first, before knowing its complexation, we have to know the complexation of ligand L4. So L4 is already reported in literature, and the ligand L4 upon complexation with palladium nitrate, it has resulted a PD2L4 type of cage, where 2 palladium is connected with 4 ligands to give a PD2L4 type of cage. In this case also, template is needed in order to form this PD2L4 cage. Without the template, the cage will not form. So nitrate or halides, chloride, chloride, bromide, anions is needed in order to form this PD2L4 cage. The complexation of ligand L1 with palladium Y2, where Y can be different counter anions, we have performed the complexation and we have observed a dynamic equilibrium of PD2L4 and PD3L6 type of cage. We have seen that in presence of nitrate template, the cage, binuclear cage is the major one, 80%. However, by changing the counter anion, like bigger counter anions like BF4, perchlorate, the trinuclear cage predominates. So these cages were characterized by variable concentration and variable temperature proton mass spectroscopy. As we know from Lee-Chatter's principle that equilibrium depends on the concentration, temperature and pressure. We have studied here concentration and temperature to find out the equilibrium, and some other techniques like ESIMS, and crystal structure supports the PD2L4, and we have seen that 2 nitrate molecule and 2 water molecule are encapsulated inside the cavity in the solid phase. In the crystal structure we could see. However, we couldn't get any crystal structure of PD3L6 type of cage. Next, we move towards the complexation of ligand L2, which is a tripyridyl ligand, and complexation of ligand L2 with palladium nitrate interestingly resulted a double cavity cage, where we can see the 3 palladium is coordinated to 4 number of ligands, giving a PD3L4 type of cage. And these cages were characterized by proton NMR spectroscopy, ESIMS, and single crystal XRD. In the single crystal XRD, we could see that 2 different sizes of PD2L4 are conjoined. The upper cavity is small, and the bigger cavity is other cavity is bigger compared to the top cavity. And the smaller one encapsulates a nitrate molecule inside, and the bigger PD2L4 cage would encapsulate 1 nitrate and 1 DMSO molecule inside the cavity. So why I say that interestingly it gave this PD3L4? Because we have seen that this bigger bidentate part gives a mixture of product, PD2L4 and PD3L4. And this, however, we didn't see any other product forming. Exclusively it formed a PD3L4. So we are assuming that the smaller PD2L4 is helping for the formation of the PD2L4 exclusively. There is no PD3L6 formed along with it. We have also changed the counter anion from nitrate to perchlorate. And we have also seen in that case that exclusively a PD3L4 cage is formed, while the upper cavity is empty, because the smaller cavity can
cannot encapsulate any perchlorate because its perchlorate is too used for the smaller cavity. And the bigger cavity may encapsulate few perchlorate molecules. Similarly, the tetradentate ligand, which is a tetrapyridyl system L3, upon completion with palladium nitrate has resulted a triple cavity system where the peripheral cavity is smaller and the central cavity is bigger. This is also characterized by NMR and DSIMS, however, we couldn't get any crystal, and this is the DH structure. So what caught our interest is the ligand L1 in presence of perchlorate counteranion gives major of PD3L6, and the L4 in perchlorate doesn't give any discrete product, it gives a mixture of product. However, when these two ligands L1 and L4 are combined, which is L2, it resulted a discrete cage. So we are proposing that maybe both the cages, that the smaller PD2L4 and bigger PD2L4 cages are symbiotically helping each other to form this double cavity cage. And the same as the case of the triple cavity cage. So after successfully synthesizing all these cages, we moved towards the gas encapsulation study. We could find out the palladium distance is around 11.3 angstrom. So we searched for some suitable gas which can be encapsulated inside the cavity. So we selected 1,4-benzoquinone and pyrazine NN dioxide. From DFT study we got to know that size-wise it can fit. However, size cannot be the only factor for host-test interaction. There should be various interactions, electronic effect, steric effect. So we have studied other things. So if we compare the benzoquinone and pyrazine dioxide, we can see that NO bond is more polar than the carbonyl because of the charge polarization. And also that CH bond in pyrazine dioxide is more electron deficient since it is near to the N+. From the electrostatic potential map also we could see this red color is more here, which supports the negative potential in case of pyrazine dioxide, and this blue color gives the positive potential of the CH bond. And this pyrazine N oxides are important because it is a redox active moiety for many heterocyclic N oxides which have anti-tumoral, antibacterial, antimicrobial, anti-inflammatory properties. Thus we chose pyrazine N dioxide. We have observed that when we added excess amount and 7 equivalent to be exact of pyrazine dioxide to this equilibrium mixture, it resulted in the equilibrium shifted towards the binuclear product. So it is a gas mediated that equilibrium shifted towards the binuclear product forming a post-stage complex. However, when we added excess amount of benzoquinone, there is absolutely no change observed. So it is not able to encapsulate inside the cavity. So by comparison, we could say that this is the electronic, other than size, electronic compatibility matters for the host-test interaction. And since it is more polar, the pyrazine dioxide, it can replace the nitrate or DMSO molecule already present inside the cage. However, the benzoquinone is not polar enough to replace counteranion or DMSO molecule. So this is the crystal structure, and we could see various type of supramolecular interaction between host and guest. Three type I have shown in 3 different colors. The black line between the oxygen and palladium shows electrostatic interaction, and there is hydrogen bonding between the pyridyl CH hydrogen and oxygen of pyrazine dioxide, and also carbonyl, the ligand moiety, the carbonyl also interacted in the supramolecular interaction with the guest molecule. So all these combined help to stabilize the host-case chemistry. We have also studied the steric compatibility, and we have seen that by increasing the number of CH3 groups or the phenyl groups near the pyrazine dioxide reduces the binding ability. So this is due to steric compatibility. Also due to the lower number of non-covalent interactions. Since supramolecular interactions are additive, by lowering the number of interactions, the host-case binding affected. So this is the steric compatibility and electron compatibility. Further, we have studied the selective guest binding in double cavity cages and triple cavity cages. We could see that the smaller cavity can encapsulate halides, that fluoride, chloride and bromide, and the bigger cavity could encapsulate one molecule of pyrazine dioxide. Similarly, the triple cavity, both the peripheral cavity could encapsulate 2 molecules of halides and the central cavity would encapsulate one molecule of pyrazine dioxide. So after studying this guest binding, what we noticed that for this host cage formation of the single cavity cage, we need 7 equivalent, and for the double cavity cage, we need 2.5 equivalent of guest. However, for the triple cavity cage, we exactly need 1 equivalent of guest. And in all these cases, 1:1 host cage complex is common. So 1 equivalent should be needed. However, in these cases, more amount of guest is needed. Probably it can be attributed to the weaker binding in the single and double cavity case. So that tempted us to find out the binding affinity of BJDO in all these cases. So there are various methods of finding binding affinity of guest inside a cage, like proton NMR spectroscopy, UV visible spectroscopy, IPC method. We have chosen NMR spectroscopy method, and we could find out that for the double cavity cage, PJTO binding affinity is 10 to the power 3 molar inverse, and for the triple cavity cage, it is more than 10 to the power 5 molar inverse. So, however, we couldn't find for single cavity cage as there is equilibrium. Finding out the concentration is difficult. So we have used a simple formula where binding affinity constant is equal to host cage concentration divided by host concentration into cage concentration. We could find out from the NMR study and put those values in the equation, and we could find out the binding affinity of this all three type of cages. So we can conclude that the triple cavity cage binds better than the double cavity cage, which in turn binds better than the single cavity cage. So also we have performed some qualitative competitive binding study that to this double cavity cage we added exactly 1 equivalent, which formed host cage complex. Some amount of host is there and some amount of free guest is there. As it needed 2.5 equivalent of guest. 1 equivalent adding, it gives a mixture product. To that we added the triple cavity cage, thinking that if triple cavity cage is stronger, it could encapsulate or it can capture the guest from the double cavity cage if it is strong enough. So we also to our support, we observed that this triple cavity cage could encapsulate or could capture the cage already present inside the binuclear cage. So this shows that the triple cavity cage is stronger or strongly bind the PJDO rather than the binuclear cage. So similarly, we have also competitive study we have done between the single and triple cavity cage as well as the single and double cavity case. In all those cases, we could find so we could find out that triple cavity cage binds better than the double cavity, which in turn binds better than the single cavity cage. So what could be the reason? We are proposing that probably the single cavity cage there is no such locking. It can twist, open, close, and change conformation in various possible ways. However, in double cavity cage there is one PD12 cage on the top of the palladium, so it is kind of locking from one side. So it is restricting from one side. So binding is little bit better. While in the triple cavity case, there are two locking from both the palladium sides. Two PD12 are present peripherally on the PD12 case. So locking is more. So that's why the guest binding is better in the triple cavity cage. So this we are proposing the neighboring cage participation. That the neighboring cages help augmented guest binding or enhanced guest binding. So as we couldn't observe any cooperative binding, but a new kind of phenomena that the neighboring cage participated for guest binding we observed in this multi-cavity cages. So to summarize, we have prepared some double and triple cavity cages of PD3L4 and PD4L4 type. And the smaller PD2L4 cages, it has this double and triple cavity cage has two type of PD2L4 cage of different cavity size. The smaller PD2L4 can selectively encapsulate nitrate and halides, while the bigger PD2L4 can encapsulate 1 unit of pyrazine dioxide. It is also demonstrated that during the preparation of these cages, the neighboring cages symbiotically participated in the formation of each other, and the guest binding behavior of these multi-cavity cages are also intriguing, as the presence of the conjoined cages enhance or augments the guest binding behavior of the bigger cavity, and further augments when two neighboring cages are there in the triple cavity cage. So this is the diagram showing the binding affinity is enhancing.
Okay, thank you.
So thank you all. I'd like to thank my guide who supported me. And Thank you all for that.
See, competitive binding of PZDO, pyrazine, and dioxide. Okay. You see, these are all analogues of dicarbonyl. Say carbonyl is polar. You have made it still more polar. But did you compare all? I mean, S double bond O, P double bond O, and things are there. So that is one thing. Which is more polar? If you can predict from theoretical calculation, so that will predict your result. That is one. Second thing, the counter ion. Counter ion you have selected only a few, but there are many counter ions. Say triflate, good living groups like triflate, tosylate, mesylate, mesylate, brosylate, like that. Say I more larger size and good living. So all these factors can be. You have used. Okay. So it depends on many factors. You have only calculated only binding influence of PZDO.
Yes, sir. There are many other factors which can be considered, and we can explore.
The size, the host guest complexes. This is host guest complexes in chemistry.
Yes.
Right. So there are many factors of binding.
Yes.
You have to take all parameters. Okay. That is my complete.
Okay. Any other question? No. Okay. Let's give a big hand in for Kunsu. And I suppose PK Justin who asked something is present. Please come here. PK Justin, Professor Jana, you must be remembering that he said we will conduct Olympiad, we will take the charge. मते पचारले जे तमे चार्ज नब की ओलंपियाड के करिया पैक न सके केते वर्ष न मैं आपण कोन चाहते 5 वर्ष में 10 वर्ष में करी तापर ओलंपियाड आरंभ आई विल अप्लाई टू प्रोफेसर पीके जस्ट हां हां असो तुम्हें असिस्टेंट
प्रिंसिपल थे से
असो तो असो
President समझा गैस प्राइस
That the gas price to be declared by Professor Acharya.
Professor Donald Matheson and Professor B.K. Jesti Award. It is given to Dr. Shravani Srutaswini Mishra and with the cash prize award of 1,000 rupees. Sir, take here. Thank you, sir, for chairing the session. So now we are half an hour late. So tea break, tea has been sought. Tea is also outside. If anybody wants, you can go and take the tea. Next session is will be chaired by Professor Sarat Kumar Swain. Professor Sarath Kumar Swami is currently professor in chemistry at BSSUT Burla. He completed MSc, MPhil, PhD from Utkal University. He was a postdoctoral fellow in USA. Before joining BSSUT Burla, he was a reader in chemistry in North Odisha University and also rendered the service as lecturer, assistant professor and associate professor in KIT University and ICFI University of Orissa. He has published more than 200 research papers, book chapters and reviews in different national and international journals. He has 2 patents in his name. He has guided 18 PhD and 3 postdoc candidates. I now request Professor Swami, please chair the session. And in this session, we have 2 talks. That is Professor Surendra Kumar Martha, Professor, Department of Chemistry, IIT Hyderabad. Then another is Professor Asif Ali Memorial Award, Category 2. It will be delivered by Dr. Santosh Kumar Behra. Since we are late, I request the chair to please stick to the time.
Hello. Thank you, Professor Acharya, for a nice introduction. Now I will go to the session. And I think battery is gone. Without delay, we will start the session. First speaker, Professor Surendra Kumar Martha. Professor Martha now is professor and head of Department of Chemistry at IIT Hyderabad. He received his PhD during the year 2006 from the Solid State Structural Chemistry Unit, IISc Bangalore. And he joined, started his career as assistant professor in 2013 and promoted to associate professor in 2018 at IIT Hyderabad. His recent research interests are the material electrochemistry with particular emphasis on the advanced metal ion, dual carbon, lead acid batteries. He has published around 140 publications in peer-reviewed journals related to material science and electrochemistry journals. He has 18 patents, 10 book chapters, and contributed over 90 academic conferences. He delivered the lecture. He received the Best Teacher, Best Researcher Award from IIT Hyderabad 2022-23 also. He was a recipient of CSI Amar Rajya National Award during 2024 this year. On this introduction, I request Professor Martha to start his lecture. Yes, I request you to finish it by 25 minutes.
Thank you, sir. Thank you, the organizers of MC 2024 and for inviting me and giving me a great hospitality. And they say in a month, in 2 months I have come 3 times. In a month I have come 2 times. It's homecoming for me. Yesterday I was talking to our Jana sir that anytime you organize a conference or we'll be happy to come over here. It's not only homecoming, we want to contribute. So as usual, so this year I have come 2 times for a meeting, actually especially for the meeting. So we'll try to contribute as much as possible. So last month, when we met, I gave a lecture on dual carbon batteries where no metal ions are used. Today I'll talk about, that was also a lithium based battery. Today I'll talk about the low cobalt to no cobalt based cathodes for the lithium based rechargeable batteries. Before I go to the next presentation, the real thing, I want to just say a few words about the research. Basically, I am a material electrochemist. We work in the interfaces of new materials, you see, and electrochemists become material scientists, and this is our strong backbone of electrochemistry. We work mostly on the latest batteries. I think I am maybe the one still continue to work on latest batteries and carbon capacitors. Our major backbone is metal ion batteries. So then we work also develop a concept. I told you the dual current batteries. Also we work on the next generation batteries like lithium sulfur batteries. Also we do we develop a lot of metal ion batteries. We work also metal ion capacitors and then recycling lithium ion batteries. So today's talk will be mostly on only one aspect. So this is actually, these are like 5 different topics. So in the electrochemistry conference, I talk only one material. So today I will talk about 4 different materials which are the next generation cathode materials for research for lithium ion batteries. So I am giving a brief overview. So you should know what is lithium ion batteries, the development today, and what are the future. As I am going to talk in next 25 minutes. So let's understand a little bit about batteries. So you know that the past the electrochemical cell, Volta pipe, correct? Volta use copper zinc plates stacked alternatively to get electricity. And today we use the same concept of making batteries, correct? What has changed? Only battery chemistry has changed, correct? So he uses a brine cloth solution, that is the separator, the brine is the electrolyte, and we use aqueous and non-aqueous solvents. And this is the battery stack. You see the Volta to semi-volt, which is general motor battery stack used in plug-in hybrid vehicles or electric vehicles. And you see, it's a battery pack of 430 kilogram, or Tesla, if you see, it's a 400 kilogram with a 60 kilowatt. This is a 60 kilowatt battery pack, and the weight is close to 1/3 of the battery vehicle weight, which is around 400 kilograms. And it consists of, you see there at the bottom, lithium, nickel, manganese, cobalt oxide. This has come from the parent compound lithium cobalt oxide. So that's what I'm going to talk today. Because of this, lithium, right? So because of lithium, the energy density has increased. Now this is because of this materials, the energy density has increased today to 50 watt-hour per kilogram. You are using latest battery, correct? The energy density is just 30 watt-hour per kilogram because it's very heavy, correct? So if you look at lithium, so lithium is the lightest metal. If you calculate the capacity, you can get 3,860 milliampere per gram. 1 gram of material will give you 3,860. You calculate from the Faraday's second one. Okay, so 1 gram equivalent of material will give 26.88. You can calculate any element from the periodic table. You can calculate the capacity, and it has a lighter. It has more cell discharge, and because of this, the energy density has increased to 250 watt-hour per kilogram. That's why it has been used in your cell phone, laptop, camcorders, and today EVs we are talking about. We talk about the renewable energy and wind. And even Indian Ministry has declared 30% EVs on the road by 2030, right? And 600 gigawatt of renewables by 2030. Okay, so that is we are going to achieve. You see here, we have already Nexal so Tata is one of the leaders in India for electric vehicles. And you will see when every company, even Hyundai, BMW, or any company you just see today, they are now focused on EVs. And two-wheeler companies are like merging, like Ola, OUTR. You see, we have a startup from Hyderabad, Fruto. Is a third in India, and they are selling in the name of Pluto. It's a pure EV from Hyderabad. And you see, the electric buses already running, everywhere in India. Okay, I had a small EV program at Hyderabad. We started in 2019 because of COVID. It was a bit halted. So then last year I approached JICA and they gave me a small fund, and the goal is to develop. See, everybody uses a lithium-ion battery in their cell phone. Do you think that the lithium-ion batteries are manufactured in India? Not a single battery company. They get the batteries from elsewhere, and they make the battery modules and packs and put into the field. Okay, so that's the real scenario. So that's So we are trying, it's a small market, which is some Japanese collaboration, we make a 10 ampere or 30 ampere of cells. So I hope the dream will come true in 6 months to 1 year time. So anyway, not to worry about, let's focus on today's concept of lithium-ion battery, So in lithium-ion batteries, you see, these are, I'll show you the real electrodes of lithium-ion battery. These are the, you see here, this is the real electrode of lithium-ion battery. This is the cathode, this is the anode. You see, one side is a aluminium, is the current collector, this is a copper, correct? This is, you see, on the, this is the, what is the black mass? That stores energy, not this current collector. The black mass stores energy. Even in the black mass, you have some binder, you have conducting diode, they don't also contribute to energy. Only the active material which contributes to stores the energy. Correct? So if you look at, so we have the first lithium and metal oxides. They are the first, followed by now lithium iron phosphate. Now people are talking about lithium manganese iron phosphate that goes into future cathode. We talk about the spiral cathodes. Okay, so mostly if you see, I come in the next slide, mostly we see the lithium and metal oxide are the leaders today in the lithium-ion battery along with lithium iron phosphate. And if you see another side, we have a graphite. Graphite is the best, lithium and graphite is the best anode still today for lithium-ion batteries. Tesla uses 10 to 20% of silicon because silicon has high capacity, but it has a lot of issues. Okay, so along with that, we have a lithium titanate. There is another anode for lithium-ion batteries. You see, if you open today in materials science journals, you get thousands of papers on materials. But only few, you see, I'm talking about only tens of materials are used today in the lithium-based batteries. And so we don't use pure lithium battery. I told you, 1 gram of lithium will give you close to 4 ampere hour, but your cell phone is not 4 ampere hour. Like 1 gram of your cell phone battery, which is 4 ampere hour, is not 1 gram, right? So that means pure lithium is not used. You just you see here, they are using this kind of materials. And so this is a lithium material. So because of safety issue, lithium forms dendrite during charge discharge. You see again, now people are trying, can you use lithium in lithium batteries? Because 1 gram of lithium will give you 3860 milliampere hour. Right? That is the good today. That is the future in the solid state batteries and other batteries. So you see here, during charge, the lithium intercalates in the graphene sheets of carbon. Okay, this is graphite. The layers, the graphite is a layer structure of this is a layer structure, and lithium can go and intercalate, and during discharge it can come back. And if we use a electrolyte called alkyl carbonate in a like this, it's the organic electrolyte. Okay? So the voltage you can get, it is LFP. This is LFP. This is called LCO or NMC, and this is called LNMO. Okay, so this is a short pump, and you can get 3.74 in this kind of system. You can get 3.3 volt in this system. You want to increase the voltage? Simply iron can be replaced with manganese, nickel, cobalt. So you can get, if you replace manganese, you can get 4 volt. You can replace with cobalt, you can get 4.8 volt. You can get, if you replace with nickel, you can get 5.1 volt. You can ask me, why did you replace that? The main thing is the electrolyte. We don't have good electrolyte operating above 4.4 volt today. So that's why your cell phones are operated at 4.3 volt and below. So as long as you can, the structures are stable during the charge or discharge, you can charge discharge your cell phones or laptops. They should be structurally stable. That's why, so lithium ion hops between cathode to anode. That's why you tell a rocking chair battery. Okay, that's why people tell lithium-ion battery as rocking chair battery. So let's talk a little bit about what is the current status today in these materials. So if you look, so lithium-ion, because these three gentlemen, Professor Budena, Professor Whittingham, Professor all the three got Nobel Prize in 2019 because of their discovery. So I'm not going to details of this. So just want to tell you. So Budena, who is no more, he died this year at the age 100 from University of Texas or Austin. So he is the pioneer. He is my professor always tells he's more than good enough. The lithium cobalt oxide you are using today is his contribution. Okay? The lithium nickel manganese cobalt oxide you are using today, that is his contribution. The LFP you are using today is his contribution. You know, I don't think many of you know, there are two Indian scientists, along with one Orissa scientist, you know, Dr. A.K. Pai, who developed lithium iron phosphate, which you are using a cathode material for lithium ion battery in the 1990s. And the graphite anode, I told you, the graphite anode, the first intercalation of lithium into graphite anode was done by Professor Samarwas, which is often forgotten actually. This guy is often forgotten in the history of batteries. I really don't know actually. He was felicitated, I got the YouTube video and from there I copied. And in Wikipedia, any time people write his name and many times people remove his name. I'm really surprised why they do that. Anyway, so he is one of the pioneers who showed lithium intercalation into graphite. These are the three Indian scientists, along with A.K. Pali and Nanjana Swami from IS Bangalore. When they were working with good enough, they developed lithium iron phosphate. And today, still we are using. Okay, and this is the status today. So we are using lithium, cobalt, substitute lithium cobalt oxide because cobalt is expensive and biohazardous, thermally not stable. And I'll come again in the details of cobalt. So mostly this is the start of silicon. I told you a little bit of silicon is used today. The current goal, you know, we have organic chemistry and also here. So if you can develop a 5 volt electrolyte, we can have plenty of materials. The problem bottleneck is LiPF6. Alkyl carbonates are very stable till 5.3 volt. The LiPF6 is not stable near 4.4 or 4.5. Anyway, the future is lithium sulfur, lithium ion batteries with solid state and sodium ion batteries. We also work on sodium ion batteries. There is a dual carbon batteries, completely carbon, and there is no metal ions required. The electrolyte is the source of lithium. And then non-cobalt, as I'm going to talk today in my talk. Briefly, I'll talk in today's talk. So just want to tell you how we develop. You all talked about nano. Nano, see, if I make a nanomaterial, see, today people talk in one centimeter square, we have loading of 50 milligram in 1 centimeter square. If I make nano of lithium iron phosphate of 100 nanometer, I can load only 5 milligram. The energy density will be very low. Okay, that's why lithium iron phosphate energy density is very low compared to NMC. Okay, so what people generally do, people make the primary particles are nano, the secondary particles. We make a secondary particle like this, which is micro, and the primary particles are the nano. Nano will have fast diffusion of lithium ions, and then the second particle will increase the gap density. You can have good loading on the particles, on the particle. And often we do, these materials are non-conductor, not good conductors. We add electric conducting layer on surface. When we want to go high voltage, we do a lithium conducting layer on surface. And as usual, we do also doping to stabilize the structure. These are the 4 ways we do we synthesize the material and to increase the capacity. So the goal is to increase the capacity so that you can get energy, which is the charge. Charge is nothing but the capacity, which is ampere hour into voltage. You get this is called watt hour. Right? Voltage into current is watt into time is H. So it is watt hour, and with respect to when you tell energy density, watt hour per kilogram. Okay? So this is the way. So you have to increase the charge or you have to increase the voltage. You can get the energy. This is a simple concept. Another way, I told you they are copper and aluminum. So we use a 3D carbon fiber based electrode architecture where you have a very good contact of mass. So there you don't have to use the binder like PVDF or polyvinyl alcohol or SCMC what is used. Here you use a carbon binder which will be directly embedded into the 3D electrode architecture, and that will have faster diffusion of lithium ions. The goal is that when we talk about faster diffusion of lithium ions, we talk about the C rate charging. You are able to charge your cell phone at 1 C rate. But 1 C refers to the capacity in 1 hour. That means if a 5 ampere hour cell phone, you are charging at 5 amp current. That's why you give it 1. This will give you 5 ampere hour. So that's called 1 C rate charging. 1 C rate charging is not enough for electric vehicles. You may need 20 C. What is 20 C again? 20 C refers to like it is 3-minute charges. we talk about 3 minute, 5 minute charge discharge. This is based on again not the this cannot depends on the material also. If material, the dynamics, yesterday Professor Bhavani was talking, dynamics plays important role for the performance of this metal ion batteries. So today I will be mostly talking about what we do in our lab. So today's presentation is mostly covered in the contact cells. First we make a contact cell. Our materials we study the contact cells. Then we go to a single electron contact cell. When particle agency doesn't like that, we have to go to like a multi-electron contact cell. And then finally, we don't have the support to get 10 ampere cell. That's why I'm trying to collaborate with this Japanese companies so that we can make this. Anyway, so mostly the data what I'm going to present room temperature data. It is not 50 degrees centigrade or 0 degrees centigrade. It is at 45 degrees centigrade. So these are the materials I'm going to talk. So I told you in electric chemistry conference I will be speaking only one material. I will to talk about the 5 different work, what 5 different materials which are the future for the lithium batteries. So why cobalt? Why we want to reduce cobalt? Cobalt is required to improve the structural stability. I don't want to go again details of the chemistry aspects. It's crystal stabilization energy is very high, so it improves the performance. And nickel is also important. It improves the stability and gives the capacity. So you can go. When you go to nickel, very high content of and cobalt. See, if lithium and batteries continue to grow, you can invest cobalt instead of your gold. Because it's available only in Congo. And Congo, you have child labor and other things. So that's why the focus is towards non-cobalt based electrical materials. When you go to non-cobalt based and nickel rich, you have lot of issues happens. When you go to like the nickel rich, there's the materials like this, the bottom one. So first I want to talk about in a lithium rich, so which I started in the postdoc and I graduated the student. And this is the only material which can give the double the capacity of the currently available lithium ion batteries. So you see here, it can give you the theoretical capacity of lithium cobalt oxide is 274, but it gives only half, that is 140 milliampere per gram. Here if you see, now we can get full capacity. So again, what we have to do, we have to charge beyond 4.4 volt because this material is an integration of 2 different materials of Li2O and NMC. And the Li2 MLO3 component will be activated when you go beyond 4.5 volt. So that's the critical part of this. I mean, when you go beyond 4.5 volt, electrolyte instability is another important factor. So we try to add some additives and do the cycle, but that's not the ultimate goal for the commercial scale application. So we developed this material by co-precipitation method, and you can see here the primary particles are nano, and the secondary particle is a micron. And you see the peak cross-section, the engineer such that you have hollow core, so that electrolyte can be absorbed, and all the materials can be utilized for electrochemical reaction. So that's the goal. So you can see the highly faceted morphology. You have lithium ordering the crystal lattice, and most importantly, you can see manganese in the surface as it is a 0.53. Okay, so let's see the electrochemistry. So if you see electrochemistry, so only a Li2O3 component is activated, you see, when you go beyond 4.5 volt. And also at 4.5 volt, you get less capacity. This called, I told you, so what is cycle number? One charge or one discharge is one cycle number. So that means it is 80 cycles, means it is 80 times charge and 80 times discharge. So you see, when you operate 4.5 volt, you get 220. When you go to 4.9, you can directly get 280. And 5 volt, the electrolyte decomposes, you don't get stability. So another important thing you see here, after 150 cycles, capacity drops. This is the problem of material. And again, the 3.7 volt profile becomes down. When voltage becomes suppressed, then energy also lost. And then impedance, if you see, it becomes completely resistive. That means no electron flows, no ion flows after a few hundred cycles. That's why the capacity falls. So the goal was how to address this issue. So simply, we have done, as I told you, we take two strategies. One is to improve the conductivity of the the layer, the material by carbon. So here we have the carbon nanofiber additives which are produced at 3000 degrees centigrade by chemical decomposition and is added to soil. You see, they make an electrical connection between the particles actually. And very few results. This is, we have 2 papers on this. I am showing in 3 plots. So you can see here, so it improves. So it was in the conventional, capacity loss was there complete. Now it is stable. And it also improve the C rate. That means if 1 C refers to capacity in 1 hour. C by 10 means 10 hour charge discharge. So it improves the rate also. But, so also we try to do lithium ion conducting layer on the surface. It improves the performance. But our energy loss is one of the factors. So it was giving 3.7 or 4 volt plateau, and now it has become reduced. The capacity is almost similar. So half cycle energy is 1000 watt per kilogram. If you calculate the area under peak, which is capacity, and the voltage, which is energy, so which is 1000 watt per kilogram, but now 700. If I ask Bola, can you take this material and do it? They will tell no, because it's after 300, after few hundred cycles, you have the voltage separation. What electronics will help me to, to balance the cells? Very difficult. So this was even this material was studied by a lot of people actually. People thought this is the next generation cathode material. But it didn't happen. So you have to, because you have a significant voltage drop. This is because manganese. Manganese, so you have a general distortion and it goes to a spinel phase from that structure, and mostly it happens because I come in the next slide. So you see now earlier manganese was on the surface, now nickel is on the surface, and you can see external studies which was done in collaboration. So we show that like you have spinel expansions, and even this STM ideal image, so you can do FFT and you can see the spinel phase transfer. So that means when you go to the spinel phase, the voltage will reduce. We know that manganese 2 plus. So every oxide is 2 plus to 3 plus, 3 plus to 4 plus have different voltage profile. So after seeing our data, some people predicting. So what happens actually? Nickel goes from the lattice to the surface of lithium for the theta of bond. That's why the structure Tyson occurs. So what we tried to think, we thought, can you dope something and so that this Tyson can reduce? Plus, can you suppress the voltage profile so that we can improve the capacity and capacity tensor? So what we try to do, we do a chlorine doping. Anion doping plus cation doping. The anion doping will help. So when you do a anion doping, so what will happen? The sum of oxygen will be replaced with chlorine. It stabilizes the MF bond is stronger than the MO bond, and it will improve the structure and improve the tap density. We have seen all the things, and then most importantly, you can see here. So it was initially you get capacity above. So most of the capacity above 4.5 volt. Now it is decreased. So that's because of chlorine doping. And also what we noticed, the voltage profile, energy loss was reduced, and finally we make the full cells with the power type commercial type cells, and this was also patented. And we tried to sell this technology, but many were not very keen and so on, because it was I approached many companies actually. So unfortunately, India still doesn't have a company who makes their own cathode anode materials. Amaraja is coming up with the Gosam technology. That's I'm going to tell in briefly in a slide. So neither surface coating nor electric conductivity improves the surface stability. Maybe doping to some extent improves the stability. So I just we do also lithium rich NMC cathodes, NMC 81 cathodes, where you can see here, when you go to NMC 81 of nickel high content, they are not stable in the air. You have to keep in dry room so that the stability will be increased. Otherwise, it will be very difficult. And this kind of material will form in the metabolization, and you have link cation ordering can happen, oxygen evolution can happen, and you can have also a lot of structural tension can happen if you hit the material. So we have attempted few things I won't tell in details. So one approach we did coating of LIGO, the organic electrolyte, because and LiPF6 to improve the stability. So it forms
LiF and Li3PO4 on the surface, which improves the stability, and the performance can be drastically improved. This is the chart discharge claim. Another way, so LiGO and LiPF6, they are not air, you cannot do air, so you have to do it in glow box. So we thought, can you attempt with the ML3PO4? This was one attempt we did, another attempt we did recently with this one. This is one of the best, and we are going to commercialize with this, and this works very well for lithium-rich NMC. So this pristine NMC cracks happens during cycling. Now our coated material doesn't have any cracks. So we also work on LNM cathodes. I'm not going to talk about that. That is another feature cathode like lithium, nickel, manganese oxide. The feature structures are very good for this kind of application. What we try to do, people do tens of synthesis, like a lengthy process, a weak approach to synthesize this material. We have done it in a day, no, in 24 hours, 24 hours to synthesize material, and we have also some good results. I'm not going to show about that. The last one, I just wanted to show this one. This is one of the important material that is going to replace your lithium iron phosphate, but K. Padi, Nanjuna Swami, and Professor Gurena made it in 1997. This, I started this work, you see here, I published in 2009, and today, I don't know what happened during the 15 years, nobody was interested in the lithium manganese iron phosphate, and today they talked about the future cathode material for lithium ion batteries. And that's what I wanted to show. Second, the same structure, same problems of lithium iron phosphate, the problem can be mitigated in a similar way. Only manganese is one of the issues that need to be addressed. And the advantage is that you have high energy, high voltage, that means high energy. So lithium manganese iron phosphate is a good material for lithium, next generation lithium batteries. And we have done, you see 2009 versus 2024, almost similar performance but high C rates. You can discharge in 10 minutes, 15 minutes. We improvise the process. The same approach, we improvise the process, and we are working in this area as well. This is the last slide. So this is also another new area coming up. So what I presented, you have one aluminium, copper, you have metal ions. Now we we did a work, both sides carbon. You take a graphitic carbon on both sides. Okay. Now I'm talking about, you have only lithium ion is intercalating. Now I'm talking about, now my electrolyte, LiPF6 at a certain voltage can intercalate, PF6 can intercalate to the graphite of the cathode, and Li plus can intercalate to the anode. Now I'm talking about dual ion batteries. So this we made in a all carbon graphite battery, and this was published just after COVID, and it's a 4.6 volt system. Again, electrolyte is one of the issues here. Electrolyte is the only player here. There is no lithium in the cathode side or anode side. Electrolyte, the LiPF6, is the major player here for operation of this kind of system. And a lot of issues in this system, this I presented in the last month meeting at Oak University. And so what is the difference between them? What we told is a rocking chair mechanism. Here both the ions are intercalating. There is a scissor cutting mechanism. So the advantage that they have half of the energy, but 100% recycling. You put carbon into the smelter. So that's what I want to tell. And with this, I just wanted to summarize again. I talk LMR-NMC is one of the leader of cathode, which can give you 280 milliampere per gram, double the energy of the currently available cathodes. NMC 81, where you increase the nickel-rich material, go to nickel-rich material, phase stability is one of the important factors that need to be addressed. Lithium manganese, when we talk about LNMO, is also another good material. Again, electrolyte is also an important factor. In the dual carbon, also electrolyte is also another important factor. So that means you can go away from the conventional organic electrolyte to solid elements, and that could be the solution. With this, I thank my funding agency and my students for their hard work. So this, what I presented, 5 students, this is one of them have graduated and 4 of them are Thank you.
Thank you, Professor. Now we can take one question. because we are in shortage of time. Any question? Okay, then we can discuss more in the during lunch.
Sure.
Let us thanks to speaker in the big hand. Thank you, man. I think this is the second time that I am chairing and you are the speaker.
In a month.
It may be a coincidence.
In
Yes,
a month.
In a month.
You will not invite everyone to your guest house?
I request Professor Swami to please felicitate Professor Martha.
Second one is the award lecture, and again it is a Professor Ashit Tripathi Memorial Award, and in category 2, I think no need to introduce Professor Ashit Tripathi, already it is introduced by Professor Acharya. Then without delay, I request to deliver the award lecture Dr. Santosh Kumar Behera. His affiliation is Model Degree College, Niagara. Dr. Santosh. And
So good afternoon to all of you. So I will take this opportunity to thank OCS and our management committee for giving me this nice opportunity to talk about my research work. So today here I will be talking about photophysics of the donor acceptor system on by optical spectroscopy and TFT. So before going to talk about my work, I will quickly acknowledge I would like to thank all the people to whom I am work with and all the funding agencies. So today here I will briefly talk about three of my interesting work. So those are having different photophysical properties such as the excited state intramolecular phototransfer and very nice based on the room temperature phosphorescence and thermally activated period process. So since we are talking about photophysics, so I think it is very important to know about the photophysical process, that is the fate of the photophysical process by the very commonly Perrin-Jablonski diagram and its recent advancement. So as we all know, the population of the molecule is more at the ground state. So absorption of the photon, what will happen? So with the absorption of the photon, the molecule come to the excited state depending upon the energy of the absorbed photon. So if you can take up any of the excited state, that depends on how much amount of energy the photon is absorbing. So once upon the molecule in the excited state, what will happen? The molecule will be energetically frustrated. So it will always come back, try to come back towards the ground state, different pathways. So very immediate process is the internal conversion. So we know already. And you can see here the energy gap between S0 to S1 and will keep on increasing, the energy gap will decreasing. So once it will non-reactively come to the S1 state, it will have a larger time. It will spend a lot of time there. So that here once the molecule is in the S1 state, what will happen? The molecule have the different opportunity. And one of the very immediate opportunities is that it will give the fluorescence. So not only the fluorescence, once the molecule in the excited state, what will happen? It will have the different criteria. So it may undergo charge transport, it may undergo proton transport, it may form excipients or exciters. So a lot of things it will do at the S1 state. So what the other things it can also do? So what will happen? The next thing is the ISC, what we call it intersystem crossing. So it is a spin forbidding process. So by the method of which I will tell what favors the ISC, but even if it will come to the T1 state, it relatively also will get the phosphorescence. So I will know that how the ISC favors. So we should have a heavy metals. So recently what will also, if there is, we will not use also heavy metals, so what will happen? We will have the carbonyl. So it will follow the L-side rule and it will also give the phosphorescence. And very recently what will happen? The pure organic systems having multiple donor acceptor system, that will also favors ISC. So in this way, what we will get a phosphorescence. So what is the more? So here the interesting thing is that in the last couple of years, what is the research is going on, if you can tune the energy gap between S1 and T1 state, what will happen? We will have also reverse intersystem crossing. So we can reversely populate the molecule from the T1 to S1 state. So in this way, we will get another process, what we call formally activated delayed fluorescence. So in this way, in this my talk, I will briefly explain the different examples, what are the fluorescence and what are the characteristics, again phosphorescence, and also in the last, I will conclude with my few examples which will show formally activated delayed fluorescence. So let's start with the excited state intramolecular proton transport in HPBI derivatives, what we call 2,2,5 hydroxyphenyl base imidazole carbene. This is a very common used molecule, so that will show proton transfer upon photoexcitation. So if you look at this molecule structure, so here the nitrogen and OH group in the same side, what we activated is just this now. So since the carbon, this single bond is there, it will also form a rotamer. So what we call it is a transcender. So what is the interesting thing is that when we photoexcite it, so this C signal will go to the excited state where the acidity of the OH group will increase and basicity of the nitrogen group will increase. So basically it will act as a photoacid and photobasis. So what will happen in the excited state, this proton will transfer to the nitrogen group, and here it will form a ketone tautomer. And we will get a high Stokes shifted emission. That means there is a huge gap between the absorption and emission. In the meantime, so this trans also will be excited and it will give a normal emission. That means in the S1 state, two simultaneous emission will be there, and by virtue of which we will get a dual emission. So if you look at the fluorescence spectrum of HPBI in ethanol, you can see the normal emission, this sort of this is the normal emission and this is the tautomer emission. But now people want, since everybody wants to apply this molecule in the ophthalmology or bioelectronics like this, so they don't want this normal emission because that will waste the fluorescence by because of the energy transfer or charge transfer. So what will happen? By keeping that in mind, so we have designed this molecule. So where we have two base imidazole moiety, and in the ortho to the OH group, we put a tertiary butyl group. And what is the role of this tertiary butyl group? I will also talk soon. But here, if you look at this fluorescence spectra of this SPBI with different solvent, with increase in the solvent polarity, it will keep on blue shifting. So blue shifting, that is the negative solvatochromism, is a very characteristic of the proton transfer behavior. And which also we confirm from the when we plot it is ET30, that is a solvent polarity parameter with this lambda mass. So there also we clear that there is also we got a negative solvatochromism. So here it clearly confirms that this molecule also giving a proton transfer. So what is the next? We also call this as the photophysical parameter, but here one computer time parameter is the lifetime. Time resolved fluorescence measurement. In the cyclohexane it is giving 4 nanosecond and acetonitrile is the 2.6 nanosecond. That means in the excited state it is giving a single lifetime. That means in the excited state one emitting species is there. So what is that? So that is a little bit confusing because in this BCSPBI we have the 2H group. That means 2 ketototomer should form and that should give 2 lifetime. But here it is giving 1 lifetime. So this suggests us that means 1 keto only form. To further understand this, so what we have done? We have done the DFT by optimizing all the possible conformers of the BCSPBI. And from here also we know it is the emission which is formed from the monoketoform, it is experimentally matching with the ketototomer. And when the experimental emission from the diketo is not, it is energetically unfavorable. From the theoretical calculation also we conclude that this is a single proton transfer, not a dual proton transfer, though it is having a 2OH group. So further we also single proton transfer evidence because we have used different neutral density filter and we have series of experiments with the different excitation intensity, and here also you can get the slope is equal to 0.96. That means this is a single proton transfer process. So what will happen if you, what is the difference that if you check about the SPBI fluorescence spectrum in methanol and the fluorescence spectrum of the BCSPBI in methanol, this normal band is almost wedge. So what is that? That means as from the beginning I am telling, this rotamer is not favoring in the BCSPBI because already in the ortho position this tertiary butyl group is there. So it will unfavor the formation of the rotation. Because of this steric effect, so this normal emission is not coming. So from the BCSPBI we conclude that it is giving a single proton transfer and that is due to the excited state intramolecular proton transfer process. So what we further did, so in place of the NH we have put the oxygen and here sulfur. That is we have oxazole and thiazole derivative we have put. So we went for the similar photophysical studies. In the BCSPBO, the photophysical properties is more or less similar. But when we went for the sulfur, what we observed, this last one, this sulfur derivative one, is not soluble in most of the organic solvent. So that is because we tried to do the molecular photophysics study, but in the last one, it is not soluble in most of the organic solvent. But it is found that it is well soluble in the tetrahydrofuran and also not soluble in water. And with literature review, we found that, so now a lot of research is going on the aggregation induced kind of things, that is the organic fluorescence nanoparticle. So what we did, we have tried to prepare the aggregate by using precipitation method. That means the molecule is soluble in the THA and we are different water fraction of the water. So that it is insolubility that leads to the formation of the different aggregates. So what we call also fluorescence organic nanoparticle. So if you look at the optical studies, it is very interesting. So with the increase in the water fraction from the 0 to 60%, only the observations keep on decreasing. So no spectral change, nothing is there. So still it suggests that the molecule is molecularly dispersed solution. Only the difference is that there is a change in the polarity. But when we went for the higher water fraction, let's say around 70 to 90%, the absorption is red shifted and also little bit of scattering was there in the red side. So this confirms that there is a formation. This scattering suggests there is a formation of the something aggregated particle in the system. That's why this scattering is there. To know that aggregating structure, so we also did the imaging. So you know in the 0% there is no such morpholysis for and here in the last one we got the fibrous morphology. So when we also go this emission properties, you can see this molecule in the 0 to 6% no such emission is formed, and in the 70% this aggregation is suddenly enhanced. So what we call this is nowadays is aggregation induced emission. So and because of this is and also evident by the different studies like thermal studies, emission studies in the different medium and also time fluorescence lifetime measurement. So here also we conclude that this is because of the aggregation induced emission. So in the 1 minute, so I will just, so this is the application, I will skip this slide. So next one is the room temperature phosphorescence, but in the 1 minute I will finish. So as I talk about, the phosphorescence is not very tricky to get because you know very slow IS intersystem crossing from the T1 to S0 transition, and the triplet state highly sensitive to the oxygen and moisture, so it will quench the emission. And so mostly this phosphorescence is highly reported using the heavy metal atom because that is favors the inorganic coupling. Because heavy metals are toxicity, so people are trying for the alternative because phosphorescence materials they are also used in the optoelectronics. So now what is people are using boosted organic molecules and they are using also crystallization that non-ready decay will be reduced. As a result of which it will also give phosphorescence. That means if you design all these molecules, we have to take care of these parameters, so we will get a phosphorescence. So we have also designed this molecule and we have all the PL studies. And here you see that in the boundary receptive pattern of the crystals powder with grinding with a different type, it has a different pattern. That means this pattern is different in the different medium. So here, when we are giving the delay, that means when we are removing the fluorescence, we are getting the emission around 30 microseconds in that range. So this is again, this is a behavior of the triplet thing, that is the ADA for phosphorescence. Further, we have different studies like oxygen purging, lifetime measurement, fluorescence decay, analysis in the different temperature, even in theoretical studies. So from here also, we conclude that this is a room temperature phosphorescence one. So again, this is just quickly, when we are handling with phosphorescence, we will also take little bit of care because if you see the first paper in the 2021, ultra low room temperature phosphorus found to the boric acid, but the 1 year later, the lab where we worked in the Spain and with collaboration with the government, then we published that pure boric acid does not show room temperature phosphorescence. It is in the organic chemistry. That means when we are handling with phosphorescence, we should take care of the purity of the sample. Because in the first report, the molecule itself is not showing any phosphorescence because of which molecular behavior, but due to the impurities. And also this, and all the criteria what is taken care, we have clearly written in our review in the aquatic chem also, where we have discussed all the factors. So last, this is also one organic molecule. We have did lot of spectroscopic properties. And this is a highly used 4 dp IPVL, and this molecule also highly used in the organic synthesis. And this is also TDL here also we have studied, and also we have used the transient absorption studies. Because of the time shortage, I am not going to details explain these things. And also we have also done a lot of theoretical things to show this TDL behavior of this molecule. And this is all about my talk today. And thank you very much for your time.
Thank you, Dr. Bera, for completing the time. In a shortage of time, let us interact with him during lunch time. Thank you.
I now request Professor Swain to elicit Dr. Asri Tripathi member in our category 2 with a cash prize of ₹1,000, certificate and 1,000. I now request Professor Das to felicitate Chair Professor Swain. Next, thank you, Professor Swain. Next is two talks are there. I request Professor Bhubaneswar sir to please chair the session. Professor Bhubaneswar is a retired professor of Orissa University of Agriculture and Technology, OUTR. Professor Behra received his PhD degree from RRL Bhubaneswar. Presently, CSR IMMT. He has more than 35 years of teaching experience. He authored 35 publications, 2 patents in his name. He has guided 3 PhD students, 30 MSc students, and he is also the former president of Orissa Chemical Society. I now request Professor Acharya to please chair the session. Oh, sorry, sir. Professor Sipati Pani Memorial Award. It is Mr. Rohit Kumar Raut of NIT Rourkela.
Well, it gives me great pleasure to talk about Professor Sipati Pani. Once we were colleagues, so I am the first person to say a few words about a nice gentleman, Professor Pani. He was born in 1917, Patna, MSc in chemistry. Then he went to London for his PhD on Commonwealth Fellowship, got the PhD from a renowned inorganic chemist, came back, joined our government service, was appointed as a lecturer in Orissa College. Later on he was shifted to UC Burla, now BSS UT Burla. Then he jumped to University, Sambalpur University at Jyoti Bihar, continued there for 6 years, then retired at the age of 70. In 1977 he retired from active services. He is a nice gentleman, never speaks anything to hurt anybody. That is the beauty about him. Never, as head or as a man, so meticulously, he calculates all the, suppose you are having a feast or some dinner or some lunch or a big gathering, then he will calculate everything, one by one, everything. He was known as Professor Pani in Burla. 60,000 population, but he is well-known Dr. Pani. Everybody knows him, that he is Dr. Pani. So this is Dr. Pani. He was blessed with 3 daughters and 2 sons. 2 sons are no more. 1 daughter is no more. Only 2 daughters are there. The elder daughter and the youngest daughter are living. So with this I hand over to my.
Now request Mr. Rao to deliver a talk. So Mr. Rao, just 1 minute. You try to finish within 15 minutes. And 5 minutes for discussion. Because you are a student, I think. So you only focus on your own work.
Yes, sir.
Review work just become a little less. Okay.
Okay.
The previous work every month possible.
Okay.
Focus on your own.
Hello everyone. My name is Rohit Kumar from NIT Rourkela, working with Professor Ravindra Kumar Pera. And the theme of the work is we are proposing that iron protein can be used as iron supplement over the commercial available iron supplement to eradicate iron deficiency anemia. So let's start with iron deficiency anemia. This is the most nutritional disorder in the world. Due to its broader impact, it is called as hidden hunger. And why it occurs? When your body doesn't have sufficient iron to produce hemoglobin, which is found in the RBC, and the role of hemoglobin that carries the oxygen to the various tissues in your body. So if you account the stats of iron deficiency anemia in the world, it is around more than 1 billion. That means 1 in 8 people is suffering from iron deficiency anemia. And mostly, if you see the world scenario, this I have depicted here the maps of world, and sadly, India is suffering most in iron deficiency anemia. mostly the children and women in the world suffering from the iron deficiency anemia. So let's see what are the causes of iron deficiency anemia. Before that, let me tell you that our body doesn't synthesize iron in our body. The only source is the diet. So I have highlighted here the insufficient iron in the diet and the inefficient absorption of iron, and most importantly the blood loss. So whenever you are suffering from iron deficiency anemia, you will go to the doctor and doctor will prescribe some medicine, that too dietary mostly. If you are severely affected, then you will be having the intravenous. So mostly people are doctors prescribe the dietary thing, that is ferrous salts or ferric salts. These are some examples I have shown here. So how it is absorbed? Whenever you eat something, it will go from the stomach to, from the mouth to stomach. Then it will absorb at the intestine, mostly the duodenum and the jejunum. And when we found that the solution became the another problem. Then thereafter, what are the problems associated with the iron supplements? So they are prone to produce the infection, and the Fe2 plus participating in the Fenton's reaction produce the hydroxy radical, produce ROS that may kill your cells, that may upset your GI tract, the gastrointestinal tract. And when it will traverse from the stomach to intestine, it may the Fe2 plus convert into Fe3 plus, and Fe3 plus is insoluble at pH 7. It will be precipitated at pH 7. That as a result, the impaired absorption of iron will be occur at the intestine. If it is soluble, then only it will be absorbed, and most importantly, it will be absorbed in +2 form, not the +3 form. So what we have proposed here, the protein I told that I am working with the iron protein, that is ferritin protein. It's like hemoglobin, that is 4 subunits. It has 24 subunits. It will make a cage-like structure, and the important point is it stores iron and sequesters Fe2 plus, and it oxidizes the Fe2 plus into Fe3 plus, and that Fe3 plus will be stored as hydrated ferric oxide mineral in soluble form, not precipitated, in soluble form. So our aim is that whenever you eat the protein or the fortified protein with the ferritin, that has to cross the stomach in intact form and will be absorbed at the intestine. So this is our aim. And most importantly, that hemoglobin contains 4 iron. Here the ferritin contains 4,500 iron. So let's compare between the commercial iron supplement. As I discussed that these are the disadvantages of commercial iron supplement, and let's see the advantages of ferritin iron mineral. So most importantly, it is soluble in water, aqueous medium, and it can store 4,500. And by sequestering Fe2 plus, it shows antioxidant properties. And like the Fe2 plus, that is ingested by DMT1, that is divalent matrix transporter 1. Same like whenever you are suffering from iron deficiency anemia, the intestine overexpresses the transferrin 1 receptor, and that receptor will specifically recognize your ferritin protein inside it and ingest into the intestine. So soluble iron can be alternative supplement, that ferritin, to all such problems it can eradicate. So whenever I am saying that is dietary iron supplement, you have to eat it. So you have to face the gastric stomach, that is around 1 to 3. We have taken that is 2.5, and you will meet the pepsin, the endopeptidase. Whatever you eat in food material, you will find if you have some proteins, it will be broken down by the pepsin, that is endopeptidase, and the retention time, keep in mind 1 to 3 hours or 4 hours. We have taken here 1 to 6 hours to show the stability of the ferritin protein, how far it is stable in the gastric condition and the pepsin concentration. So we have taken here the utmost concentration of pepsin, and we have shown in nettipage analysis. The nettipage is like the polyacrylamide gel electrophoresis, and we have prepared the gel, and you can see the blue stains. These are the proteins stained with the Kumasi, and you just see in 1 hour condition the protein is still intact. But whenever you increase the concentration, the degradation starts. But whenever I am saying the retention time 1 to 3 hours, the pretty stable at even at 5 mg per ml, the ferritin protein. So this is the normal concentration, physiological concentration of pepsin, that is 0.5 to 1 mg per ml. You just see the lane 2 and lane 3 has the pepsin concentration 0.5 to 1 mg per ml, and it's showing the pretty stability against the gastric pH as well as the pepsin concentration. To further stabilize, what we have done, we have taken a polymer, the natural occurring polymer, that is chitosan. This is biocompatible and biodegradable. To further stabilize the ferritin protein as well as the mineral of the ferritin protein, what we have done, again we have done the native page. What we have seen, we have added the mineral, and you just see the stored iron can be stained by the ferrocyanide, acid ferrocyanide, and it will be shown the insoluble form of Prussian blue, and you can see the iron mineral, the blue, the Prussian stains, the iron minerals. So in 1 hour condition, you won't see any kind of degradation or leakage of iron, but when you increase the time period, the degradation happens, and whenever you add the chitosan, you just see the retention of iron mineral as well as the protein structure. These are the protein structures and these are the mineral. So here we can see, we can say that chitosan stabilizes the ferritin protein as well as the mineral inside of the ferritin protein. Then to further see the cage-like behavior, as I said, this is a cage-like behavior, and at pH 7, that is the native structure of the ferritin protein, and in the gastric pH, without adding the pepsin, you just see the core mineral, that is the iron, is showing in black dots. Whenever you are adding the pepsin, it degrades the ferritin protein. Whenever you are incubating, it may degrade and leaches the iron protein, and you won't get any kind of cage-like behavior of the ferritin protein. But whenever you are adding chitosan, you just see the size of the ferritin also increases, the peripheral area of the ferritin increases upon adding the chitosan. Whenever you are adding chitosan in presence of pepsin, still the cage behavior is there. That means chitosan protects the iron mineral as well as the ferritin protein and increases the size, that first confirmed by the DLS study, that is the blue color one. Then after, we have gone for the reductive and non-reductive iron release, just to show how ferritin behaves in presence of chelators and reducing agents. We have taken here ascorbate as a reducing agent and bypyrityl as the iron 2 chelator, and this one is the definiprone, that is clinically available chelator. Whenever you are suffering from iron overload, the doctor will give you DAP to chelate the iron and minimize the overload of the iron in your body. So we have seen, then after we have found the binding stoichiometry, and we have seen that bypyrityl is 1:3, it binds to the iron, whereas the DAP binding is sensitive to pH. Whenever it is pH 7, that is 3 DAP, 1 iron, and whenever it is pH 2.5, that is 2 DAP and 1 iron. So from there we calculate the extinction coefficient and iron release, the amount of iron release from the ferritin protein. You see at pepsin and gastric pH, the amount of iron release is high. Whenever you are adding chitosan, the amount of iron release is significantly inhibited in presence of pepsin. Further, to check the stability, we have gone for the SDA space. In SDA space, you disassemble the 24 subunits into one subunit. This one is the pH 7, the control. This is the one subunit. Still, we saw that chitosan, in presence of chitosan, still the monomer band is there. That means chitosan not only stabilize the cage, also the subunits. That means it is interacting with the ferritin protein. Thereafter, further we have studied the secondary structure, and from the secondary structure by CD, we confirmed that chitosan stabilizing the ferritin protein, the orange color one, and whenever you are adding pepsin, this degrades the ferritin protein. But whenever pepsin is there and chitosan is there, it restores the ferritin protein, the secondary structure protein. And we further confirmed on the fluorescence that whenever we are giving chitosan, the intensity increases upon increasing the concentration of chitosan. So this is the I will summarize that in 1 to 3 hour condition without modifying the ferritin protein is stable and it retains the iron. But whenever you are increasing the iron amount, the incubation time, it degrades the ferritin protein here. But in modified condition, it restores the ferritin protein and as well as the iron. So it can be seen in the TM image. So I would like to show this article selected for hot article in RS Delta, and this is our proposal that it can be used as or developed as a iron supplement. So with this, I would like to thank my Professor Ravindra Kumar Behera, NIT Rourkela, and OCS for giving this opportunity to present in front of eminent professors and my staff from Ravenshaw University and my lab mates, the OUTR organizing team, family and friends, funding agency. Thank you.
Thank you, Mr. Rao. Finish in time, very good time. Keep it up. Okay. Is the next one? Ms. Chirasmai Man.
Any questions from audience?
Thank you. Okay, thank you. Thank you. Okay. I thank Mr. Rao for his good delivery, and he has maintained his style. Very punctual, very good time you maintained. Finished within 15 minutes. Any question? Anybody? No question. Okay. What's his other thing?
Professor Sripati Pandey Memorial Award. It is given to Mr. Rohit Kumar Rao with a cash amount of 4,000 rupees.
Next speaker. Mr. Suresh Rao. Oh, sorry. Chirasmai Mahanti, from Uttar University.
So before lunch, this is the last talk. So after this, we will go to lunch.
Sit present. Okay. This is Professor byDepartment Memorial Award, and I request Professor Jana to speak about him.
Okay, so I will not waste more time. 1 or 2 minutes, I'll say something about Professor Dayanidhi Patnaik. We have not seen, myself I have not seen Dayanidhi Patnaik. I am told that he was the professor and head of chemistry of Ravenshaw College, the then Ravenshaw College. And at that time no PG was there, it was only Ravenshaw College, but the PG was there. And he was the head of chemistry. He did PhD from Cambridge. That is how Cantum. Those people who do PhD from Cambridge, it is written PhD Cantum. So our S.R. Mahanti was also PhD Cantum, and Ravenshaw, Dayanidhi Patnaik was PhD Cantum. So that speaks of the person, the quality of research and everything. And in 2018, I think Professor Samantraya was the president of OCS, and in Ravenshaw we had the centenary celebration at Ravenshaw College in honor of Professor Dayanidhi Patnaik. And at that time Professor Samantraya was the chairman of OCS. We had a grand celebration. And one more thing I will tell him, he specialized in physical chemistry. And Professor Balaram Sahu, who came yesterday, happens to be his very close student. and Balaram Sahu was doing his PhD, MSc thesis and PhD, everything with Dayanidhi Patnaik. And I am also, yes, he had nature publication. So very high quality research publication from Ravenshaw College in those days from his group. And I am also told that Balaram Sahu was staying in his residence. He was a bachelor. Dayanidhi Patnaik was a bachelor, and Balaram Sahu during his research was staying at his residence in Ravenshaw campus. And Dayanidhi Patnaik at the fag end, we are told that he left Ravenshaw College in a fine morning. He packed his everything. We are told, we have never seen that. He packed everything, wrote a letter of resignation to Government of Orissa that I am quitting the service. So, and he wrote to the government that I will not claim any pension, any terminal benefit, anything from the Government of Orissa. So he joined Bhutan, Binoba Bhabhe Ashram, and then the Binoba Bhabhe Ashram he joined, spent throughout India. He spent his life, rest of his life in other states, and finally I think he died in Haryana when he was in the ashram, Binoba Ashram at Haryana, so he expired. He was a very legendary figure. Professor Patnaik guide Cambridge, I have to see the book. I still, no, Gordon Norris. Gordon Norris. Norris type 1, type 2 reaction.
Professor Jana, one thing I have to add there. Professor Norris, while submitting a paper for Nobel Prize, he got Nobel Prize. He wrote to Professor Patnaik because I could be informed this during that celebration. Professor Norris कहले जे दानिदी तुम नाटा मु आदरे माने इंग्लिश से कहले जे मु लेखुची तुम एते काम करछ यू विल गेट आल्सो से जानि थरो रुपे मिलि बोली कि जो नाही सर आपण दियंतु एते से एंते लोक थिले and that paper got Nobel Prize. So he was deprived of Nobel Prize. That was the thing because ei matter ta Patna University vice chancellor astel guest agree mate se कहले. So you do not know. Yes, he told me such things.
Yes. Many things are written in that book.
That a person for no country has deprived of Nobel Prize.
That centenary book, which was published in honor of the centenary celebration, contains lot of things about Professor Dayanidhi Patnaik. Very renowned professor, and he voluntarily quit the teaching profession, joined Bhutan. And in his honor, I think there is a trust by his, I think, Professor Prashant Patnaik. Prashant Patnaik, a retired professor from IIT Bombay. He was the secretary of the trust. Balaram Sahu was the president, and they spent everything for the celebration of that centenary celebration at Ravenshaw. And this award is in memory of Professor Dayanidhi Patnaik. That's all.
Ms. Bang, you are very fortunate to get all of this very, very great person. You might be the Professor Jana might be grand student of Dayanidhi Patnaik, not student. Anyway, please finish within 15 minutes. And we'll finish
it before that.
Okay, okay. Thank you. Thank you.
First of all, happy Krishna to all of you. Good afternoon, everyone. I am Chirasmikanti. At first, I would like to thank you, OCS, for allowing me and share my insight on this topic: concurrent photoreforming of polyethylene into commercial chemicals and hydrogen generation using graphitic carbon nitrate cobalt oxide catalyst of waste to wealth concept. These are the outline of my topic. Today I am going to discuss, that is background synthesis of catalyst, characterizations, activity evaluation, and conclusion. Before diving into my topic, I would like to give you a brief idea regarding the current issues carrying on in our society of plastic waste. As if plastic is omnipresent, plastic is omnipresent, it is found in every sector of life, from small household engineering to large industries goods. So plastic, if this present manufacturing continues, then by 2050, our surface will fill with 12 billion tons of plastic waste. During COVID-19 pandemic, a lot of PPE kit and face mask and PPE kit are used to create a serious concern how to manage the waste. Again, to eradicate this issue, we have to implement 3R rule, that is reduce, reuse and recycle, but that is not enough to recycle the plastic waste. So, there are several strategies have been implemented, such as incineration, mechanical recycling, thermochemical recycling, photocatalysis, and hydrocracking. Among these, incineration is a good process which usually convert plastic by burning into useful fuel. But it requires a higher temperature around, but it releases actually toxic gases to the environment, that is dioxin and carbon dioxide, ultimately hamper the climate change along with air pollution. Among these methods, all these methods are cost intensive. Rather, we should focus on the cost effective one, the photocatalysis, as our sun comprises of 43% of visible light and 5% of UV light. So by utilizing sun energy and using a semiconductor, we can convert the plastics into a value added product. Along with, we can generate the hydrogen. So from this slide, we can conclude that photoreforming is the emerging as a sustainable and environmental friendly approach to utilize and reform depolymerized plastics. Next, then what is photoreforming? And actually photoreforming and water splitting both are similar. Then in actual case, they require in water splitting they split into hydrogen or oxygen, but in plastic photoreforming we will get the value added chemicals along with hydrogen. It requires this process, water splitting process is highly endothermic in nature, and it requires a little amount of energy to change the plastic waste into valuable products. Photoreforming process is actually a fascinating green way to obtain hydrogen, and it uses as if our contaminant was plastic, that is polyethylene, used as a sacrificial agent to convert into hydrogen and other chemicals such as small aldehyde ketone or butanic acid. These are the, in order to perform photoreforming reaction, there are several catalysts has been used, which ranges between the band gap range between the 2.3 to 2.8 electron volt. So, in order to conduct the photoreforming, the conduction bandage potential should be more electronegative than the hydrogen, and valency band should be more positive than the oxidation potential. So, along this, several catalysts have been used to do the photoreforming of plastics like polystyrene, polyethylene terephthalate, polyethylene, polythene. So among this, graphite carbon nitrate graphite carbon nitrate has been used as a best photocatalyst and if we load some semiconductor into it, then a new novel photocatalyst will be developed, and that can easily convert plastic waste into a value added product. This is the scenario why we have chosen graphite carbon nitrate and cobalt oxide Z-scheme heterostructure. At first, graphite carbon nitrate is a visible light response photocatalyst along with good thermal and chemical stability, sp2 high nitrogen, and it contains 2D morphology. So at first, graphite carbon nitrate was synthesized through thermal polymerization using melamine as a precursor, or at 550 degrees centigrade it was calcined for 4 hours. Then with pairing graphite carbon nitrate, we have prepared the composite C3N4 cobalt oxide through hydrothermal process. So with that weight percentage defined, first we have prepared the neat graphitic carbon nitrate, neat cobalt oxide, and with the varying percentage of graphitic carbon nitrate, we have prepared the several samples. Among this, 10 CN cobalt oxide was found to be the best one. These are the characteristics of graphitic carbon nitrate cobalt oxide, which represents at figure 1. Graphitic carbon nitrate diffraction peak appears at 27.6 degree, while in the composite it disappears because with the loading of with the little amount of loading of graphitic carbon nitrate, the diffraction pattern doesn't show in the XRD of composite. As if the band gap energy is the important parameter for analyzing the light harvesting capacity of a photocatalyst, we found that the graphitic carbon nitrate band gap energy is 2.8 electron volt and cobalt oxide is 2 electron volt, while for the after the formation of composite it was found 2.75 and 1.55 electron volt. It means that it has already formed without any impurities. And again, same theme confirm the formation of graphitic carbon nitrate cobalt oxide. As we can see that the white dots, spherical particles of cobalt oxide was completely loaded onto the surface of graphitic carbon nitrate sheets. And this is the XPS data which entails about the chemical oxidation state and chemical composition of formation of graphitic carbon nitrate cobalt oxide composite. And also this characterization FTI shows that the cobalt oxide peaks were found at 572 and 64 centimeter inverse, which corresponds to the cobalt oxide formation, complete formation of cobalt oxide. And this is the PL graph, which indicates that the higher intensity was found at cobalt oxide, while the lowest one is the 10 CN CO3O4. It subjects that the lowest emission intensity indicates that there will be least charge carrier recombination. This is the comparison table. I will skip that. And this is the photoreforming of polyethylene. At first, we have dissolved the polyethylene into 5 molar of sodium hydroxide, and it was under the irradiation of light. It continued up to 6 hour and 12 hour. The gaseous products generated in that reactor, that is retrieved through syringe and subjected to gas chromatography instrument. Then we found that then we have calculated that 17.25 micromole per gram per hour inverse hydrogen was produced. And this above graph shows that this graph is that liquid was collected and run to the UV visible spectrophotometer, and found that after 6 hour and 12 hour we found that there is a complete degradation of polyethylene. And this is the hydrogen production efficiency of this catalyst under visible light. After as if the recyclability, as if the catalyst has a good stability, chemical stability, it was confirmed from the XRD data. Again, in order to check the photocatalytic activity of that catalyst, we have chosen the reactive blue 19 as a model dye. So there is a complete mineralization of dye using of reactive blue 19 dye, usually 40 mg per liter, that is 40 ppm, with the loading of 0.05, that is basically written 0.5 gram. So 0.05 gram catalyst was taken, and individual catalyst was checked that there is very lower photocatalytic degradation, that is 23% found in the cobalt oxide, and graphitic carbon nitrate showed 67%. Here from the scavenging study, we have found that the superoxide and hydroxyl radical participate in the photocatalytic degradation process. Again, this is the last one. This scheme is a Z scheme, as if the charge carrier, this Z scheme involves the electron transfer from the conduction band of cobalt oxide to valency band of carbon nitrate rather than traditional type 2 mechanism facilitating efficient charge separation. Both the radicals, as we confirm from the scavenging data, that hydroxyl and superoxide radical are the main active species driving the photodegradation process. Here we can say, in order to confirm the mechanism, we have taken hexachloroplatinate acid into that reaction and run for 3 hours and got that the platinum got reduced from +4 to 0 on the graphitic carbon nitrate sheet, not on the cobalt oxide. This is the conclusion, and last but not the least, a series of graphitic carbon nitrate cobalt oxide composite was synthesized by FSI in Institute of Hydrothermal Technique. Among the 10 CN cobalt oxide was found to be the best one, and it was used both simultaneously for transforming plastic polyethylene along with generation of hydrogen, and it also degraded reactive to nitrate. I would like to thank my supervisor, Professor Nigamananda Das and Dr. Ajay Kumar Behra, and my senior lab mate, Dr. Alka Samban, and my lovely juniors, Priyanka and Subhasri, and to the Department of Chemistry for providing Orissa 2.0 fellowship. And this paper has already published on the International Journal of Hydrogen Energy. Last not the least, I would like to thank OCS.
Thank you.
Any questions may be discussed during lunch hour because it will be late, too late. I now request the Professor Acharya to felicitate Chiraswai with a cash award of 1,000 rupees, a certificate, a memento, bouquet. One book of Mahindra Anand is given to her. And similarly, in the morning session, we have not given to Dr. Jena and Behra. So we will hand over the books during lunch hour. They are not present here already. Since we are late, now we have to proceed for lunch. And we will assemble here at 2:45. I request all the participants, particularly the students, they have to come early so that the next talks will be arranged at 2:45. Sir, Raman sir, Rajan sir, apna asentu.
বিভূতি বাবু and they left. First, Amar left. He went to Germany, Humboldt's fellow. Then a few months later, Manju also moved, and from Germany they went to US, and from US they went to Canada. In Canada, in Guelph University, both of them are very distinguished professors, and they are really doing well on biocomposites. They have their own industry, and they have many PhD scholars guided by both of them. They have got some civilian honors also. Manju has got some civilian honors also. So in that country, you can see more details about her when Madam Anita Pati presents her work. And she contacted me to institute, in fact Amar contacted me to institute this award, and in the name of his wife, by donating 5 lakh, meant for senior scientists, women scientists of the state. That's how this Manju Mishra Award has come into existence in Orissa Chemical Society. So with these words, I think I have done my job. Thank you.
Thank you, Dr. Samal. Dr. Pati, Dr. Anita Pati, please. Time allowed is 15 minutes, although it is 20 minutes, but I am constrained to tell you 15 minutes because there are 30 to 35 oral presentations, which will take up to 7:30 p.m. Okay? Please do not mind for 5 minutes. Okay, take it.
Good afternoon to everyone. Hope I am audible to the last bench. Last students, am I audible? Okay. So my revered teachers, distinguished delegates, and dear students. First of all, I am very much thankful to the Orissa Chemical Society for considering my candidature for the award of Professor Manju Mishra Award. And I feel honored and blessed to receive this award. And on the basis of the contribution that Professor Manju Mishra has given to the scientific society, I feel it is not a simple award. It is a responsibility given to me, and I will try my best throughout my career to give justice to this award. It's my duty to introduce Professor Manju Mishra to the gathering present here. Professor Manju Mishra is an Indo-Canadian professor. She is a Tier 1 Canada Research Chair in Sustainable Biocomposites at the University of Wales School of Engineering and holds a joint appointment in the Department of Plant Agriculture. Professor Mishra is also a lead scientist at University of Wales Bioproducts Discovery and Development Center and a fellow of the Royal Society of Canada, at the American Institute of Chemical Engineering, the Royal Society of Chemistry UK, the Society of Plastic Engineering US, and the Indian Institute of Chemical Engineers. Professor Mishra was born in Orissa into a family of academics to her father late Pandit Govinda Chandra Mishra and her mother late Mrs. Subhashini Mishra. She received her high school from Ravenshaw Collegiate School, Cuttack, and bachelor's degree from Stolawala Women's College, Cuttack. She completed her master's and PhD degree from Ravenshaw College, Cuttack, at present it is Ravenshaw University, and pursued her postdoctoral research in Frisch Haber Institute of the Max Planck Society, Berlin, and Technical University, Berlin, Germany. She has many awards and accolades to her credit. The most prominent one is like in 2024, she has been selected for the Global 50 Women in Sustainability Embrace Boldness theme, and that is in New York City, USA. She is a recipient of Lifetime Achievement Award by the Bio-Environmental Polymer Society, USA in 2021. She is also a recipient of Canada Research Chair, Tier 1 Sustainable Biocomposites from NSERC in 2020. In the same year, she has been selected for the Canada's Most Powerful Women top 100 awards in the category of like Manulife Science and Technology. She is also a recipient of like CEPS Undergraduate Supervision Award. She is also a recipient of the prestigious Glory of India Bharat Jyoti Award in 2019, Women of Distinction on STEM in 2019. Similarly, NSERC Synergy Award for Innovation by the like Natural Science and Engineering Research Council Canada in 2018. She is also a recipient of Andrew Chase Forest Products Division Award in 2017, University of Wales Innovation of the Year Award Canada in 2016, and also the Composites Parte Most highly cited paper award in 2014, and Jim Hammer Memorial Service Award in 2012. With this brief introduction of Professor Manju Mishra, I pay my utmost respect to her and going to start my presentation. So before that, just as it is an award lecture, just I want to give my brief overview of what I have done in my career. I started my research career as an MPhil student in Sambalpur University in 2003. There in my MPhil and PhD both, I have done some heterocyclic synthesis, and in particular I have done some spiroheterocycle synthesis where pharmacological active compound we have synthesized. With the same, having the same heterocyclic synthesis base, I joined the group of Dr. Santosh Janardhan Kharpure and Dr. D.K. Chand, and have been introduced to an interdisciplinary field that is supramolecular chemistry, which includes both organic synthesis and supramolecular. And then there I got a relevant experience in the synthesis of triptans, triazole-based oxabols, and then cages and their applications. On the basis of then same experience, I joined KIT University in November 2013, started my independent research, and again I started in the same like heterocyclic synthesis, but in working in two different domains. One is based on the synthesis of other heterocycles through conventional, non-conventional and catalytic approaches, and also we are working on the heterocyclization of cavetants, and at present we are focusing on the resorcinary cavetants. So today my work like that I am going to focus here on the other heterocyclic synthesis, and particularly my topic of discussion is heterogeneous nanocomposite catalyst, an efficient and greener method for the synthesis of structurally diverse 5-membered and heterocyclic derivatives. This slide I have kept for the students. You know that like actually 5-membered heterocyclic compounds are one of the significant class of heterocyclic compounds. We can divide it as 1 nitrogen, 2 nitrogen, 3 nitrogen, 4 nitrogen. When it is 1 nitrogen, we can call it as pyrrole. Then 2 nitrogen, there are pyrazole, imidazole compounds can be there. And when it like 3 nitrogen, it can be 1, 2, 3 triazoles, or it can be 1, 2, 4 triazoles. You know that 1, 2, 3 triazoles can be synthesized by the famous like reaction that is click reactions. Similarly, when 4 nitrogen enter, you can have the tetrazole derivative. These are very important class of like compounds, heterocyclic compounds, where you all know, the students particularly, you know the DNA RNA, right? So purine bases, pyrimidine bases are there. Purine bases is having imidazole derivative. So one of the important component that is present in our body. Along with that, it is also having a lot of applications like pharmaceutical applications, most importantly. Then it is also having industrial applications. It is also having like optoelectronics applications, light emitting diodes we are using, like anti-corrosive dye we are using. In that case, like photocatalysis, we are using this one, flow chemistry, and many more applications are there for these compounds. Now, many in literature survey, we have got like many conventional and non-conventional approaches has been like given, and here in most of the cases, we have found that they have harsh reaction conditions, long reaction time, and toxic organic solvents people have used. Now, tedious workup and purifications are required for the getting the pure compound, and also they use the strong oxidants as a catalyst. Now also in many cases we have got like complicated and expensive catalyst people have used, and also in most of the cases the productivity is very low, having the low atom economy. So the objective of our work is to introduce efficient and eco-friendly synthetic methods for the synthesis of 5-membered N-heterocycles, to find the green and inexpensive simple catalyst for the synthesis of 5-membered N-heterocycles, to focus an environmental friendly approach with high atom economy, and after synthesis of these compounds, to study the biological applications of the synthesized compounds. With that objective, we started working in the catalytic approaches. In our lab, we have used many different type of like natural compounds also we used, like orange juice, lemon juice, tea leaves. We have used like benzimidazole can be prepared using the tea leaves. Similarly, we have also used simple catalysts like copper 1, copper 2 catalyst. Also, we have used a very simple metal complexes for the as a catalyst. And recently, we started using the nanocomposite catalyst for the synthesis of the heterocyclic compounds. And here, for the students, what is a heterogeneous nanocomposite catalyst? You might be thinking that this is actually a material that consists of the nanoparticles combined with other substances. Now, depending upon the other substances like metal, you can use metal oxides, you can use carbon-based material, you can use, and polymer-based components also can be used as the other substances, and to enhance the catalytic activity and selectivity in various chemical reactions. The main key features of these compounds are they are having nanoparticle in size, and they have like better surface area, and enhanced catalytic properties they have. Synergistic effect, actually when you combine A, you are taking one compound, other one B you are taking, and they are having two different activity. When you combine and they are having better activity, that is called your synergistic effects. So they are having better stability and durability, and also their reusability is more. Now depending upon the substance, you can categorize this heterogeneous nanocomposite catalyst. Like if you are using metal, you can say it is metal-based nanocomposite. Similarly, metal oxide-based nanocomposite, carbon-based nanocomposite, polymer-based nanocomposite. So here I am going to give two examples. One is the GeoTiO2 nanocomposite material, which we have used for the imidazole synthesis, and the second one that we have used the cesium-based like mesoporous zirconium phosphate catalyst that we have used for the tetrazole synthesis. So my first example is this GeoTiO2 nanocomposite, an efficient catalyst for the conventional and ultrasonically mediated multi-component synthesis of imidazole derivatives. Here, the research content of this particular total work I have confined here that we have actually reported a flexible, reliable and effective method for the synthesis of wide variety of highly functionalized 2,4,5 tri-substituted imidazole derivatives, and it involves a one-part synthesis, and this like multi-component process we have used variety of the components like varieties of aldehydes, ammonium acetate and benzyl and benzoyl. These both we have taken for the reactions, and like GeoTiO2 has been utilized as a catalyst. Now in this one-part synthesis has numerous benefits, particularly like Benning reaction conditions, a quick reaction time, low catalyst loading, efficient productivity with better atom economy, and functional group tolerance, which makes this methodology more realistic. Now TiO2 is a very known catalyst which has been employed in many like reactions. However, GeoTiO2 was not explored. It was not at all used any time like for the heterocyclic synthesis, and for the first time we have used this one for the synthesis of imidazole derivative, and that's why we have introduced this nanocomposite catalyst to the heterocyclic synthesis. Now among the TiO2, GeoTiO2, both that like catalyst we have like used for the synthesis, and in that case actually GeoTiO2 exhibited better catalytic efficiency and provided greater substrate scope with alpha hydroxyketone, that is benzoin, and 1,2-diketone, that is benzene. Now both conventional and ultrasonically mediated method we have used, and we found that ultrasonically mediated method given a better yield as compared to the other one. Now TiO2 has been synthesized by using the precipitation method. That graphene oxide has been used like synthesized by using the Hamas method. These are the known methods, and they have been combined for the like formation of GeoTiO2, and hydrothermal method has been used for the synthesis of this particular catalyst. They have been characterized by using the FTIR like XRD and many more characterization techniques. So in case of FTIR, you can see there is a TiO2, TiO-Ti like at almost like 1698, and another one is like in TiOC, which is 67. So in that case, like we have got some confirmation for the synthesis of this, not actually proposed for the like molecule that has been synthesized. Now in case of XRD, you can see the 2 theta index is 002, which has given a significant actually confirmation for the formation of this particular composite, which has also been supported by the Raman analysis. Now we have used the FeSEM, and in that case for graphene oxide also we have taken, and graphene TiO2 also we have taken, and when we combined it, we got a cluster, a nano cluster, and we observed it, and it is very clear from the FeSEM. And actually the element analysis also has been done by using the ATX analysis, and it is in support of the formation of the GOTiO2. Now by using the GOTiO2, we have used both TiO2 and GOTiO2 we have used separately for the synthesis of the imidazole derivatives, and in both the cases we have taken benzoin also and benzyl also, and to understand the substrate scope we have changed many substituents in these cases. Now we did the optimization reaction because we were interested to utilize the efficiency of the GOTiO2, so we have done the optimization reactions. And in case of TiO2, you can see when you have used we have used particularly 15 mole percent and 100 degree Celsius temperature, we have got maximum 80 degrees 80 your percent of the yield. And in that case however, when GOTiO2 had been used with the same solvent system, and in that case 90% yield we have got with 10 mole percent of the catalyst, and giving it is proving it as a more efficient catalyst than the TiO2. Now we have done the ultrasonically mediated method also. In this case the temperature requirement is low, and here 60 degree and with 18 minutes only. In that case actually it was taking 25 minutes, here it is 18 minutes. We got the better yield similar type better than that 92% yield we have got. Now so we have to understand the substrate scope. We have used 20 examples we have done by using the GOTiO2, and in that case by using the optimized reaction conditions, and in case when these two phenyl groups were at test benzyl, in that case and normally benzaldehyde when we have taken, we got 95% yield for this product. We have also tried to understand the recyclability of the catalyst, and it was used up to almost 6 cycles without having any significant change of the catalyst. So this can be reused more than 6 times, and this was also by checking each time the FTIR of the catalyst we have proved this one. Now a plausible mechanism we have proposed that from ammonium acetate, ammonia, actually this ketone is being activated by the GOTiO2, and then the ammonia is reacting with the aldehyde, giving an imine system which is further converted to the diamine. Now diamine is actually reacting with the diketone system, giving the precursor of the imidazole derivative, and from this imidazole derivative, also from benzoin if you try that is also given by the imine system which is being converted to the imine system, then that is reacting with the imine, another imine system which is with the aldehyde, and given the component this C which is a precursor of the imidazole derivative, and then further dehydration along with the 1,5-C, the desired product is obtained. Now my next example is the cesium based mesoporous zirconium phosphate catalyst. It is also a novel catalyst. Here we have synthesized this novel catalyst by actually and given that heterogeneous nanocomposite catalyst with well-defined surface acidic sites and structural porosity. And zirconium phosphate is an inorganic material, and it is having a layered structure which exhibits ion exchange, proton of conductivity and adsorption properties. Then alpha zirconium phosphate studied extensively for its catalytic activity, and for the particularly the reactions that is dehydration, isomerization process, as well as the selective drug delivery. And but it is having the low surface area and small interlayer spacing, which limits its application as a solid acid catalyst. Now to overcome actually this problem, advancement in the alpha zirconium phosphate has been done by giving it a mesoporous architecture. Now during that, after the advancement, it started showing a better excellent catalytic activity with high surface area and narrow pore size. Still, there is a limitation for its application towards the acid catalyzed reactions. Now again another type is there, that is heteropoly acids, which generally, yes, I'll complete it. So Kegging type heteropoly acids, these are actually widely employed for the catalysis due to their accessibility and chemical stability, but it is having very low surface area. So what people have done, generally they do alkali ion like metal ion exchange heteropoly acids people have used. So by combining these things, what we have done, we have used mesoporous zirconium phosphate as actually that we have taken as the porous matrix, and we have taken the cesium exchange phosphotungstic acid as the nanoparticle, and we dispersed it and we generated a catalyst. We have taken different type of cesium compositions like 0.5, cesium 1, cesium 0.5, cesium 2. 3 types of components we have synthesized, and we observed that cesium 0.5 was much better, having the more number of acidic sites and having more like its potential. And then this has been utilized for the 3+2 cycloaddition for the synthesis of this tetrazole derivative by using the starting material as the substituted nitriles and sodium azide. Now this molecule, that actually as I told, dispersion has been done by using the hydrothermal method, and different characterizations. I am skipping the characterization due to the time limit. Just I'll go for the, yes. So here we have utilized this like substituted nitride with sodium azide for the synthesis of the tetrazole derivative, and here we observed that when we have used the 0.5 cesium system, at that time we got a much better yield as compared to any other in all the components. For the students that I am telling, it is not when I am showing this slide, it is 1 minute or 2 minutes, but my students have invested more than 6 months to 1 year for this particular table generation. So then by using that optimized reaction conditions, we have done 16 examples in this case, and we have got like 70 to 90% yield by using this particular component catalyst, and particularly when it is a benzene system, at that time we have got like benzenitrile system, at that time we got 90% yield of the compound. So recyclability test also we have done, and we got 7 cycles in this case without any significant change of the catalyst. Now in conclusion, we have developed 2 very novel catalysts for the heterocyclic synthesis, particularly imidazole and tetrazole. In one case we have used its UTiO2, which was first time it has been introduced. Similarly, the cesium exchange phosphotungstic acid dispersed in the mesoporous zirconium phosphate we have used as a novel catalyst for the synthesis of tetrazole derivatives. So again, it is always my pleasure that it is not a single that I am presenting, but the work has been done by students. So I always am like thankful to my students, like Kanyanjali Samal, most of the work she has done, and Manas Ranjan Soil is my PhD student. He also a part of this particular synthesis, whatever I have shown here, and I am indebted to my collaborator, Dr. Savita Patel from NIT Rourkela, Dr. Braja Gopal Mishra from NIT Rourkela. This catalyst, second catalyst what I have given has been like given by him. Actually, he has given us the idea and everything. And like Dr. Chandrasekhar Purohit from NICE Bhubaneswar, who is always helping me, and our Central Research Facility of KIT University, because we are because of the instrument system we are able to do all this characterization properly, and all the finance like SCRB, VRNS, and particularly KIT. My sincere thanks to our founder, Professor Achyuta Samanta, for giving us this platform to have this kind of like your research thinking that we are doing innovation. About the innovation we are able to think. And last not the least, my family members. I have just like in my slides, application slide, I have written that actually for the inspiration of the students, I got married at the age of 18 when I was in BSc first year, and I completed my BSc, MSc, MPhil, PhD postdoc after my marriage. So I am always like thankful to my daughter and my husband who supported me. It is because of their sacrifice, their support, I am standing in front of all of you. And my parents, whose blessings always helping me to like do something in my career. All my teachers, thank you very much. Thank you all.
Thank you, Dr. Mrs. Sarthi, for the presentation with all clarity. So let us give a big hand once more to Dr. Pati. So any question? One question only. Because there are a lot of mechanisms, so there will be certainly one question.
Anita, an excellent lecture. Your target molecule towards the last part which you have shown, that molecule can be converted, you see, stator reaction, when thiazolium salt is used in presence of a base for ompolong reaction. Okay, is a cyanide surrogate. So your target molecule, I was looking at it, you can convert that one to the starting material for stator reaction. So this is an input for you, because what you synthesize, that will convert, that can be used in stator reaction. Stator reaction is thiazolium salt in presence of base, and that acts as a surrogate for cyanide ion.
I will discuss with you and I will try further.
Okay. After this, I will discuss with you.
Thank you. Thank you. No more question. Now, next one is.
Sorry, madam. Please stay here. We have to felicitate Madam Misra with Dr. Manju Mishra Award and with a certificate, and prize money is 15,000. 15,000.
Award money.
Highest in any of the OCS award.
Certificate. এটা ବହୁତ ପଇସା ଆମଠୁ ଅଛି next is Bhubaneswar Das Memorial Award in Environmental Science. It will be delivered by speaker is Sri Aparajita. Regarding Bhubaneswar Das, let me tell one or more two sentences. He is the father of our teacher, Professor Chittaranjan Das, was a man of physical chemistry. And, he has contributed to institute this Bhubaneswar Das Memorial Award in Environmental Science. This talk will be delivered by Sri Aparajita. Please. I am allowed 15 minutes, please.
OUTR. So first of all, I want to thank the OCS organizing members or committee for awarding me the prestigious OCS Bhubaneswar Das Memorial Award. And the paper for presentation, the topic is AG co-catalyst dispersed monoclinic Di2O3-GC3N4 with induced vacancies and porosity for fluoroquinolones abatement and antimicrobial activity. So without further ado, I would like to start presenting the paper. So what are the forever chemicals? The toxic molecular compounds, sometimes referred as the forever chemicals, that are persistent to environmental degradation through chemical, biological and photolytic process. So there are several kinds of organic pollutants available like pesticides, BPA, polycyclic aromatic hydrocarbons, and antibiotics are also regarded as one of the organic pollutants. You may think why the antibiotics should be regarded as the organic pollutants. Basically they are the medicines that fight the bacterial infections in the people and animals. However, they have also certain toxic impacts in our society. See, the highly persistent seems only partially degraded. They have a high lifetime or higher half-life time. Because of that, they are partially degraded and are ultimately discharged in the environment. Second is that because of the higher half-life time, they are contaminating the natural resources. They are also causing the bioaccumulative and involved in a biomagnification. Biomagnification means that from a tiny cellular level, they ultimately get upgraded to the higher predatory level, means the tertiary consumers. And due to that, they get persisted in the environment for a larger fraction of time. Also, they can cause several various health hazards also. When we all know that there is an optimum dosage of all the antibiotics. Beyond that, if we take that one, they may cause health hazards also. They are also the key factors for endangering the wildlife and native plant species. Now, I would like to explain about the fluoroquinolones. These are a class of antibiotics which are basically used for treating maximum of the infections that are present inside the human body. For example, the ophthalmic infections, respiratory infections, GI and abdominal infections, prostatitis, and also the infections of the bones, joints, and soft tissues. They are usually administered through oral administration, and their mechanism involves inhibiting the DNA guidase and topoisomerase. However, these three kinds of antibiotics that have been presented here, like TCH meaning tetracycline hydrochloride, NOR meaning norfloxacin, and IS meaning isoniazid, they have also certain kinds of adverse effects on our environment. See, TCH it reduces the protein synthesis, enhances the urea accumulation in the human body, can cause gout also. It also causes the irritant property like nausea, vomiting, and diarrhea, and also can cause the kidney and liver damage. Beyond that, the norfloxacin, which is usually used for the central nervous system, it can also cause tendonitis and tendon rupture in the adults taking corticosteroids, and it has effects on CNS like dizziness, headache, confusion, and seizures. Besides that, isoniazid, which is usually administered for liver damage, it can cause hepatotoxicity and peripheral neuropathy. So what are the pathways of the antibiotics? Besides the oral administration, they are also discharged into the environment through various routes. As I have discussed here, it can be discharged via the sewage, factory, expired antibiotics, pasture-reared animals, the aquaculture and integrated farming, and the livestock husbandry. So the health hazards which are associated with it includes the accumulation in living beings and imparts bioresistance. Now, what is bioresistance? Whenever a antibiotic is administered towards a specific pathogen, what happens is that if that antibiotic has a higher lifetime period, then that pathogen is totally consumed for a longer period of time, then it imparts a resistance within itself. So the researchers would have to create new vaccines with regard to that. So this bioresistance is a toxic problem which the researchers worldwide has created havoc within the researchers here. Now it is also included in the food chain and food web, as I have already discussed, that from a tiny cellular level it can get upgraded towards the tertiary consumers and finally the decomposers also. Then it could not be removed from the ecosystem easily. Now among all the remediation techniques, the oxidation, co-precipitation, adsorption, ion exchange, membrane filtration, photodegradation and coagulation, the photodegradation is considered as one of the most sustainable ways to impart this degradation of the antibiotics. Now why photocatalysis? As I have mentioned here in the blue section, you can see it is economically feasible, environmentally benign, and operates under mild temperature and pressure conditions. Although it has some drawbacks also, why we cannot use a single semiconductor photocatalyst for the degradation of the antibiotics, because it causes the inefficient utilization of the visible light. It can be difficulty in retrieval of the nano-sized particles and difficulty in distributing the particles uniformly. So what happens during the photocatalysis is that, as the name suggests, it means photocatalysis. Photo means it uses the sunlight. So what happens, whenever the light is irradiated upon a semiconductor photocatalyst, the electrons get transitioned from the valency band to the conduction band, leaving the holes. So if there is a poor recombination rate between that electron and the holes, so what happens will that the electrons will get converted to the superoxide radicals by reacting with atmospheric oxygen, whereas the holes will get converted into the hydroxyl radicals, and these radicals are the key reactive species in degrading the toxic organic pollutants present inside the environment. Now going to my sample fabrication, what we have actually prepared. First we have taken one of the precursors, GC3N4. We already know that GC3N4 is one of the most optimum photocatalyst present in the environment, and many researchers have already focused on it. But it has a band gap of 2.7 electron volt, but it is also, as I have already mentioned before, that it cannot be used singularly as a photocatalyst. So we have first prepared the precursors and then we have made the nanocomposite. So for making the precursors, we have taken for GC3N4, we have taken the melamine as one of its ingredients. Then we have put calcined it at 550 degrees Celsius for 2 hours at 5 degrees per minute ramp rate. Then we have prepared the GC3N4. For BO means alpha BI2O3, which is one of the most stable phases of BI2O3. We have taken bismuth nitrate, and then we have from addition of acid and base, we have finally made a white slurry and calcined it for 450 degrees Celsius at the ramp rate of 10 degrees Celsius per minute. For comparative purposes only, we have created our AGCN as well as our ABO. Finally, the nanocomposite, which has been, the fabrication has been mentioned below, we have taken all of the ingredients and we have ultrasonicated it for 2 hours, because from the early literature survey we have known that through ultrasonication what happens, that there is the exfoliation of the sheath of the GC3N4. So ultimately what will happen, the other ingredients will get infused between that exfoliated sheet, and maybe they can show an alteration in properties in its physical and chemical behavior. So we have finally, through using the ultrasonication, we have made a nanocomposite. Different amounts, weight percentages of BO were taken, like 5, 10, 15, 20, and ultimately 4 millimolar of AgNO3 was added, and finally our AbOG nanocomposite has been taken. So this is the fabricated samples, the GC3N4 and BO. We see that there is a slight contrast in color in our X weight percent AbOG. X means the amount of loading percentage of BO, and see that it has a high contrast in color. That means it is more visibly active. It's also reported in the previous studies. This is the monoclinic structure of the alpha BI2O3 upon which our Ag nanoparticles are deposited, and we have predicted that maybe oxygen vacancies could be generated in our samples. So due to the oxygen vacancy, we can see that the electrons are generated, which can be the 3 reactive species in our nanocomposite. So the characterization has also been done. So we have presented the XRD. This represents the XRD of both the precursors as well as all of the nanocomposites. And ultimately we see, as we are increasing the doping percentage of BO, there is broadening of the peak at 27.4 degrees, which indicates that ultimately it is interconnected. Means BO and GC3N4 are interconnected. Also the peaks requiring the Ag is also found at 3 separate positions. Now we could know that from the XRD whether the Ag is deposited on BO or the Ag is deposited on the GC3N4. To know that, we have done the XRD, and we found that in AGCN we have not found any kind of shifting in peaks. However, in case of the ABO, we found that there is slight shifting in peaks. I have note down one of them, 37.75 in case of BO, whereas in ABO it is 38. That means there is a slight shifting of peak, which denotes that yes, the Ag has been incorporated into the BO rather than GC3N4. Now we have predicted that to know that whether vacancies has been created or not, we have done the Williamson fault plot, so that the strain in the sample could be known. So from the Williamson fault plot, as represented in the D graph, is BO. It is a horizontal line representing that there is no strain induced inside the moiety, whereas in case of 15% AbOG, the straight line is formed with R square value of 0.9975, which indicates that yes, the microstrain has been generated inside our nanocomposite. Now this is the FGCM, EDS and elemental mapping of a primary nanocomposite, where BO shows a worm-like morphology, GC3N4 shows clearly sheet-like morphology, and we see that there is a porosity which is induced within the AbOG nanocomposite owing to the ultrasonication in the sample. Now the EDS and the elemental mapping shows that yes, all of our elements have been perfectly found inside our nanocomposite, 15% AbOG. Now HRTM images, we can see that here ultra small pores has been generated inside our AbOG nanocomposite, and the clear crystalline fringes are also obtained. The D11 value of 0.206 nanometers goes to the presence of the silver nanoparticles, whereas the D value of 0.316 goes to the formation of the alpha BI2O3 inside our nanocomposite. This clear distinct fringes can be observed here. The SAD pattern shows that it is slightly polycrystalline in nature. Now we have done the photoluminescence as well as the UV visible DRS. From the photoluminescence, we can know that whether the rate of recombination of the electrons and holes is maximum or minimum. And we know that if the photocatalyst has low rate of recombination in case of electrons and holes, then it poses boosting in photocatalytic behavior will happen. Clearly, we can see that as compared to GC3N4, BO and AGCN, all of our nanocomposite shows a lower intensity. That means there is lesser recombination of electrons and holes, and hence a boosted photocatalytic activity. Similarly, in case of the UV visible DRS, we can see that when we extrapolate, we will find that in case of our precursors, it will form, the wavelength is between 400 to 500. However, all of our nanocomposite has a redshift, hyperchromic redshift between 500 to 600, showing boosted photovoltaic activity. Now the band gap analysis and the fat band potentials were also evaluated, and from the fat band potentials we can see that it's showing the positive slope, indicating that N type of heterojunction might be present. Now we have also done the EIS plot, meaning impedance study. So from the EIS plot we see that a lower semicircular arc has been formed, which indicates that it has a greater photovoltaic behavior. To symbolize whether the oxygen vacancies has been generated or not, we have done the EPR study, and we can clearly see that in case of the EPR, we are getting a clear intense peak at G value of 2.003, which indicates that yes, oxygen vacancies has been generated inside that moiety. Now the BED surface area analysis and pore volume analysis also proves that there is induction of more surface area has been formed inside our APOG composite, and volume also increases. The space analysis proves the presence of the oxygen vacancies. As you can see, in the case of oxygen, we get a peak at around 530.2 electron volt, which is a clear indication of the surface adsorbed OH moieties as well as the oxygen vacancies present inside our moiety. Now, contact angle analysis was also done, which is the wettability test, which means that if the contact angle is less than 90 degrees, then it is hydrophilic in nature. So all of our nanocomposite clearly shows an decrease in contact angle, which shows the increase in hydrophilic behavior of our nanocomposites. The scavenger study was also done. That means which of the key species is acting as a role model for the photocatalytic activity. So parabenzoquinone was used to quench the superoxide radical. DMSO was used against our electrons. EDTA2Na+ was used against holes, and IPA means isopropanol was used against our hydroxyl moieties. So we can see that the most quenched one is the DMSO, which means that the electrons are the key active species which degrade the antibiotics. 3 antibiotics has been degraded here. TA test and NPT test are the proving points for whether the hydroxyl radical and superoxide radicals have been generated. And clearly we can see that there is an increase in the TA test. That means fluorous nature of the GA, and NPT, there is a decrease in intensity of the NPT, which means that yes, our hydroxyl and superoxide radicals has been generated properly. This is the UV degradation plots of the antibiotics, which shows that the first order kinetics has been followed in all of the cases. The 15 weight % ABOG composite was used, and in all of the cases we see the first row is for TCH, the second row is for NO1, and the third row is for IS2. These are the apparent rate constant, correlation coefficients, and the degradation efficiency values. Now we have also done the real-time analysis for all of them, and we have seen that in all of the cases whether there is a small depreciation in degradation efficiency, yet we can see that the 15 weight % ABOG shows the maximum degradation in comparison to GC3 and PO in all of the cases. Now apart from that, since silver is present in our nanocomposite, it is a pre-notion that yes, it can be used for antibacterial study. So we have tested it in the solution form as well as in the powder form, and we can see clearly that in 15 weight % ABOG, 0.05 gram of the sample deletes all of the bacteria that is present. E. coli bacteria has been taken, H5 alpha E. coli bacteria, and it retards all of this bacteria present in the sample. Finally, the mechanism is SE. And we have also done the reusability study. That means the XRD, FACM, and HRDM. After 4 catalytic cycles, our compound is found to be stable enough. So thank you for allowing me to present.
Okay, thank you, Prakash. One question only. No question. Thank you. Let us give a big hand.
Bhubaneswar Memorial Award in Environmental Science. Pragyansi Aprajita from NIT Raurkela, she has been given ₹3,000. Next session, it will be chaired by Professor Nigamananda Das. Professor Nigamananda Das is a retired professor from Department of Chemistry, Utkal University. Before joining Utkal University, he served as a lecturer, SK University, scientist at CSIR, National Meteorological Laboratory, Jamshedpur, and professor in chemistry at North Odisha University, Baripada, and Ravenshaw University, Cuttack. He joined Utkal University as a professor of chemistry in 2015 and continued till his superannuation recently, that is 30th November 2024. He has published 160 plus research articles in national national and international journals with 5500 plus citation, H index of 33, I-10 index of 62, besides publication of one book, several book chapters, one Indian patent. He has successfully guided 19 PhD students. He is also a recipient of Best PG Chemistry Teacher Award 2018 by Association of Chemistry Teachers, India. In 20 years of service at universities, he is also a pattern life member of many professional bodies and also fellow of Royal Society in Chemistry. Now I request Professor Das to please chair the session. And there is one announcement, those who have the posters, now they can put their poster and it will be evaluated after the talk will be over. And the oral presentation will be held simultaneously in 2 rooms. So the rooms are just, if you go out from the end door, in front of that there is a room. In that room, the oral presentation will be made. And those who are present here for oral presentation from 1 to 15, they can give their names to here, Rosaline Pradhan, Dr. Rosaline Pradhan. And from 16 to 31, after that we can conduct that. So please give your names, those who are present for oral presentation. Sir, continue.
Thank you, Professor Chidaranjan Acharya. And thank for giving me this chance to chair this session. And this session there are 2 lectures. One is invited speaker and the other one is one of my teachers, Professor Dinabandhu Bhatt Memorial Award. So first lecture will be invited one and it will be given by Dr. Piyush Mishra. Dr. Piyush Mishra is currently an assistant professor of Department of Chemistry at IIT Kharagpur. He has completed BS-MS dual degree at IJR Mohali and received PhD degree from Bode University, USA. He was a postdoctoral fellow at MIT, USA and University of Ottawa, Canada. Before joining IIT Kharagpur, he was an assistant professor at the Department of Chemistry and Chemical Biology at IIT Dhanbad. His research interest is studying chemical dynamics in gas phase using high resolution spectroscopy. This I request Dr. Mishra to deliver his talk.
Thank you, Professor Das, for a very nice introduction. And hello everyone, my name is Piyush Mishra. I recently joined the Department of Chemistry at IIT Kharagpur as an assistant professor just about 6 months back. The title of my talk is Probing Chemical Dynamics Using Broadband Rotation Spectroscopy. This is definitely off topic from the theme of this conference, so I apologize to the audience ahead of time. And I also very sincerely want to thank Professors Behera, Acharya, as well as Professor B.R. Das for giving me this wonderful opportunity to present my research, especially for a young up-and-coming researcher. It is important to spread the news about their group, and this does give me a very wonderful opportunity to say. All right. We work in the field of gas-phase chemical physics or gas-phase physical chemistry. I'm a trained high-resolution spectroscopist, so the panel on the left is essentially what I deal with. This is what I see on a regular basis. But I've always been interested in molecules in motion, so molecules performing a collision process or a reaction and trying to study that. So our essential idea is to connect spectroscopy with dynamics. And it is important to study these chemical as well as molecular processes in the gas phase Because in the gas phase, you are removing the surrounding effects, like environmental effects, solvent effects, and you can really peer into and really extract the quantum mechanical details of the molecular properties as well as the characteristics. And that's where our interest lies in. This is the electromagnetic spectrum. I'm sure everyone in the audience is familiar with it. Every molecule has a bunch of different excited electronic states. It can be singlet state, triplet state, dissociative potential, interesting dynamics like conical intersection going on and so on. Each and every one of these potential energy surfaces that you see over here is made up of 3n-6 vibrational modes, where n stands for the number of atoms in a molecule. So for a triatomic molecule, there are 3 modes. For a tetratomic molecule, there are 6 modes, and this number keeps very rapidly increasing. This makes these potential energy surfaces truly multidimensional in nature. Every single one of these 3n-6 modes have a bunch of different vibrational states that are built in. So this picture is already getting kind of complex. In high resolution spectroscopy, however, we go one step further. We look at the rotational states that are built off of these individual vibration levels, which can be further split due to tunneling, hyperfine splitting, and various interesting quantum mechanical effects. In order to study these very finer details of molecules in the gas phase, what we do is we perform short pulse molecular rotational resonance spectroscopy. This is a relatively new technique which was invented about 10 to 15 years back, and it does not exist in the eastern hemisphere of the world. This spectrum that you see over here corresponds to an astrochemically relevant molecule. This is a broadband technique. You see almost 10 gigahertz bandwidth over here. It is high resolution. The individual peaks that you see over here are actually split into multiplets due to tunneling and nuclear quadrupolar effects and all those interesting things. And it's also multiplexed. What it means is that the entire stretch has been recorded in just a single shot. The analytical capabilities of this instrument, of this relatively new technique, can be emphasized by focusing on the very wide classes of compounds or chemicals that it can distinguish, which includes isotopomers, isotopologues, structural and stereoisomers, conformers, as well as excited state populations. And it gives you all this information at the same time simultaneously because it is multiplexed. Alright, now the instrument that I had used during my PhD is kind of a bulky instrument, as you can see over here. The reason for that is because microwaves occupy a large volume. If you remember, when you heat up your food in your microwave oven, there are hot spots and cold spots. And if you're careful about measuring the distance between 2 subsequent hot or 2 subsequent cold spots, you'll find that it is about 5 centimeters. The reason is because 5 centimeters is the lambda by 2 value of the standing waves that are generated inside your oven. So this is just to give you a sense of how large of a volume these microwaves occupy. Corresponding the optics and all the instrumentation also becomes more and more bulkier. Alright, now although I can go on and on talking about its analytical capabilities, in today's talk I want to focus on the dynamical information that you can extract using this particular technique. So it is unconventional, but what we want to do is we want to study molecular vibrations using pure rotational spectroscopy. Typically, you must have heard of row vibration spectroscopy because people are trying to look at the rotational fine structures in a vibration spectrum. We are doing this the other way around. We are looking for the vibrational fingerprint or the vibration satellites in a pure rotational spectrum. The reason is because the spectral range is just about 0.1 wave numbers of the experiment, but the energy range that you can probe can be greater than 10,000 wave numbers. So highly excited vibration states can be probed. It's almost like the order of like 5 orders of magnitude different from each other. Monitoring vibrational populations is much better using rotational spectroscopy than using vibration spectroscopy. This point is counterintuitive, but if anyone is interested, I will emphasize or I'll explain this point in the question answer section. We are essentially trying to understand chemistry, like bond breaking and bond making chemistry in terms of vibrational mode excitation. We want to see during a process and right after a process how much of vibrational energy is stored in these isolated molecules, and then back calculate what must have happened in a reaction or in an energy transfer process. Now this profound idea was thought by my postdoc supervisor, Dr. Robert Field, and I was fortunate enough to apply this to like 4 to 5 systems. But I'll be talking about just a couple of systems in today's talk. So the first system is atom-molecule inelastic collisions. This is helpful not just in astrochemistry to understand star formations and so on, but also to understand greenhouse gases and how they trap energy and transfer its the vibrational energy to other gases, and also in combustion chemistry. So it has kind of widespread relevance. We started by choosing helium and started colliding helium with different kinds of molecules. We changed a whole bunch of experimental parameters, we looked at multiple vibrational modes, and the molecules are chosen across many different properties, as you can see over here. We must have done more than 120 unique experiments, all different from each other, and every single time we were only able to get one single result. The result is helium, when it comes and collides with a molecule and removes its vibrational energy, it does not care what the molecule is. It does not care if it's a bending mode, a stretching mode, or an in-plane or out of plane vibration. It just cares about what is the value of the frequency value of the vibration mode. If the frequency value is large, then energy transfer becomes much harder. If the frequency value is small, then the energy transfer becomes much more easy. This can be very nicely explained by a breathing sphere model. Over here you see a helium. When it is interacting with or coming and colliding with any molecule, all that a helium is seeing is a spherically symmetric object that is performing an isotropic vibration that does not have any directionality. And because of the simplicity of these experiments, it was kind of profound. We did not really anticipate helium collisions to be this easy and to show very universal behavior. Of course, helium may be relevant to astrochemistry, but when we talk about terrestrial chemistry, we started looking at hydrogen, neon, argon, nitrogen. We were able to extract some trends, this vibration energy transfer, which is more, which quenches much more efficiently, which quenches slightly less, and so on and so forth. I won't get into the details. I'll jump on to the second example, which I think is going to excite the audience a little more. We started looking at photodissociation of symmetric triazine, using the same setup, using the very same idea. Symmetric triazine can either dissociate via a concerted mechanism or a sequential mechanism, forming 3 HCl molecules. Now, although the HCl molecules are chemically identical, they can be dynamically different. What I mean is that the 3 HCl photofragments may be produced with different amounts of energy. One of them may be moving with a very high kinetic energy, the second one might be rotating at a very high energy, the third one may be vibrating with a different energy. So although they are chemically identical, they can be dynamically different, and that is what we wanted to see. Right? So in other words, we wanted to see if it goes via a symmetric 3-body dissociation, as you can see over here, or an asymmetric stepwise dissociation mechanism. Alright. We did our experiments, we hit triazine with our laser, and this is the pure rotational spectrum of the photofragments. You see the down state over here, this is the ground state signal, the S in bending progression is going towards the right, the C in stretching progression is going towards the left, and this is indeed high resolution because the individual transitions are split due to some nuclear effects. One thing to notice over here is that we did not see any excitation along the CH stretch mode, right? What that tells us is that an H atom migration is not a pathway. Of course, when you look at these structures, that is an unlikely outcome, but still it is nice to have experimental evidence that removes all those pathways. Among all these, the various calculated pathways, that helped us reject most of them and then arrive at just 2. The next one, CN stretching mode, right? We did see a little bit of excitation on the CN stretching mode. The bond order of CN for the 3 HCl moieties are 2 at the transition state. But when it forms hydrogen cyanide, the CN bond order is 3. So when the bond order is increasing, the bond distance is decreasing. because there's a change in the bond length, there was some excitation seen along the CN stretching mode. Whereas the bending mode, right, for the HCN, the three HCN moieties have different bond angles, and that showed up as like a bimodal distribution just along the bending mode. Now this is a little counterintuitive, so let me explain the same thing in a slightly different way. At the transition state, if there is an angle strain, the bending mode will be very active. If there is a change in bond angle between the transition state and your final geometry, the stretching mode will be active. If there is no bond order change, the stretching mode will be inactive. We have seen that for CN stretch, as well as for the HCN bending mode. So this helped us confirm the presence of the sequential dissociation pathway rather than the symmetric or the concerted dissociation pathway for this particular molecule. This is just a graphical abstract that shows that the three HCN molecules that are produced from the photodissociation of symmetric thiazine is bound with different amounts of energy. Alright, so this was what essentially what I did during my postdoc in the field group, and I'll be forever grateful to them for giving me a very enriching experience. The setup that I had built during my postdoc is here on the left hand side. The setup costs more than 5 crores. Of course, in India, building or getting that kind of seed grant is really hard. So what I'm planning to do is I'm planning to change some key components of the spectrometer and to reduce its cost by over like 2 times or so. So let's see if that's going to be possible. I'll be collaborating with Brian Hayes, who is a staff scientist at CNRS France. And this is something that is going to be kind of like a longer term project, like 3 to 5 year kind of a project. I have 4 project students in my group. Subhash is working on essentially solving the Schrodinger's equation for the breathing sphere model. So it's not a computational project, it's purely a theory project. So he's actually reading up on abstract mathematics textbooks. And it's very new to me, so both of us are kind of holding each other's hands and we are learning as we are going ahead. But he has made some really nice progress. Indramani is doing some engineering design. He is building an in situ laser ablation gas cell. What this will help us to do is we are essentially trying to build a device where you can monitor laser initiated processes, and you can make this cell compatible with any commercially available FTIR spectrometer and hopefully a UV vis or a fluorimeter in the near future. So he is working on that aspect. Manoj is working on he is working on computational astrochemistry, and Arya is working on computational atmospheric chemistry. So these are both computational projects. The first lab output is this urea detection, this urea adulteration detector. We made a kit out of it, and we just filed a patent about a couple of months back, so we are pretty excited about this. Of course, you see that there is a color change. It's a colorimetric test, so the obvious next steps are trying to do the photophysical characterization. Okay, I want to thank the audience for your attention. Before I close, I just want to mention that we are actively looking for interested students to pursue research in spectroscopy in the group. I don't have any PhD students yet, so I'm actively looking for PhD students. So if you can just help me spread the word, or if anyone is interested in spectroscopy, if you can let them know, they can contact me. That would be much appreciated. The projects exist across a very wide spectral region, from the electronic region, like in the electronic spectroscopy in the UV vis region, or the vibrational spectroscopy in the IR region, or rotational spectroscopy in the microwave and the millimeter wave regions. Thanks again for your attention, and I'll take any questions you have.
Thank you, Dr. Misra. And now one or two questions we can take because he has finished within time. One question and your issues. So if there is no question, let us thank Dr. Misra.
I request Dr. Subhash to felicitate Dr. Misra.
Any questions are available or not?
So we continue this session, and the next talk will be a memorial lecture, Professor Dinabandhu Bhatta Memorial Award, and this will be delivered by Ms. Nirmala Niharika Bhuyan from Sambalpur University, Sambalpur. So about Professor Dinabandhu Bhatta, he was my teacher at MSc from when I was a student at Utkal University, and then I did my PhD from Utkal University, so he was always there. And as long as I was there, if you do not find anyone, Bhatta sir will be there in the department from starting from 9:30 or onwards to till 12 p.m. So he will be there in the department. And whenever sometimes, say for example, I have forgotten my key to enter to the lab at 9 or 9:30, we just call him from the window. So he will be there always. So he is that kind of that. If I assess him that he was not a very good in teaching or other type, but he was a dedicated worker, and I have seen him working like anything. So that's why he has produced almost 39 PhD, I think 39 or 40 PhD in different fields, different areas. And he will always doing something writing or like that, he will be doing that. So he has a lot of dedication, particularly to his work, and which credited him also. And after retirement in 2004, I think, from University, he retired in 2004, and he joined in Naharkanta, one of the pharmaceutical institutions, and there he continued till 2015 or 2016, I think. And in 2018, April, he passed away in 2018. And with this brief introduction, I now invite the speaker, Nirmala Niharika Bhuyan, to deliver her talk.
Because same thing, I was also a student of Utkal University. He is always there, as Professor Das told, that he is always present in the department. And normally he doesn't ride any two-wheeler or four-wheeler, but he was present everywhere. If you go to market, he is there. If you go to anywhere, he is present. And moreover, besides chemistry student, he has good contact with the arts and other history, political science. All the students he knows, and those students also knew Professor Bhatt. But sir, se ete bhala bhare madhya jananti. So tankar joti kama tha se chali jai seiti pahunch jibe. Mu jetole se Naharkanta rahile setole mu register BP uthi. जहाँ कॉलेज काम पड़ो से 7टा बेले टुकटुक हेकरी संध्या 7टा रे आसी से आनी जानती जे 7टा पर मु प्रीति से सेतबे आसी तो ताकर काम अछि में से निश्चय से कामडा करे कि रहबे तो खाली से जे न्यूक्लियर केमिस्ट्री रेडिएशन केमिस्ट्री पढ़थले से कनो तापर मते फार्मास्यूटिकल केमिस्ट्री सेठी किछि काम करथले किंतु पॉलीमर को सब बोली से ही हैज टच्ड एवरी फील्ड ही हैज टच्ड या ताकर थिला माने कथा हो जे ही हैज डेडिकेशन. In spite of everything, he chemistry put it about affection till the end. He was there with chemistry. Thank you.
A very good afternoon to one and all present here. Respected sir and ma'am. I am Nirmala from Sambalpur University. First of all, I would like to
So today I am here to present my research work, and the topic of my presentation is an estimated humanine anthracene conjugate as efficient culinary acceptor for organic solar cell. During this presentation, I will take you through how the solar cell device works, what type of materials are used, and their advantages and challenges, and what type of material I have synthesized and how it influences the device performance. So let's start with the motivation behind developing organic solar cells. As we know, the world is facing an energy crisis. Therefore, there is a growing need for clean and renewable energy sources like solar power, which converts sunlight into electricity. Organic solar cells are photovoltaic cells which utilize organic semiconducting material as an active component. Unlike traditional silicon-based solar cell, which utilizes inorganic semiconducting material, organic solar cell utilizes organic molecules or polymers to generate electricity from the sunlight. So the device structure of organic solar cell consists of multiple layers, and each layer has their specific roles. The first layer is the transparent conductive electrode or anode, which is usually made up of indium tin oxide, and it allows the light to pass through to the active layer. And the second layer is the hole transport layer, which facilitates the transportation of the holes while blocking the electrons. And the third layer is the active layer, which is blend of donor and acceptor molecules. And this layer is responsible for the generation of excitons. And the fourth layer is the electron transport layer, which facilitate the transportation of the electrons while blocking the holes. And the fifth layer is the back electrode or cathode. It is usually made up of metals like aluminum, calcium, and silver. This layer collects the photogenerated electron and completes the external circuit. And these are the three different types of device structure of organic solar cell. But in this topic, we have used wall heterojunction architecture of organic solar cell. The working principle of organic solar cell involves several steps, and this is the graphical representation how the solar cell device works. So the first step is the photon absorption. When light falls on the donor material, it generates an exciton. The excitons are then migrated towards the donor and acceptor interface, where they can be dissociated. Once they dissociated into free charge carriers, the free charge carriers are collected at their respective electrode. So holes are collected at the anode and the electrons are collected at the cathode. The flow of electron and holes towards the electrode generate an electric current. So why we prefer organic solar cell? Organic solar cells are cheaper to produce as compared to the silicon-based solar cell, and the material and the manufacturing processes are less expensive. And the material used for organic solar cells are more environmentally friendly and can be produced by using less energy intensive methods. Organic solar cell can be flexible and lightweight, which allow them to be integrated into various surfaces like building facades and windows. Organic solar cell can be semi-transparent and can have adjustable colors, which make them suitable for aesthetic applications. Although organic solar cells have a variety of advantages, but they also face challenges that researchers are continuously working to address it. Several small molecule and polymer-based donor and acceptor materials have been synthesized and utilized in the development of organic solar cells. With the emergence of non-fullerene acceptors, donor molecules have shown excellent device performance and achieving power conversion efficiency is above 20%. This plot illustrates the year-wise progress of organic solar cell. It highlights how the incorporation of the non-fullerene acceptor boosted the power conversion efficiency above 20%. So in our lab, we usually synthesize humanine derivative because of its outstanding photophysical property, tunable energy levels, and excellent device stability. These are some previously reported coumarin-based donor molecules which have shown remarkable device performance and DHTPC above 15%. So researchers are now planning to design new type of donor acceptor-based coumarin-based molecule to enhance their performance. So, motivated by the remarkable performance of coumarin derivatives, this study focuses on replacement of aryl group with acyl moiety and to investigate how it influences the protophysical property and the device performance. So, in this study, we have used PTB7TS as the polymer donor and the DIC-TF and CSN as the fullerene-free acceptors. So this is the synthetic procedure of synthesis of CSCN. The compound C was reacted with, the compound C was synthesized by the reaction of salicylaldehyde and ethyl acetoacetate using piperidine as the catalyst under cooling at 0.5 degrees Celsius. Subsequently, the compound C was treated with malonyl in presence of ammonium acetate and acetic acid, gives rise to the product E. The condensation of product E with 9-anthranaldehyde gives rise to the product CSCN with a 70% yield. And the product was purified from column chromatography, and the structure was confirmed from the proton NMR and carbon 13 NMR study. And we are successful in growing single crystal structure of CSCN from the mixture of chloroform and ethanol. Single crystal structure analysis provides information about the molecular geometry and intermolecular stacking modes of organic molecules. And this is the single molecule view of CSCN. And the molecules are arranged in a zigzag manner with different type of non-covalent interaction. And this molecule show two type of pi-pi stacking arrangement in which the anthracene moiety of one molecule so exhibited pi-pi stacking with neighboring coumarin moiety at a pi-pi distance of 3.24 angstrom, and the anthracene moiety shows parallel displaced arrangement with at a pi-pi distance of 3.33 angstrom. We have carried out the thermal measurement by using differential scanning calorimetry and thermogravimetry analysis. In DSC, we determine the melting point of CSN, which is about 228 degrees Celsius, and TJ shows that the decomposition temperature of CSN is about 350 degrees Celsius, which indicate excellent thermal stability. The electron density distribution of frontier orbital of donor and acceptor molecules were calculated by density functional theory using D3LYP631G TP basic set. And this is the molecular electrostatic potential distribution of the donor and acceptor molecules. The molecular electrostatic potential distribution is an important factor in understanding the intermolecular interaction and electron density distribution of the donor and acceptor molecule, as it provides insight into how the molecule interacts with each other. So here we can see that the electronegative nitrogen, oxygen and chlorine group shows negative PSP, and the majority of the conjugated backbone shows positive PSP, and this is the electrostatic potential area distribution of the donor and acceptor molecules. This is the absorption and emission spectra of CSN in chloroform solution, and this is the absorption spectra for donor and acceptor molecule in thin film. We can see that compared to solution in thin film, redshift of absorption band and widening of the absorption band occurs, which is due to the molecular planarization and intermolecular interaction in the solid state. Then we have determined the HOMO and LUMO value by utilizing cyclic voltammetry. The HOMO and LUMO value was found to be slightly downshifted. This is because of the electron withdrawing dicyanomethyl group, and we have found that the molecules CSN have low lane LUMO energy level, which make it to be used as an electron acceptor. Then we have calculated the cost of CSN.
based on the reagent and solvent used during the synthesis and purification. And we have found that the molecule CaCl is very much cost effective with minimal number of synthetic steps as compared to the well-known acceptors. So these results suggest that by synthesizing less expensive materials with minimum number of synthetic steps can improve yield and also beneficial to achieve cost effective active material for organic solar cell. In order to determine the photovoltaic performance of CaCl, we have taken two binary blends and one ternary blends of donor and acceptor molecule, and this is the device architecture. We have plotted current density versus voltage curve from which we determine the solar cell parameters such as short circuit current JSC, open circuit voltage VOC and the field factor value. By using the power conversion efficiency formula, we have calculated the power conversion efficiency. We have found that the ternary blend shows higher power conversion efficiency of 14.91% as compared to its binary counterparts. And this is the external quantum efficiency spectra of optimized OSC, in which we can see that the binary blend of PTB7TH and DICTF shows poor photo response below 500 nanometer. This is because of its lower JSC value, and the integrated JSC value obtained from the equispectra is well matched with the JSC value obtained from the JP. So why the value of ternary blend is higher as compared to the binary blend? To know that, we further extended our experiment and measured time measured photoluminescence spectroscopy of the donor acceptor blends, which gives information about efficient exciton dissociation at the interface. So compared to the pristine CaCl, the other two blends shows lower PL decay time, which indicate efficient exciton dissociation at the interface. And we have measured tangent photocurrent and tangent photovoltage measurement to know the charge extraction time and charge carrier lifetime. So here we observe that the ternary blend shows lower charge extraction time, which indicate strong ability of charge extraction. And in tangent photovoltage curve, we observe that the ternary blend shows higher charge carrier lifetime, which indicates suppression of charge recomposition, which will influence the solar cell parameter as well as the power conversion efficiency. So in conclusion, we have synthesized a new wide bandgap dicyanomethyl substituted fumarine anthracene diet, which has low laying LUMO energy level, which make the molecule to be used as an electron acceptor. And the molecule CaCl, when used as an acceptor with PTB7TH, it delivered an excellent PC of 11.47%. By incorporation of 28% of CaCl in a binary blend of PTB7TH and DICTF, it gives improved PC of 14.91%. So this PC value is among the best achieved for the wide bandgap fluorine-free acceptor. And this study indicates new direction for the development of wide bandgap fluorine-free acceptor and their potential applications in organic solar cell. So I would like to thank my research supervisor, Dr. Amresh Mishra, for his constant support and guidance. And I am thankful to my labmates for their help and cooperation. And I thanks to Professor G.D. Sanmutar from NIT Jaipur for device fabrication study, and Dr. Chandrasekhar Pure, Nigel Bhubaneswar for single crystal structure extractive analysis. And I thanks to the funding Science and Technology Department of Orissa for financial support. Thank you.
Thank you, Ms. Priya, for your nice talk. And any question?
One reaction that you have taken marrow nitride to react with an alpha beta unsaturated ketone. The ketone reactivity is very less, and two in the keto group each conjugation with two double bonds. So site is there. Synthesis. malonacous E structure. So how you are, how do you rule out the formation of microadaptation? Adult because that you in basic medium you are doing, obviously. Yes. So ammonium acetate you have.
Sir, ammonium acetate is also there, acetic acid also there.
No. I think I said. I'm sorry. See red color.
Yes,
Again. Red color. CN. Okay. So keto group is there. So why do you rule out the microadapt is there? Because it will attack your beta position.
Why Michael Edison doesn't go? That is the question.
No. Red color structure. Last. Okay. Yes. So Michael has a beta position. That carbon. Yes, this position. That is also this my carbonyl function is in conjugation with two double bonds. In a coumarin double bond, another is there. Alpha beta such a ketone. So two double bonds are there.
Fundamental question. And it is always asked in this project. When the project is funded, I think this is the project funded to your guide, summary specific.
Sir, this carbonyl.
Now first listen to the question. It's a very fundamental question. You see in coumarin you have a carbonyl group attached to oxygen.
Yes.
Right?
Yes.
And you look at the other carbonyl, starting material C. That is also alpha beta double bond, keto. So why Michael Edison doesn't go? That is first part of the question. Second is why the methyl group gets functionalized. See, answer is very simple. Look at structure C.
Yes, sir.
The carbonyl character is not there. See, third line is C.
Yes, sir.
But see, carbonyl character, oxygen lone pair conjugates there, aromaticity is created. So carbonyl group character is lost.
Yes, sir.
That is the answer.
Yes.
Carbonyl group character is lost because the ring becomes aromatic. So A and B both ring aromatic, and the outside ketone gets functionalized.
Yes.
That's the answer.
Okay. Thank you. There is no more question. Then let us thank.
Now I request Professor Das to felicitate Nirmala Nyarika. Professor Dinabandhu Bhatt Memorial Award. It is given to Miss Nirmala Nyarika Bhuya with a cash amount of rupees 5,000. Thank you, Professor Das. So next, I request Professor Sarat Chandra Das to chair the next session. Professor Sarat Chandra Das is the former president of Orissa Chemical Society. Professor Das joined as lecturer in chemistry at Bhubaneswar Mahavidyalaya, Banpur. Subsequently worked at various colleges at Kendrapada College, DAB College, Titlagod, SBM College, Jagatsinghpur, Salipur College, Bhubaneswar Science College, Atgod. After completion of his masters, Professor Das was awarded PhD from Utkal University. All over the world, years working as lecturer or leader in chemistry. He completed 4 research projects and could set up an independent research lab at Salipur College, Salipur. 10 scholars have been awarded PhD degree under his guidance from Utkal University and published 52 number of research papers. After retirement from professional career in 2013, he is actively engaged still in academics by running an English medium school in his village and looking after the research activities at Institute of Pharmacy and Technology, Salipur. Sir, please. We have 2 talks.
Overall, give one sentence about me. Probably, I am a person who loves chemistry very much.
Thank you, sir. One talk is Professor Bimbadar Naik Memorial Award. It will be delivered by Samir Kumar Naik. And next talk, it will be delivered by a little bit pre-poned. The talk will be delivered by Professor Vishnu Kumar Patel. Second talk will be delivered by Professor Vishnu.
Kumar Naik, working under the supervision of Dr. Chaitanya Sharma Amidal.
I'm sorry to interrupt. I would like to introduce this house. Professor Bimbadar Naik. Professor Bimbadar Naik was first class passed in BSc, first class passed in MSc from Ravenshaw College, and he did his PhD from University of London way back when there were no airplanes. He traveled all the way from Calcutta by sea with Professor Bantam, his guide, Professor Bantam. He came back, became a faculty in Ravenshaw College, and then subsequently moved to IIT Kharagpur, and he was there as a professor, became head of the department, and he is very famously known as a physical chemist. And I had the opportunity of being associated with his family because my brother-in-law was his younger brother. In that context, I used to visit IIT Kharagpur and stay in his P49, quarter number P49 IIT campus for several weeks on my research quest. So Professor Naik is very famous in one thing. When in his bedroom, he used to keep physical chemistry by class 2. That book is always by his bedside. Very famous physical chemist. His son has instituted this award prize, and hopefully the family members have been informed.
Yes.
So, I've been informed. So, with these words, I introduce Professor Naik to the audience. Thank you.
Thank you for this kind introduction and for giving me a chance to deliver the talk. So,
Samir Naik. So your timing is?
20. So the title of my talk is Integrated Strategies for the Degradation of Foreign Polyfluoroalkyl Substances, basically predicting the accurate bond dissociation energy and exploring different metallic nanoparticles, that means plasma and degradation of the substances. First, I will give a brief introduction about the foreign polyfluoroalkyl substances. Then I will shed some light about the different approaches, which is connectivity based approach and molecular tailoring approach. Then I will explain about the prediction of different thermodynamic properties. Then I will finally explain the plasma induced degradation of the papers, and I will conclude my talk with some future predictions. So before going to the question what are PFAS compounds, all of us know that hydrocarbons are basically consist of carbon hydrogen atoms. So once we replace all the carbon hydrogen bonds, the compound is called as foreign polyfluoro substances or the PFAS substances. The majority part of the PFAS substances are carbon fluorine bonds. As all of you know that the strength of carbon bond is beyond that is carbon hydrogen bond, and the carbon fluorine bond is the strongest bond. So due to the presence of these carbon fluorine bonds, these substances are extremely chemically as well as thermodynamically stable, as well as due to low surface tension, they are hydrophobic as well as lipophobic in nature. So due to exceptional thermal stability, both water and oil repellent nature, they are used in various industries as well as household appliances, including non-stick cookware, firefighting foams, fast food packaging, etc. And as I have already mentioned, these substances are anthropogenic in nature. That means we have created these substances. So biological enzymes do not at all evolve to degrade these substances. So these substances accumulated in different organisms, including human beings, and their accumulation can lead to different diseases, including kidney cancer, liver damage, etc. As one of my colleagues already explained about this forever chemical, that means their stability, due to their stability, it is very difficult to degrade these substances. And they can migrate from one place to another place, like air to water to soil. So majorly from air, water and diet, they can enter to anyone's body and can start accumulating. So this is a quite old study which suggests that these substances are present almost everywhere in all the states of the United States of America. And due to their toxic nature, the United States Environmental Protection Agency has set a limit of 4 nanogram per liter intake limit per day. So but you can see that in the latest study, in Tamil Nadu suggests that their presence in the different water sources in Tamil Nadu is more than 100 nanogram per liter. So there is a latest study by IIT Madras which suggests that their presence is more than 160 nanogram per liter, which is much more beyond the permitted level. So by looking at the toxicity effect of these substances, it is important to degrade these substances. But the thermal and chemical stability of these substances pose a challenge for the degradation. So in order to address these effects of PFAS substances, we need to degrade the substances. So to degrade these substances, it is important to find out the accurate thermochemical as well as chemical properties of the substance. So in today's talk, I will basically talking about the two different aspects. One is the prediction of thermodynamic properties. Another one is the degradation of these substances by exploring different nanoplasmonic and metal sources. So in quantum chemistry, there are different methods like G4 or CCSTT, which can be used to predict the thermodynamic properties or chemical properties accurately. But their computational cost is so high that we cannot implement these methods to predict the thermodynamic properties of all substances. The DFT can be an affordable method of choice, but the errors associated with DFT is very high. Sometimes it can go beyond 25 kilocalorie per mole. In my earlier slides, I have mentioned that the bond strength between carbon fluorine, carbon hydrogen is approximately 20 kilocalorie per mole. That means the bond strength which we will predict for carbon-carbon bond can go for the carbon fluorine bond. And sometimes the reaction we will be predicting endothermic can be lead to an exothermic reaction. At the same time, so the question today I am going to address whether we can predict these thermodynamic properties accurately but at an affordable computational cost. So the answer is yes, there are different fragmentation based methods like molecular tailoring approach or connectivity based hierarchy schemes. So here what we normally do, we calculate basically we capture the higher level G4 or CCSTT level of correlation energy by the fragmentation scheme, and we add this correlation energy to the low level energy we reach at the high level G4 or CCSTT energy. So then how to fragment the molecule? Should we fragment it randomly or there is a systematic way of fragmentation? The answer is atoms or molecules, since molecule is made up of atoms and bonds, so the fragmentation scheme can be atom or bond centric in nature. That means we can extract the atoms or the bonds, or an atom with its immediate connectivity, a bond with its immediate connectivity, so on and so forth. And the name is basically CBH0, which is only atom. The bond is CBH1, atom and its immediate connectivity is CBH2, so on. also. So basically in this study, I will be explaining about CBH3 scheme. CBH3 means here we will be extracting all the heavy atomic bonds. Suppose in this case there are carbon-carbon, fluorine and two different types of carbon-oxygen bonds. If we are considering suppose this bond, carbon-carbon bond, the immediate connectivity will be this carbon with fluorine atom, carbon with fluorine atom and carbon. And by adding appropriate number of hydrogen atoms, the fragment will be CH3, CF2, CH3. And for all other bonds, the fragment will be like this. So but the problem is, if we are considering suppose this one and this one, there will be the intersection. That means one atom will be overcounted. One atom with its immediate connectivity. But interestingly, it will be the fragment for this one, the overcounted fragment will be same as this one. That means in the reactant side, we have to add the fragment for the CBH2 scheme if we are designing a CBH3 scheme. But why there was essence to further modify the scheme? The essence are, here we are dealing with the perfluoroalkyl substances. For all or most of the carbon-hydrogen bonds are basically replaced by carbon-fluorine bonds. So the wave function we are writing for this fragment, mirror mandate match for the original molecule. So what we thought of? We thought to satisfy the valencies of these unsatisfied fragments by adding chlorine atom instead of the hydrogen atoms. So the fragments, now this, instead of this fragment, instead of this fragment, the fragment generated will be this one. So this is a larger part of the original molecule. So the wave function will be writing, will be better match with the wave function we are writing for the original molecule. So for this project, what we have used the Gaussian zero-line program with 5 different varieties of density functional theory with one moderate size basis set. For this study, we have considered two different class of PFAS substances. One is perfluorocarboxylic acid and perfluorosulfonic acid, and from each class we have considered 5 different representative PFAS molecules. So before going to the result section, as all of us know that ground state free energy basically is the major component on which the thermodynamic properties and kinetic properties depends on. So the accuracy of this thermodynamic and kinetic properties depends directly on the accuracy of this ground state free energy. So first we have predicted the ground state free energies using CBH3 and MCBH3 and absolute G4 level. So we have compared that CBH3 and MCBH3 predicted ground state free energy with G4 predicted ground state free energy. We found that once we are using this MCBH3, the mean absolute deviation is well within 2 kilocalorie per mole except the PV functional. But for this CBH3 one, it is slightly higher than the MCBH3 predicted ground state free energy. So further, to establish the accuracy of the CBH3 and MCBH3 scheme for the predicting bond dissociation energy, so we predicted the bond dissociation energy of all the carbon-fluorine bonds of perfluorobutanic acid. Here we have calculated using 4 different acid functionals with CBH3 MCBH3 scheme in conjunction with G4 method, and we compared that one with absolute G4 one. So here you can see the DFT can deviate up to 10 kilocalorie per mole. But once we use either CBH or MCBH in conjunction with the G4 level with same density functional theory, so the deviation is more or less within 1 kilocalorie per mole except with density function. So inspired, motivated by this inspiring result, we predicted the bond dissociation energy of 46 carbon-carbon-carbon-fluorine bond. We benchmarked against the G4 bond dissociation energy. Here you can see that the bond dissociation energy is well within 1 kilocalorie per mole. So next, in the next project, what we are doing, we have predicted the bond dissociation energy of thousands of PFAS using CBH3, MCBH3, along with various different rounds of this CBH and MCBH. So conclusion till here is the MCBH3, either MCBH3, MCBH, CBH3 can predict the bond dissociation energy, which is very close to the G4 level. And interestingly, the lower round of MCBH, which is MCBH3, results are better than CBH3 results. So we are not only dealing with the prediction of thermodynamic properties, we are also exploring different metals and nanoparticles to degrade these PFAS substances. So here basically we are using plasmon induced degradation of the PFAS. So first I will explain what are the plasmons. Plasmons are basically quantized, collective and coherent oscillation of conducting electrons. So these plasmons can be used to drive the reaction. In this case, the breaking of this carbon-fluorine bonds. So for this study, we have used the JIPA of software package along with real-time, time-dependent method. So here, suppose we are shining a light. So the perturbation in terms of this light can be recorded as photoabsorption spectrum. In this case, this orange line belongs to the photoabsorption spectrum of Ag147. Further, the violet line is for Ag147PA4 and the green line is for perfluorooctanoic acid alone. Here you can see that perfluorooctanoic acid do not show much absorption throughout this one. So, but the absorption between this Ag147 and the heterostructure, there is a very minute change. We suggest that the PFOA is freezes up on this metallic nanoparticle. So generally, the experimentalist can assign that this peak is a plasmonic peak. But how do we ensure that this peak is indeed a plasmonic peak? So for that, what we have done, we have plotted this induced charge density plot. Here you can see that there is clearly accumulation as well as depletion of the electron density. We suggest that the electrons are collectively oscillating. So, but if you consider this PFOA, in case of PFOA, this type of structure is absent. That means that this is a single particle in nature. For this peak, what we have done, we have calculated all the excitations responsible for this peak. So, like HOMO to LUMO, HOMO minus 1 to LUMO plus 1. Here you can see that this black line is basically a resonance line. Below this resonance line, there is a collective oscillation of electrons can be shown. Basically, the intense peak one below this one further strengthens the presence of plasma in the system. Now, in the next one, what we did, we signed a laser of strength 0.514 millivolt per angstrom. Here you can see that before the start of this laser, there was no dipole moment in the system. But once the laser was tuned to the system, there was a change in the dipole moment, which suggests that this laser basically has induced the dipole moment in the system. Here in this case, like once you tune the laser, it pumped some energy to the molecule and the energy is stored in the excited state. Like here you can clearly see the energy steadily increased up to the laser was there. Once the laser decayed, there was no further change in the total energy. And this total energy further can be split into non-resonant as well as resonant energy. You can see initially there was a high growth in this non-resonant, basically the plasmonic energy. But as time proceeds, these plasmons converted to the single particle which is resonant energy basically, and this single particle or hot electron hot holes can drive the degradation of these previous substances. Further, we will consider three different spots, like here this point, at the neutral point, at the different phase. You can see that the phase basically of the electron is changing. That means the electrons are oscillating in this manner, and at this point there is no depletion or accumulation of these charges. Further, here also you can see that initially there was the major contribution from this non-resonant energy, and as time proceeds, the contribution was from resonance energy. This can be further established from this TCM plot. Like in this case, you can see that the plasmon are there at earlier time step, which is at 11.3 femtosecond. But at a later time step, basically at 26.68 femtosecond, all the plasmons converted into hot electrons or hot holes. Whereas the hot electrons are majorly concentrated over the PFOA molecule, whereas hot holes are concentrated over this silver 147 nanoparticle. We suggest that basically the hot electron is transferring from the Ag147 to the PFOA molecule, which help in the degradation of these substances. So to show that one, so we have performed this Ehrenfest dynamic, which shows that these substances can be degraded at 90 femtosecond. So I can conclude this topic like first we have established the plasmonic nature of the in the Ag147 PFOA system. The later we have established the plasma formation and hot carrier generation. Further I have explained about the spatial and energetic distribution of these hot carriers. Finally, we have already shown that the PFAS can be degraded at a time span of 90 femtoseconds. So these are some ongoing works. So I would like to acknowledge my research supervisor, my lab mates, and this PMR for the funding agency, and for computational researches HPC and ground. Thank you all for listening.
Thank you, Samir. I would like to invite one question or half question. Basically, people who have more interest in this topic.
If there is any question, I would like.
These compounds, as you said, are greatly not degradable.
Yes.
In real world, they are never degradable. Forever. Now, this computational work that you do,
Yes, sir.
from that, what you suggest, how could we degrade these compounds in real world?
Yes, sir. That's what we are exploring different nanoparticles. Whether like silver 147, whether this nano, like earlier maybe some lady pregnancy, she told that photocatalysis can be used to degrade the substances. So in this work, we are exploring different photocatalytic active metals, basically the plasmon active metals, whether the plasmons can be used to degrade the substances. The name forever is given due to the strength of the substance, but that doesn't mean that it can be degraded ever. It can be degraded. We have to explore different metal or metallic nanoparticles. That's what we are doing.
Now I request Professor Das to felicitate Mr. Naik, and he will be given Professor Bimbadar Naik Memorial Award with a cash prize of rupees 5,000.
ऑफ कर दे बैनरटा बंद हो आजिकल मैं सब गुड़ाक आजिकल से एत हाइट लाइट हो
This award carries a cash prize of 5,000 rupees. Mandra, our guru, yes, our guru, founder, go through it. Lot of research here.
Actually, for them to
Thank you. Now the last it's my pleasure to announce the name of a very prominent and prolific person of chemistry. Professor Bhubaneswar Patel needs no introduction in this audience. I think any student of chemistry or any persons of chemistry knows very well, he is very acquainted with the Chemical Society of Orissa, Chemistry Fraternity of Orissa, and this is all about Orissa. Overall, a very big personality in our national sphere also. We are really proud of him. Professor Bhubaneswar Patel is currently a professor of chemistry in the Department of Chemistry, IIT Guwahati. He completed his master's from Sambalpur University and received his PhD from the Department of Chemistry, IIT Kanpur. His current research activities involve carbon-hydrogen activations, that is metal and metal-free, tandem and cascade catalyst synthesis, organic reactions mechanisms, heterocycle synthesis, organo and organometallic catalysis, theoretical investigation on selectivity in organic reactions, green chemistry, organic tribromide mediated organic synthesis, metal catalyzed oxidative transformations, hypervalent iodine
mediated organic transformations. He has authored more than 230 research articles, reviews, and book chapters with above 8,000 citations. Congratulations, Professor Patel. And high index of 53, H index. He also has 3 patents in his name. He is one of the members of editorial board of Tetrahedron and Tetrahedron Letters, and associate editor in Journal of Chemical Sciences. It's a very brief introduction about Professor Patel, and now we'll love to listen to him for next how many minutes?
I'll take about 22 minutes.
Thank you.
Okay, because thank you Orissa Chemical Society for inviting me and adjusting me in this short notice, because my talk was originally due tomorrow. Okay, so thank you for giving me this thing opportunity. So I just sorry not to see many students around this thing, but that's what happens at the end of the day. Okay. So I'll be talking about the non-template synthesis. So I'll tell you the basic little introduction and I'll skip through the slide. Okay. So many of the heterocyclic molecules, when you do particular fuse heterocyclic, you make one of the heterocyclic over the another one. So that's called the templated synthesis. One existing template, heterocyclic make another one. So there are so many examples are there, but there are not many non-templated synthesis are there. That's why I'll be talking about some of the non-templated synthesis from our group. So today's already introduction has been given on the heterocyclic chemistry, so I'm not going to spend much time on this thing because there are 2 good lectures in the morning. Because beauty of this nitrile functionality is that it has a pi coordinating ability, it is electrophilic in nature, it is nucleophilic in nature, it can convert the multitudes of other organic functionalities starting from the nitrile group. It can reduce it, you can make it the amine, you can convert the ketone, you can convert the acid by selectively reacting with various kind of reagents, and some of these are given here. So our group has been contributing to the nitrile last 7-8 years, and we have already done 2 interesting review articles. Those who are interested, you can go through this thing. So there are 2 review articles from our group. So these are 3 nitrile molecules, dinitrile molecules that we work on this thing, right? In the potato, like organic chemistry, what did they do? You can make a multitude of molecules from a single starting material. Like in the potato, you can make so many items, right? You can make samosa, you can make aloo chips, you can make like this thing. So we also do the same molecule. You can see I show the how we can play around and make a beautiful organic molecules, which is likely to have many applications. Okay, some of the molecules you have seen in the little while ago, that kind of dinitrile compound. So these are 3 nitrile compounds that we are working this thing, and this can be easily synthesized in any laboratory in the India. Okay, they are not very difficult starting material. The first work I am going to tell you, this is the gamma keto dinitrile. So this nitrile, what you do? In the presence of copper acetate, you selectively hydrolyze one of these things, partially to the amide group, and that's become amide, get intramolecular attack, and they can convert this one. In this thing, you can see there are NHCH are there, so they are suitably placed for the annulation reaction to react with the alkyne in the presence of lithium catalyst, and you can make a polycyclic aromatic heterocyclic compound. So we call it a fused isoquinoline molecule. So this molecule has many material applications, but we are looking mostly to a synthetic point of view. And also we have done the extensive mechanistic investigation, but I have not spent much time on this work. And you can see the red bonds, particularly the red bond on the right product. These are the number of bonds that is formed in a single state. Okay, you can see the carbon-carbon single bond, carbon-oxygen double bond, 2 kind of carbon-nitrogen bond, and 2 kind of carbon-carbon double bonds are forming. So this is a real cascade process where you can make a multitude of bonds in a one process. So this is the mechanism of this reaction. It forms a selective hydrolyzed amide, dehydrated hydrogen cyclation, and these are the various kind of metal catalyst, standard metal catalyst reaction, and we exclusively investigate this mechanism. So now coming back to the one of the beta keto dinitrile, where earlier one of the nitrile was participating, other nitrile was remaining intact. In this case, both the nitrile are participating in a different. One is participating in intramolecular cyclation, other is participating in intermolecular cyclation, and giving me 2 kind of fused molecules. Okay, one is the furan, another the pyridine. So you are making a furopyridine, again in non-templated synthesis. No template is involved in this thing. You are making a furopyridine, and you can see the number of bonds that is forming. The red ones are on the new bond that is formed. Carbon-carbon single bond, carbon-carbon double bond, carbon-nitrogen single bond, carbon-nitrogen double bond, and carbon-oxygen single bond. And you can make the fused heterocyclic in excellent kits. And also did a lot of further modifications because organic chemists will play around this molecule and create a library of the molecules. So if you look at the synthetic strategy that exists in the literature, is the furan on the pyridine. pyridine is already built. You can see all the pyridine rings are built, and on that they make a furan. So these are the all templated synthesis. Or second approach is the pyridine on furan. Already pre-existing furans are there. On that you build the pyridine. So these are the templated synthesis. But however, there are few other miscellaneous strategies are there where both the things are constructed simultaneously. But look at the complexity of the starting metal that is being used this one. Okay, there is couple of more examples are there where you can see the complexity of this molecule. But in our case, you use a simple starting material where you can build both the heterocycle simultaneously in a one-part process by non-templated synthesis. This is the optimized reaction condition where you use the palladium acetate 10 more percent, phenanthrene as the ligand, and paratoluene sulfonic acid in dichloroethane gives 72%. So I am not showing the library of the compound that has been synthesized. These are few of the selected examples. It works with the symmetrical alkynes. These green ones are coming from the alkynes. It works with the terminal alkyne. But due to the some of the electronic factor, some of the alkynes are not successful. We have also provided appropriate explanation in our publications. Okay. So this mechanism is what is happening here. This palladium is not involved in the first step of the reaction. It undergoing a simple acid catalyzed reaction to form a furan ring. So this is also well documented. Furan ring is there. On the other hand, this palladium binds to the phenanthrene ligand. At that, it undergoing coordination with the palladium. Then alkyne insertion, the nitrogen. Then undergoing carbonmetallation. Then paratoluene sulfate photodemetallations is taking place. And then ligand exchange, and that's what you get the product. So you can make the furan this kind of compound. So beauty of this molecule is you can play a further player on this molecule. There is a hydrogen is lying over there. So you can do a alkylation reaction, CH activation reaction. You can make this molecule, or you can also do the alkyne insertion. So there is a CH and alkyne insertion. So you can make a again like this highly fluorescent molecule, water soluble. So you can play around with the various kind of bioimaging. Also, you can carry out the further reaction, like you can carry out the Heck coupling, you can carry out the Sunagashira coupling, you can carry also the Suzuki kind of coupling. Another interesting aspect of this, again coming back to the gamma dinitrate, here again both the things, one is participating, other not participating. Sometimes one participate, other don't participate. In this example, what you are able to do, you are able to make a fuse imidazopyridine in the one part process, where you are taking an orthohydroaniline, so it is forming the C base undergoing intramolecular cyclations, and they are undergoing copper mediated Ullmann kind of coupling reaction, and you are able to make a fuse heterocycles in excellent yields. Okay. Here also you can see all the red bonds. Okay. The red bonds are the new bond that has been generated with the okay. So you can there is formation carbon-carbon, double bond, nitrogen, carbon-nitrogen, single bond. These are the various kind of other photophysical properties that we have investigated with the selected compounds. Okay. So if you look the literature method of making these compounds, they are all templated synthesis. On the one of the existing heterocycle, it has been constructed, but our method involves a non-templated heterocyclic synthesis. Okay. So I will not spend much time on the mechanism, so I will spend a little bit here. Okay. So what is happening here? This amine react with the carbonyl component from the imine, and this undergoing intramolecular cyclation, which is assisted by the copper acetate. Okay, and then it is forming the fast heterocyclic. So it is intramolecular cyclation. Second is the typical Ullmann cyclation involved in the copper catalyst and form this compound. Okay. So we also work on this compound triggering this reaction with the photocatalyzed reaction, because our interest in the photocatalyzed reaction, we are using palladium acetate and the bipyridine system, where you can make either a cyanopyridine or cyanopyrrole derivative in a under photocatalytic condition at room temperature. No heating is required in this condition. Subsequently, also we did a eosine mediated which act as the photocatalyst in this case, where you trigger the reaction using a thiol, and you can make the thiopyrrole derivatives in proteins. So these are the solvent which activates the human being, right? So various places people are familiar with this thing. So it will activate in a different. So many of the molecules they love different kind of solvent. We have this interesting long review article where you can see the solvent dictated organic transformation. Same reaction, change the organic solvent, product changes completely. Okay, so we have written a completing some of our own work where these two reacting partners, this dinitrile compound in boronic acid, same palladium catalyst, same photocondition, one using the ethanol, gives exclusive the cyanopyridine compound. When you use the tetrafluoroethanol, same as tetrafluoroethanol is there, but it is fluorinated ethanol. The previous speaker just talked about the fluorinated compound. It gives the exclusively jet selective this one jet selective quinoline, okay, cyanoquinoline kind of derivative. So here you get the exclusive jet selectivity. There is small amount of the E selectivity there. So this ethanol process tetrafluoroethanol. So this is the how the mechanism change. So I am telling the key step of this reaction. I am not telling you all this thing because this tetrafluoroethanol there's acoustic interaction there and this stabilizes this transition state and that's what you get the basically the this product. But normally one would expect a cis product, but we don't know what is the driving force this thing. If you look at these two products, they are differing in the energy by just only 1 kilocalorie per mole, and we are getting the cis product exclusively. So the measure of this product, but we check many of the literature. They also say undergoing photodiazomerization, all the good Anguante science kind of things. So we don't have a reasonable explanation why you are getting the cis product as the major product. Okay. So this is the ethanol mediated reaction, but this is going by this kind of intramolecular cycle, carbopalindation is stabilizing. So this is how these two solvents stabilizing the intermediate and changing the reactivity of this thing and giving two product differently. So having this molecule, this kind of molecule, so again we played around this thing. Again we did the annihilation reaction to constitute this polyfuse heterocyclic. Okay, then you can also selectively hydrolyze this nitrile to the amide group, or you can also react to the boronic acid to convert the keto compound. Similarly, playing with the other molecules, this is the other molecule, other derivative, we got this thing. So we wanted to do the epoxidation of this one. So rather than getting the epoxidation, we did the only effective way, we tried this thing. Rather than achieving the epoxidation, we got the N-oxide formations. So you can try the other epoxidized agent, it might work, but that's what we got. When you did the sodium hydrolysis, you wanted to hydrolyze selectively, base hydrolysis, so you got this cyclase product. When you did the other kind of ketonization reaction, you got another interesting product, this thing. Okay, so you got an excellent crystal structure for this thing. So coming back to the light mediated reactions, because these two compounds, because this is EDA based complex. So for the students, those who are watching the mobile phone, the last line, students, those who are watching the mobile line, this thing for your information, like EDA based complex, but two compounds are not absorbing, right? Both are not absorbing in the visible region. But when you add A with B, then they form an EDA complex. The electron transfer takes place and they're so color compound. Okay, so they are capable of doing photochemical reaction. So when you react this compound in the presence of fire, no metal catalyst, no photocatalyst, triethylene irradiate with the photokine, and you get this product in the excellent. That's what you see this thing. Both are colorless compound, but when you mix both of them in the presence of triethylene, you get a yellow compound. And you see this just goes to the visible region around 380 nanometer. Okay, so you could make this compound without any catalyst, and you can. It is a very interesting class of the molecule. This mechanism of this reaction is the triethylene forming from thiolate. It forms a EDA complex with this polyalkylated species, and then in the presence of light, it activates this thing. In the presence of air, it will form the singlet oxygen, and it forms the thiol radical. The thiol radical trigger this thing, and forming a nitrogen center radical. This nitrogen center radical attacks intramolecularly, and you get this product, and that's what you get the hydrogen peroxide formation also here detected in the medium also. This also can propose a second path involved the path 2. So all this mechanism has been supported. Another interesting aspect of this thing, these two reactors again, the conditions slightly different, though I am not saying the exact same condition. One you are using the DMF, you can use the DMS also, but DMF gives a better yield. So again this is the additive dependent. Same solvents are there, white light, blue light, triethylene, sodium carbonate. You are getting a two interesting product. One, you are getting an exclusively difunctionalized product. In this case, you are getting a trifunctionalizing product. In this case, the bisphenol is very difficult to get this kind of bisphenol product with the simultaneous oxidation taking place at this rate. So we have a proposed EDA based mechanism in this case, because this carbonate is able to carry two negative charges simultaneously. On the other hand, thiol can form a dot negative charge. So that's what it changes the reactivity path. Okay, and this are getting two different. Another interesting aspect of this text is that while working on this molecule, I will tell you the central molecules. When you expose this molecule in the presence of air, and in two different solvents, one you get the tertiary hydroxylated product exclusively, another is get the pyroesterification product. Again, a solvent dependent reaction. HFIP is the fluorinated solvent, fluorinated isopropyl. In the fluorobenzene, you are getting a pyrocyclation product. So this took quite some time to, this again itself is a full work. I'll just tell you the summary of the gist of this work. So what is happening here, there is no photocatalysis, this is autocatalytic process, there is no photocatalysis there. So part of this molecule is absorbing. So you can involve the two kind of things. One is the OH tautomeric form, one is the NS tautomer. OH tautomeric form is 11.5 kilograms, so higher in the energy. On the other hand, if you look at the NS tautomer, it's highly conjugated. So that is the absorbing species. From the dioptrical predicted that this molecule is likely to have the absorption in the visible region, and that's what we see. When you absorb this molecule, we get a absorption in the visible region. So the NS tautomer is the light absorbing path, not the OH tautomer. So we are ruling out this mechanism. So if you take the NS tautomeric path, undergoing a photoactivation, going to the excited singlet state, undergoing intersystem crossing, goes to the triplet state, and it goes to it generates the singlet oxygen. Okay. So this is the mechanism I am proposing here. So if this is localized in the at this center, electron is localized at this center, C center radical. It takes the peaks of the radical coupling with the hydroxyl radical, undergoing this one, forming the alkoxy radical, and then two of this molecule will form the corresponding hydroxyl radical, and this hydroxyl on the other hand, the chlorobenzene, it will going a dearomatization and forming the spiral product. So another aspect of this one is that I have called you 15 minutes that's taken. Okay, I'll take 5 more minutes. Okay. So again, the solvent dependent reaction in the presence of tetrafluoroethanol undergoing this alkylation is a C3 position. Okay, electrophilic metallation. On the other hand, if you take the THF, this thing we are going to getting the ortho hydroxylation, ortho alkylation reaction. So again, the solvent dependent reaction here. So we have proved this mechanism. This is non-radical in nature, which we have proved by deuterium exchange reaction. Because had it been this one, then exclusively this hydrogen are getting exchanged, this getting exchanged, not this hydrogen getting affected in this medium. On the other hand, if you take the other THF solvent, these two hydrogens are getting exchanged. So that is this hydrogen is involved in the reaction path. Okay, but when you use the large example of this one, both all the 3 positions are getting selectively. Just like you're forcing this thing, like you're forcing a tiger to eat a grass, it will not eat. So what we did, we blocked both the C3 position with the methylene linker and forced this reaction to undergo this orthoalkylation, but did not take place. Okay, so that shows that how the strong solvent dependent this reaction is. So this is the mechanism. I will not spend much time because we are running out of the time. Another manganese catalytic reaction, which is again additive dependent, in the presence of PIFA, which is hyperconductive iodine gas, to get exclusively spirocyclic product. On the other hand, if you use the selector 4, which is a fluoridating agent, you are getting a dehydrogenated product exclusively again. Again, this is a exclusive solvent dependent, and this work has been highlighted by this thing. So along with this thing, they have talked about our work is starting from the very beginning of this thing. You can note what the work of the Patel's group and that thing. So they have highlighted our work along with the other people working in the mechanical reaction. This is another solvent dependent reaction where one of my students is doing this thing. But these two substances, when we react this thing in the presence of dichloromethane, it is forming an orthofunctional product. On the other hand, when I use the dichloroethane, okay, transient act as a transient dielectric group, and this gets converted to the nitrile group. Very interestingly, it gets converted to nitrile group and reaches the molecule of the acetophenol. Okay, so this we have discussed the mechanism. So I'll come back to this one. When you react this 3-component reaction, now we are able to construct both the furopyrimidine, furan and pyrimidine simultaneously, and this is again a non-templated synthesis because these are the various kinds of templated synthesis known in the literature. Okay, so this is the mechanism of this reaction. These are the various kind of post-synthetic modification after we got that product. I talked the last work I talked this thing. So all these things might be working the monoalkanes, but when you take 2 alkanes, what we are able to construct 3 heterocyclic simultaneously: furan, pyrrole, and pyridine. So we are called the furo, pyrrole, pyrimidine ring synthesis. Okay, and you can see that the number of new bonds that has been constructed in the red ones. So this is the mechanism of this reaction. I'll just skip this part. I'll skip this one. Okay, I'll talk about a little bit of this molecule. Okay, so when you react this one again, this alpha beta unsaturated acyclic one versus cyclic one. Acyclic one is given the pentafuse heterocyclic. So you can make the pentafuse heterocyclic in a one-part process using the palladium cat. Okay. On the other case, if you take the cyclic one, you are able to make the furocumarine derivative. But when you shift the hydroxyl group, I will tell you the last one. When you shift the hydroxyl group to this one, we are getting a altogether different kind of derivative. Okay. So better I will stop this at this stage. I will tell you the mechanism. Probably Jana sir will be more interested in this thing. So what is forming? Forming a dichlorophyll undergoing 3+2 cycloaddition reaction. Okay, and which is again the silver is enolizing this one, and then is undergoing lactonization, intermolecular lactonization with this kind of product. And when you do the palladium catalyzed reaction, you can be able to construct all the pentaphyl heterocyclic simultaneously. Okay. Probably I'll stop at this stage because this is a similar mechanism, almost identical to that previously what we have discussed this thing. But the silver mirror test can confirm that the silver zero is coming out of this medium. Okay. With this, I thank my research group, which is slightly older one. A few of them have left, and some new students have joined. And thank you for your participation.
Thank you, Mr. Patel. I think I may invite only one question. So many people will raise their hands.
I have saved some time for the question and answer session.
So one after another, you can.
Yeah, I can listen.
Regarding the substrate scope, that basically the pyrimidine structure, only you have taken biphenyl acetylene. No other aryl acetylene can be taken for
Diacetylene compound.
Yes.
We have done I have not shown the example. I have done about 30-35 examples. All substituted. Ortho substitute gives lesser rate, and metal para gives better rate. Sorry, I will be happy to answer your question.
I am interested in the beginning part of your question when you said aloo, potato.
Yes.
You can have many things.
Yes.
Yes. ओडिया लोगों को से आलू पोटाटा बहुत बोलो एते जो प्रोडक्ट करे तांतर आपको सबुठार सुंदर आलू पोटाटा कोटा कोन प्रोडक्ट
Sir, we are in synthetic chemistry. I will tell you my experience. So when you try to combine the biological application, then we have a struggle to publish that in a good journal, because they will say they will not understand the biological part. Okay. So in those cases, we have end up publishing the paper in a lower impact journal. So we just synthesize this thing and publish in the organoletter DOC ChemCom. Okay, but our compounds are ready for the other people to investigate, because a lot of beautiful material application, highly fluorescent molecule, many of them are water soluble. So because you need a lot of collaboration with other people. Yeah.
Sir, you have shown one solvent-driven synthesis, that is dichloration and dichloromethane.
Right.
So how that is like, because you are having only one CH2 difference, and how it is changing? Just would like to know a little bit on that. That it is giving two different products, like if you are changing that.
Because at higher temperature, because dichloromethane you can go to higher temperature. Okay, higher temperature probably that one of the intermediate decomposition and converted to nitrile group. Okay, but lower temperature is not going. But we tried also at the lower temperature, we get a mixture of the product. Okay, so dichloromethane we cannot go more than 42 degrees. Okay, so that probably that is the reason.
Temperature, not the solvent, we can say.
So temperature is solvent, you are controlling the reaction by solvent basically that way. Yes, sir.
I have one last. It is not that selectively dinitrile you are reducing converting one cyano.
One cyano.
One cyano to amide and then cyclide.
Yes.
With a copper acetate.
Copper acetate.
What is the mechanism? Why the other cyano group doesn't?
Other cyano, after all this thing, you say one cyano, a convert to amide, other is very difficult to reduce. Other is very difficult to reduce. Even for any other reaction, one can participate in this thing. So we tried like coupling with the boric acid with palladium catalyst to convert this thing. So we can copper acetate helps. Copper is assisting the hydrolysis process. If you do normal hydrolysis, but you require maybe a very high temperature probably. But then it break down to other thing. But you need a controlled hydrolysis.
That's why you take copper acetate.
Copper acetate helps this thing.
Thank you very much.
Sir, I now request Professor Das to felicitate Professor Patel.
Because I am here, I am
So with his students he has started.
Wait.
Direction.
Now the tea will be served here, so there is no tea break. And here the oral presentation will continue 1 to 15. And in front 1 to 15 oral presentation. And in room number A204, it will be 16 to 31, just in the front of the back door. Room number A204, it will be 16 to 31. So those who are present between 1 to 15, please come here for presentation. Oral presentation number 1. Anybody present? To the all are requested to please submit the PPT. 1 to 15, please submit your PPT. And to the other room, I request Professor. Sir, you are the judge. Professor SC, Professor Sasada Chamal and Professor A.K. Mishra will be here. And in the other room,
Professor Samal has left.
all left.
I'm the only one. I'll be here.
Okay. Join the Professor Ahmed Dena.
Hey,
Nushaw, Mr. Madam and SN Park. Both will move to other room. Oral presentation 1 to 15. Please submit your PPT here. Within 5 minutes we will start.
Plain paper.
Why are you sitting at the last bench? So last bench ke bosar pakku pole asuna ke bosina anti a bosibini asuna separate kon jai hobani they are also they are sitting at the last bench.
Madam, say photo first. বইটা যদি দিবে সে বইটা আছে না আমার কথা নেবেন আরটা নেবেন
ସେଇଟା ଥାଉ ଖାଲି ହଁ ସେଇଟା ନେଇକି ପଳାନ୍ତୁ କାଗଜ
ସେ ମୋବାଇଲ ଗୁଡ଼ାକୁ ହେଲା ଯେତେବେଳେ ଏବେ ସେମିନାର ହେବ ମୋବାଇଲ ଗୁଡ଼ା ସେଇଠି ରଖାହେବ ତାପରେ
Someone should chair.
back to there.
स्टार्ट की करना है आरंभ कर आचार्य सर स्टार्ट करना चेयरमैन पटेल सर
We will start from oral presentation, and it will be chaired by Professor Bhishma Patel, and two of my teachers they will be judged here. One is Professor Sabdanand sir, and another is Professor Ashok Kumar Mishra sir. Already the instruction is given that you have to present for 7 minutes, and you will give 2 minutes for defense. So total you have to complete within 10 minutes. So each candidate will be allotted total 10 minutes.
ओपी की अच्छे सीखा हुआ ओपी हाँ स्टार्ट है स्टार्ट करो यू स्टार्ट
सर बस
First student is Sachit K. Das from PSS UP Kurla. Sachit. Yes sir. Start. ये नेक्स्ट एंट्री আছে পসিবিলিটি আছে ফ্রন্ট লাইন কে কে অଛନ୍ତି নেক্সট ওপি2 কে ଅଛି কে কে ওরাল পেজেন্ট ଅଛନ୍ତି କହିବ କେ କେ ଅଛନ୍ତି ନା ମୁଁ ଜାଣି ଦେବା କିଏ ଅଛନ୍ତି ଏଠି ବସ କିଏ ଅଛି ଓରାଲ କିଏ ଅଛି ଆଗକୁ ଆସିବ ଟିକେ ଏ ଜାଗାରେ ବସ ଏ ବସ
ओरल रे जोने कंप्लीट करछु समय
so that you save time we'll have a head count
चलो
ठीक है तो हम अच्छे पूरा आसियो ठीक है
ओके
Good evening to all. My name is Sachit Kumar Das. I am going to present my oral presentation on the topic effect of clay on titanium dioxide emitted beam in nanocomposite for high performance energy storage application. Coming to my outline includes introduction, methodology, result discussion, conclusion, and finally acknowledgement. Before coming to the introduction, I want to draw your attention towards the increasing demand of energy storage devices. So, as we know, nanocomposite has a huge role towards it. So, on the basis of factors like high dielectric constant, high strength, high thermal and chemical stability, and laminar structure, we have chosen 3 precursor materials, that is PMMA, titanium dioxide, and chlorine 93A clay for the energy storage application. Coming to the methodology, first of all, polymer PMMA has been prepared from MMA by taking KPS as an initiator. Then both binary and ternary nanocomposite, that is PMMA titanium dioxide, PMMA titanium dioxide clay nanocomposite has been prepared by small gel method. Coming to the results and discussion, first comes FTR and XID analysis. So we have studied the FTR and XID analysis, which we confirm the formation of the binary and ternary nanocomposite, which can be further confirmed from the morphological analysis. This is the FSM analysis. The large spherical-like structures confirms the presence of PMMA, while the small spherical-like structures from figure C to E confirm the presence of titanium dioxide nanoparticles. As you can see here, the cylindrical paper-like structures present in figure C to E confirms the presence of clay nanoparticles. Here the important discussion we have observed, that is the agglomeration is significantly reduced in the case of ternary nanocomposite from figure C to E as compared to figure AB, that is binary nanocomposite. Figure A represents the EDA spectra, which confirms the presence of all elements in the ternary nanocomposite. This can be further confirmed from HRTM analysis. Here we can observe the distorted cubical shape-like structures confirms the presence of titanium dioxide nanoparticles on the PMMA surface, and the stacked chlorine 93A particles seen in the dark line patterns over the surface of the PMMA surface. This confirms the successful formation of the ternary nanocomposite, and the lattice fringe is calculated to be 0.383 nanometer in figure I, figure E, and the crystallinity size is observed, which is in good accordance with the XID results of the ternary nanocomposite. This is the TG analysis. Here we can observe the maximum thermal stability is observed for the ternary nanocomposite, which is around 43.22% at 700 degrees Celsius, which is represented in this table, which gives additive advantages for the enhancement of dielectric and electrochemical properties. Coming to the BET surface area measurement, as it is shown here, we can observe the BET surface area of ternary nanocomposite in figure B is much higher as compared to the figure A, which gives the enhancement in the dielectric and electrochemical properties. Coming to my application part, this is the dielectric behavior of ternary nanocomposite. In figure A, we can see the decrease in the dielectric constant with increase in the frequency, which is due to the ceasing of polarization. Figure B represents the decrease in the dielectric loss with increase in the frequency due to the loss of dipolar and interfacial polarization at higher frequency. Figure C represents the constant increase in the dielectric constant, but after 95 degrees Celsius, as we can see here, there is sudden fall in the dielectric constant, which is due to the loss of interfacial and dipolar polarization at elevated temperature. The highest SC conductivity observed over here is 1.45 into 10 power minus 4 Simon per meter. Coming to the electrochemical measurement, this is the 3-electron measurement. Figure A represents the CB plot. At varying scan rates, even at higher scan rates, it retains its shape, which shows the good capacity behavior of the nanocomposite. Figure B represents the comparatively CB plot, specific capacitance plot between binary and ternary nanocomposite. The highest, the total specific capacitance of ternary nanocomposite at each scan rate is much higher than the binary nanocomposite. Figure C represents the GCD plot at varying current density. Figure D represents the EIS plot difference between the binary and ternary nanocomposite. Here the ternary nanocomposite experiences better electronic conductivity as compared to the binary nanocomposite, and the charge transfer resistance of ternary nanocomposite is much smaller than the binary nanocomposite. Here we can observe the CB plot, comparatively CB plot difference between the binary and ternary nanocomposite. As we can observe here, the CB curve area of ternary nanocomposite is much higher than the binary nanocomposite, and figure B represents the discharge time of ternary nanocomposite is comparatively longer as compared to the binary nanocomposite. So fascinating, from the 3-electron system, we went for the 2-electron measurement of ternary nanocomposite. Figure A represents the CB plot between the activated carbon and ternary nanocomposite. Figure B represents the CB plot at varying potential window. and here we have observed the suitable potential window is observed to be 0 to 1.6 volt. Figure C represents the CB plot at varying scan rates. So even at higher scan rates, it retains its shape which shows good capacitive behavior of the ternary nanocomposite. In figure D, the highest specific capacitance is observed to be 364 farad per gram at 10 millivolt per second. Figure E and F represents the DCT plot at varying potential window and current density. Figure G represents the solution resistance is observed to be 6.8 ohm, while the charge transfer resistance is observed to be 8.4 ohm in the ternary nanocomposite. Figure H represents the Ragan plot between the energy density and power density. Here the maximum energy density is observed to be 129 watt hour per kg at a power density of 2923 watt per kg. Figure I represents the highest specific capacitance, the capacitance retention percent of 97% even after 5000 CV cycles. So we can finally conclude here the highest dielectric constant is observed to be 1.45 into 10 to the power 3 at 1 kHz frequency and a high specific capacitance of 364 farad per gram with a maximum energy density of 129.26 watt hour per kg at a power density of 2913 watt per kg at 10 millivolt per second. So even after 5000 CV cycles, it retains its capacitance percentage of 97%. So we can finally conclude with increased dielectric permittivity and enhanced electrochemical properties. This nanocomposite can be fruitful for the future energy storage application and supercapacitor application. I want to finally acknowledge my professor, my supervisor, Professor Sarath Kumar Swami, OCS, OUTR, esteemed jury members, all faculty members, lab mates, and finally thank you.
Thank you for finishing on time, right on time. Yeah. Anybody want to ask any question?
You see, why your ternary nanocomposite is thermally more stable?
Due to the addition of clay, actually, it forms a sandwich-like structure. So that's why the addition of clay enhances the material's thermal stability.
Now what happens? What happens? The addition of clay.
Actually, the formation of ternary nanocomposite is just like a sandwich-like structure. The formation of sandwich-like structure leads to the increase in the thermal stability from binary to ternary.
No, but why is thermally more stable?
Due to the addition of chloride 93A as from the established papers, we know the addition of the clay into the polymer nitrate.
You have to explain why. Why? What is the reason? Think of it.
Sir, actually, I am saying that the formation of the structure in the ternary nanocomposite, that's the main reason behind the increase of the thermal stability.
So you explain that means bridging.
Yes, just like sandwich-like structure, like
Say
plate-like
for
structure.
example, vulcanization process. See, sulfur bridging, that stabilizes the two layers. So similarly, what happens here?
Sir, actually we don't know about that. Well, I don't know about it. But as per my analysis and all properties,
Your
I can say
analysis is
that.
okay, but what
yes,
would be the reason why?
Sir, one of the
Achha,
reasons
one more,
yes.
leave it. One more question. How do you prepare polymethyl methacrylate? Starting from acrylic acid. I am giving you acrylic acid and my target is to prepare polymethyl methacrylate. You have in the first one or two slides.
We have prepared from
first starting material.
First starting material.
How do I get from acrylic acid? I am giving you acrylic acid and I tell you prepare the starting material. Once you get the starting material, then it will polymerize.
Yes, sir.
So how do you get the starting material from acrylic acid?
Sir, I don't know the proper answer, but I think we
You
have to
guys-
first prepare the monomer units
No.
from the acrylic
This
acid.
is a monomer.
Then I am saying
Acrylic acid is also a monomer.
Yes, sir. Sir, actually, MMA is
No,
we
you
have
do
taken the
know.
commercially available.
So don't skip the question. My question is how to put the two methyl groups. Acrylic acid, I am helping you. Acrylic acid is CH2 double bond CH COH. That is acrylic acid. Okay. So how do you put two methyl groups? One on carbon, the other on oxygen. You try this conversion at home as a homework.
Yes. Thank you, sir.
Slide 6. तब कौन कंफर्म कर से
सर आईआर में जाने कि जो मेटल ऑक्सीजन पीक देखेला both bypass and ternary, which is around 688 centimeter in the here and here both. And new peak is observed around 1043 centimeter, which gives the difference between the binary and ternary. And this is this peak denotes the SIO stretching.
So because of the stretching, you are saying it is ternary.
Sorry.
Because of the stretching, SIO silicon oxygen silicon.
Yes, sir.
That only says that there is clay.
Sir, it does not clearly signifies the presence of clay, but the formation it says that the new peak is denotes the attachment of silicon SIO stretching frequency denotes the it may be the attachment of clay, which can be confirmed from other analysis that FESM or HRTM.
Pure clay रहने को ना आसू के नहीं से picture. Just take an IR of pure clay.
IR of pure clay, sir, we have taken that so that even if that so established papers also, and even if we have taken the pure organomodified clay, that is we have taken 1041 to 1045 centimeters.
So
that much. Yes, sir.
Second is go to slide 11.
Yes, sir.
You said that EIS plot, no?
No, sir. It is AC conductivity.
You go to EIS plot.
Sir, this one, figure D. Yes, sir.
So what is EIS?
Electrochemical impedance spectroscopy.
So this plot, there is a name for it, another name that now.
Nyquist plot, cold door plot.
Okay. So there is a body plot, there is a Nyquist plot.
Yes, sir.
This is Nyquist plot body.
Sir, actually, this is EIS plot. We can plot the Nyquist plot from the dilating data. For that, we need to know the breakdown strength. If we know the breakdown strength, then we can calculate the Nyquist plot. Actually, we don't have the facility to find out the breakdown strength, so we have performed the electrochemical measurement.
From this data, you will not get anything. You go to Nyquist plot, only then you get some data to.
Yes, sir. Yes, sir. Sir, actually, we don't have the facility to find out the breakdown strength. Sir, in order to find out the breakdown, at what time it breaks the substance, then only we can find the Nyquist plot and we can plot.
The way these two axes, one is a linear axis, the other one is a.
Sir, this is log one.
Why it is so?
Sir, it is actually the impedance and all those are calculated in log plot also.
Yes,
only
but
log.
that should be related to some mathematical relations, right?
Sir, there may be, but I don't have that. Sorry.
Let us thank Sachin Das for his nice talk. Thanking you.
Thank you, sir.
Now we move over to the next one. Tanaya Subhuti from NIT Roundela. She is working in the group of Ravindra Kumar Behera. So she will be talking about intricate interplay of iron thiol for the iron mobilization from keratin.
I suppose I'm not audible. Good evening, everyone. For today's talk, I have a description like intricate interplay of iron, oxygen, and thiol for iron flux from bare and ferritin-based mineral. To understand this, we need to understand what is happening and what is ferritin. So, in order to understand ferritin, we need to understand how life was originated. Life originated in the presence of iron and sulfur. I am talking about the pre-GEO era, how the life has originated. In this case, what happened? Nature modified itself in such a beautiful manner that it incorporated iron too and also sulfur in the pre-GEO era. Now, what happened in the GEO era? Whenever the oxygenation happened, there was a certain involvement of the oxygen. So now nature has learned to incorporate iron to and H2S. So what oxygen did, it caused the iron dilemma. Now we need to understand what is iron dilemma. Whenever there is an oxygen iron 2 readily gets oxidized to iron 3 and which precipitates. And due to the precipitation, what happens? Like the organism are unable to take the iron. It needs to first reduce the iron first, then it can assimilate the iron in the biological implications. Now, what is the iron dilemma? In this case, we need to understand that iron is very essential for all the biological problems, like biological systems. So, what is the toxicity? Like, why this is called dilemma? Because iron 2, whenever it is present with the H2O2, that is hydrogen peroxide, it forms OH radicals. So, that OH radicals is very reactive, which can damage all the cell organelles. So, in order to mitigate that thing, nature also designed this ferritin protein. This ferritin protein, what it does, it catalytically sequesters iron 2 and stores as a ferrihydride mineral. So this ferrihydride mineral, whenever required by the body or any organism, this channels again iron 2. And how it looks in the TM image, looks like this. It has a 12 nanometer cage, and inside which there is a 8 nanometer hollow cavity, which can store up to 4,500 iron. Then, why we are talking about thiols, like the H2S. As we understand that in our body, for a proper functioning of a body, there is also requirement of 0.2% of the sulfur. And this sulfur comes from these natural thiols, that is the GSS, that is glutathione, DHLA, cysteine, and sodium sulfate. Sodium sulfate, which is physiologically HS minus or H2S. So now, why these all are important? We know in our food, cysteine and methionine are present, which are very essential amino, right? And this cysteine is very essential for the synthesis of the glutathione. And this glutathione and cysteine are very essential whenever there is a H2S production is there. This H2S production is essential as a gasotransmitter. So with that, we have also taken the synthetic thiols. That includes DDT, TG, cysteine, and 2-mercaptophenol and TAA. By utilizing these thiols, we are trying to mobilize the iron which is present inside the ferritin. And in order to understand how this has happened, this is the schematic representation how we have done. We have taken the protein encapsulated ferrihydride and also the bare ferrihydride where the protein is not present. And we have utilized this sulfur containing reducing agent for the electron donor possibility. So what this does, it gives the electron to the iron 3 that is present inside the ferrihydride mineral that get reduced to iron 2. By capturing that iron 2 with the ferrozin, which is the iron chelator, we monitor the absorbance as 562 nanometer. And by doing that, we understood that whenever there is a bare ferrihydride where their protein coat is not present, we can channelize high amount of iron. But these sulfur containing compounds, whenever they are subjected to bare ferrihydride and encapsulated ferrihydride, they behave differently. Means there is an effect of the encapsulation that is happening. Whenever there is an encapsulation, the smaller molecules like TGA, which is thioglycolic acid, it is able to release higher amount of iron. But whenever there is no encapsulation, we can see the DTT is releasing high amount of iron. So now, in order to understand how this impact, like thiols are impacting on the iron release, we have seen, we have divided all the movement into the first one is impact of size. Why that such a thing is happening? Whenever Na2S and glutathione is present, glutathione is bigger in size. So maybe it is unable to enter to the ferritin port, or maybe it is unable to have an interaction with the bare ferrihydride, due to which it is not able to release more amount of iron. Then comes the impact of branching. If we see dihydrolipic acid and the glutathione, there is so much of branching is there in glutathione, and there is less amount of branching in dihydrolipic acid. Along with that, there is also a number of thiol group. Higher the number of thiol group, we have seen higher amount of iron release. With that, accessibility to the core. Whenever we talk about the protein encapsulation, we need to access the core properly. So in order to have better accessibility, we need to have a smaller size. So we have seen that whenever there is a smaller size, there is a iron release. But all these molecules have a smaller size. So maybe the H2S, which is physiologically present in the case of Na2S, that is HS minus, that is able to access the core. Then comes the iron chelation. Which compound is able to achieve a better iron chelation, that is able to give a better iron release. Now comes the auxiliary, which is the COH or NH2 group. Based on that, we have categorized maybe COH group is able to assist the iron release and NH2 group is able to prohibit the iron release. Now, as I told you in the first slide, that is, there is also involvement of the oxygen. If this thiol, which is an antioxidant system itself, and also ferritin, which is an antioxidant system, what happens in presence of oxygen? So we have understood that whenever there is an iron 3 present and also thiol present, the amount of oxygen consumption increases. Like this is the cysteine plus iron 3. We can see that whenever there is
iron 3, the amount of oxygen consumption has increased. So in this case, we can understand that whenever there is iron 3 is present along with thiol, the oxygen amount is very, very limiting, which is almost equivalent to the pre-GOE era. So now, how this oxygen is consumed, we understood, and whenever this oxygen is consumed, there can be various chances of forming of reactive oxygen species. So we also we have also seen that how this reactive oxygen species is impacting on the DNA completely. And in this case, we have run the DNA in agarose gel, and in which we have implicated the thiol. Yes, we have implicated the thiol, and we understood that sodium sulfate is able to completely protect the DNA. Now, these are the key findings. First one is small size is able to assist. Branching of the molecule is almost inhibiting. Then COH is assisting. NH2 group is inhibiting. Then number of thiol group is assisting in the iron release. Redox potential is also assisting in the iron release. And KH stability. This KH stability we have done with two proteins, program protein and BFRB protein. And program protein is much more stable. That's why it is inhibiting the iron release. And then the iron chelation ability is also assisting. And lastly, oxygen consumption is also assisting. At last, I would like to acknowledge NITR, my supervisor, Professor Bhubaneswar, OCS, for giving me this platform to present my work. Then, last but not the least, my family and my friends. Thank you.
First slide, ferrosulfate, hydrogen peroxide. Ferrosulfate, iron 2 and hydrogen peroxide. Go to the next one. The oxidation reaction. What is that reagent called? It is a name. Ferrocyan with hydrogen peroxide.
It's a Fenton's reaction.
Fenton's reaction. So now tell me, if I give you benzene, can you convert it to phenol?
If there is a metal present, maybe we will be able to.
No metal. Metal is iron. Iron 2.
Okay.
I have Fenton's reagent with me. Your ferrocyan hydrogen peroxide, ferrosulfate hydrogen peroxide. Now I want to convert it to phenol. Can I do it?
With the help of OH radical.
I don't know. You have to tell me yes or no. It's a conversion, organic conversion I give from your first slide. Iron toxicity, Fenton's reagent. We have shown the one equation.
Yes.
So I give you benzene and I want to convert it to phenol. Is that reaction known or not known?
Benzene to phenol conversion.
Yes.
Yes, it is known, sir. Maybe we will be able to convert it with the help of OH radical.
But then why the industry is not following it? Why sulfonation, then sodium hydroxide treatment, sulfonate, salt, alkali fusion, and then acidification, all this process.
Yes,
so that is the conversion. So why they are not, my direct question is, why the industry doesn't follow?
Maybe we will be able to convert it, but industries are not following it because this is a very unstable radical. You may want it in the proper position, suppose you may want it at the 2 position, but it indiscriminately behaves at all the, may phenolate at all the positions. So you may not be able to. No, sir, like if benzene is
No, don't make any guesswork. If you know the answer, tell, or if you don't know.
No, sir, as much as I understand, maybe that is.
See, OH radical is created. You have put it in box, so the red box. Okay. So OH radical is very damaging. Right. So it will abstract one H dot. So phenyl radical will be created and then OH radical will go there. Then phenol is prepared. Why the industries are not following that? My question is that. Think of, go and find out the answer. Okay, that is first question. Second is, in our blood, human blood, iron exists as iron 2 or iron 3? Iron 3. Why?
It is bonded with the heme.
So what? I will say that it is present in iron 2. So which is more stable? In chemistry, applying your knowledge of chemistry, tell me which ion is more stable, ferrous or ferric?
Thermodynamically, ferrous is more stable.
Don't say thermodynamically, kinetically. I want a straight answer. Which ion is more stable, ferrous or ferric?
Ferric is.
Why? Ferric is correct, but why?
Sir, the energy, if we talk about, then
Don't go to electronic configuration. Ferric ion 3D, how many electrons?
5.
So 5 means half field. Half field means more stable. That's the answer.
Yes, sir, that's what
But in complex formation, ferrous ion is more stable. Potassium ferrocyanide is more stable. Why?
So there is a potassium ferrocyanide.
Yes. Their iron is +2.
Sir, maybe due to ligand metal.
What ligand metal?
Ferrocyanide is able to give that.
Ferrocyanide is more stable than ferricyanide. Why? ଯଦି ଏଠି କହୁଛ iron 3 is more stable than iron 2, ତାହେଲେ ସେଠି ବି ସେୟା ହେବା କଥା, କିନ୍ତୁ ସେଠି ଦେଖିଲା ବେଳକୁ ଓଲଟା. Potassium ferrocyanide is more stable than potassium ferricyanide. କାହିଁକି?
Maybe we can consider the ligand CN
ସବୁଥିରେ ତ may be ଆଉ. ହଉ ହଉ
CN
ଠିକ
minus is
ଅଛି.
a strong ligand, so ସେଥିପାଇଁ maybe stable. CN
ଆରେ
minus
cyanide and what type of ligand?
strong ligand ସେଥିପାଇଁ.
Strong ligand. Strong ligand ହେଲେ କ'ଣ ହବ?
Splitting ଇଏ ହବ, ମାନେ pairing ହେଇଯିବ.
Pairing ହେଇଯିବ. ବାସ୍ ଏ ତ କଥା ଆଉ. Crystal field theory CFT. Simple ଜିନିଷ ଭଲ କି ଇଏ କର. ଆଉ ମୋର ଗୋଟେ ଲାଷ୍ଟ କ୍ୱେଶ୍ଚନ ହବ, ତମେ ଯୋଉ ଥାୟଲ ଉପରେ SH କରିଛ, ମୋର CS ବଣ୍ଡ ଅଛି, ସେ ଗୋଟେ କାର୍ବନ ବହୁତ ଜାଗାରେ ସବୁ SH ବଣ୍ଡ ଅଛି. CS ବଣ୍ଡ କୁ କେମିତି ଭାଙ୍ଗିବ? Say for example, I have 1,3-dithiene or 1,2-dithiene. माने कार्बोनिल टा को प्रोटेक्शन करछि 1,3-dithiol द्वारा in BF3. बुझ पालो? साइक्लिक थायोल फॉर्मेशन है. से बॉन्ड टा केमती भांगिबे? CS बॉन्ड भांगी के CH बॉन्ड करिबे. Any reagent you know? Any reagent you know to break CS bond? To make it CH bond.
Like we can go for a reduction, but any reagent I may not be able to take.
Have you heard the name of nickel boride?
Yes.
Huh? So nickel boride or Rani nickel. Have you heard the name of Rani nickel?
Yes, sir.
So Rani nickel breaks that bond, CS bond or nickel boride. Nickel boride केम तैयार करू? ना भितर जीव पड़िबो ना, तो भलो के प्रिपेयर करियो, तो सबुथरे एसएच अछि. हां
गोटे तो ऑर्गेनिक केमिस्ट्री ना फिजिकल केमिस्ट्री?
Sir,
फिजिकल केमिस्ट्री मान गोटे राइट अछि ऑर्गेनिक केमिस्ट्री ना जाने. ओके नेक्स्ट इज मोर गोटे क्वेश्चन के लागे इज अ फेरी हाइड्राइट टू हाइड्राइट काइंड ऑफ DRITE व्हाई इट इज सो?
Okay, this is very high, right?
हां टी है ना हाइड्राइट टू कौन से मीनिंग
हाइड्राइड ही था डी टा पी
टा काहे टी हैला?
Sir, the naming is in the.
if it is somebody has given this name, is there any logic behind it? That's not.
Okay, why it is not hydride?
No, I'm not saying why it is not something. I'm saying why somebody uses a letter T
So
there.
maybe if you see the formula, Fe2O3.XH2. Maybe due to the presence of the H2, they have written that very hydride.
T is causing that problem. Okay, just think about it. I don't know. You go to that oxygen, and one more thing for all of you, better put slide numbers so that it's easier for people to ask questions. Go to the oxygen consumption slide. Oxygen consumption what slide lo na what bas last ad ha sir solve. Go to the previous one. No. Go to the question that go to the same slide, oxygen consumption slide. Something question I forgot now. What did you say? Can you repeat so that I can remember my question?
Okay, sir, in this case, what we are saying, whenever there is only iron 3, there is no oxygen consumption. Okay. And when oxygen consumption.
Why should iron 3 means it is already fully oxidized? What do you mean by that? Why it is there is no oxygen? It's precipitating.
If it is precipitating, then it can consume some amount of oxygen.
That's okay. So precipitation is the reason for no oxygen consumption?
Then they cannot be. Even also in presence of cysteine, we have not seen any oxygen consumption.
Then how do you explain all that?
Sir, maybe the cysteine is unable to reduce oxygen completely. But in presence of little amount of iron, the oxygen is completely consumed. Similar to the situation in the pre-GO era. How?
No, which iron? Iron 3 plus? Iron 3 plus is fully oxidized. How does it consume oxygen? How does it help in consuming oxygen?
Sir, for that we have various theories like octo-oxidation might happen because as we can see, only if you put only iron 2 at pH 7, then it rapidly consumes oxygen. So maybe the cysteine which is having this sulfur and it is able to give the electron to the iron 3 and the oxygen oxidation is
Okay, my question.
Okay, so maybe you are reading too many times, maybe. Okay, because science says you have to, so maybe you should thank you. Okay, thank you for your talk tonight. Now, so I invite the next speaker. Devi Prasanna Behra, right? He is working with her business farm. From the Biophysical and Protein Chemistry Laboratory of the National Institute of Technology, Rourkela. So he will be talking about the effect of hydroluronic acid and its sulfate derivative on mechanistic path. Please go ahead.
Can I start?
Yes, start.
Good evening, everyone. Myself, Bhubaneswar from HumanitiesOdisha, Rourkela, and my oral presentation is titled as effect of hyaluronic acid and its sulfated derivatives on mechanistic pathway of bone morphogenetic protein to aggregation. So, what is first aggregation? As we already know that the protein is functional in its native state, or you can call it as a folded state. But when the protein aggregates, that means the secondary structure is lost, and one protein clumps over another protein gives a larger mass, and that's called as a protein aggregation. So in protein aggregation, protein is non-functional. So let's dive into the introduction part. So our interest of protein is the bone morphogenetic protein 2. Why this protein? This protein is a 50% unstructured part. That means it don't have structured part more than 50%. It has around 10% of alpha helix and 40% of beta sheet, and rest 50% is unstructured part, which is prone to aggregation and it is exposed to solvent. So this part can attach with another protein which makes it aggregate. By this process, the protein may lose its activity. So this protein is present in the bone extracellular matrix, and it helps in bone regeneration, bone cell nourishment, bone healing, etc. And for doing this, it interacts with, actually it's present in a proteoglycan state. It attaches to the glycans like hyaluronic acid, heparin sulfate, and other glycans are there. So we took two glycans. One is the hyaluronic acid, which is already present in the non-sulfated form in the body, and we sulfated another one to check the effect of sulfate group on the aggregation behavior of hyaluronic acid. So why aggregation is a problem for this protein? So this protein presently last 1 decade is used in the bone surgery and dental surgery, but they are putting the protein in native form to a 3D structure of collagen, that may be a glycan 3D structure, but the protein is, they reported that the protein is aggregating in vitro condition. Though it is not aggregated form, it's not prone to aggregation in vivo, but it is prone to aggregation in vitro. That's why the protein can be stored a much longer period, and that may be complicate the process where the desired use like bone surgery and dental surgeries. So what are the problems? The problems are that it is prone to aggregation, and it can be stored for a longer period, and it is not efficient as a proteoglycan. Though it is present in the body in a proteoglycan state, and in native protein doesn't have that much effect like the proteoglycan state. So what we want to propose here. So our objective is that to make it proteoglycan in vitro. So before make it proteoglycan, we have to study the protein-glycan interactions. Now what are the interactions and how it is affecting the aggregation behavior of this protein. So first we check the fluorescence spectra of this protein in presence of both the glycans. That one is the hyaluronic acid and that is the sulfated hyaluronic acid. We got somehow a little bit enhanced fluorescence that may be due to the clouding effect or which may exclude the solvent quenching. That gives rise to some enhancement in the fluorescence. And in secondary structure, we found that in case of the hyaluronic acid, in the increasing hyaluronic acid, we found it another peak, but the protein has two peaks, one at 208 and another at 222 nanometer. But higher concentration of hyaluronic acid, we got a peak at 260 nanometer. But in case of the sulfated one, we don't get that spectra, that peak actually. But this is not conclusive because the hyaluronic acid and sulfated hyaluronic acid itself has a CD spectrum. That's why we go for the FTIR spectra because, and we calculate, we got the spectra in the amide 1 region, that is 1600 to 1700 centimeter inverse, and we found that while it is interacting with the hyaluronic acid, the secondary structure that is more presently beta seed is increasing. When increasing the concentration of hyaluronic acid, beta seed is increasing, but that strain is not shown in case of the sulfated one. Second, we go for the theoretical part. We adopt the two glycans. One is the hyaluronic acid and sulfated hyaluronic acid. Both are binding to the aggregation prone region. And second thing is that the sulfated hyaluronic acid is more efficiently binding to the protein than that of the hyaluronic acid. And hyaluronic acid is binding near to the amylogenic sequence, which forms an amyloid beta formation. And till now, we are confirmed that there are some aggregation is occurring because beta seed is increasing in case of the hyaluronic acid and sulfated hyaluronic acid. There is unstructured part is increasing. So we use two dyes. One is the ANS, another is Congo red. So ANS binds to the hydrophobic patches of the protein, irrespective of the aggregation. That may be a amorphous aggregate, that may be a fibril formation. So in case of the hyaluronic acid, we got enhanced fluorescence, but in case of the sulfated one, we got enhanced, but it is less than that one. And in case of the Congo red, as the Congo red binds to the cross beta seed region, that is for the amyloid beta. In case of the sulfated one, in case of the non-sulfated one, we get enhanced fluorescence. But in case of the non-sulfated one, we don't get enhanced fluorescence. We get enhanced fluorescence, but that is not more. Further, we go for the morphological study. In case of the ANS stain, in control study, we found the larger portion of the aggregate part. But in case of the sulfated one, there is lesser aggregation is there. But in case of the Congo red staining, we found that fibrillation is here much, but in case of the sulfated one, there is less. And we also studied the TEM for morphological study. We get a larger aggregate in case presence of the hyaluronic acid, but in the lesser size aggregation in case of the sulfated one. It is not completely fibril. As we are getting that, we are getting beta seed structure larger, but we are not getting proper fiber because it has a cysteine knot which prevents the fibril formation. Further, we go for a rheological study. As the diameter is increasing, hyaluronic acid diameter is higher, and further we studied the coefficient of viscosity. Hyaluronic acid solution has a higher viscosity, hence the aggregate forms in the hyaluronic acid case has a lesser diffusion coefficient than that of the sulfated one. We propose two mechanisms. First mechanism is that in presence of the hyaluronic acid. Hyaluronic acid interacts with the protein as hyaluronic acid is capable of holding 1000 times the water than that of its molecular mass. It extracts the biological water and the protein. Biological water, and it is viscous. It is the viscous solution. That's why the nucleation phase is there, and as the molecule is larger, the larger aggregates are there. But in case of the sulfated one, viscosity is lower. So one protein can clump with another protein much faster than that. So that's why we don't get any type of lag phases there. So this is the conclusion, like higher viscosity, low diffusivity, and higher excluded volume in presence of hyaluronic acid promotes fibrillation in case of the hyaluronic acid presence, and opposite in case of the sulfated one. Lastly, I acknowledge thanks to OUTR and OCS to present my work and funding agencies. Thank you.
Go to your first slide.
So here you have drawn two organic structures, right? Can you tell me which is more stable?
Sir, both are more stable.
How can both be? Which is more stable?
Sir, it is a polymer, so stability can't be measured, sir, in my perspective.
Okay, then let us go to the monomer. See, ring A and ring B. The linkage is alpha or beta?
Alpha.
Again see. All substituents are equatorial. So, if all substituents are equatorial, it is a beta linkage. Beta linkage. Now, let us go to the fundamental question. No, here I am asking the question. See, if I take a carbohydrate where you have an alpha linkage and another case you have a beta linkage, right? Which is more stable?
Maybe, sir.
Say for example, alpha D glucose and beta D glucose.
So I don't know much about that, but it may
But
depend upon the solution.
you see, you have drawn chair-like structures, all carbohydrate structures and all that.
Yes.
I am helping you. You see, there is an anomeric carbon. The carbon connected to two oxygens, right? That is called anomeric carbon.
Yes.
So, if it is the substituent is down straight axial, it is called alpha linkage, and if it is beta, it is called beta linkage, equatorial.
Yes.
Okay. Now tell me which is more stable. Alpha, I am helping you. Alpha D glucose and beta D glucose.
Sir,
which is expected to be more stable and why?
Maybe, sir, the equatorial are more stable.
Why? That is the reason.
Because maybe the steric investment, sir.
Steric. Why
Sir,
steric?
it is different. It may differ, sir. Maybe solvent is there. Another solvent is more. One is more stable.
See, no solvent. You see, do you know 1,3-diaxial interaction? No.
So need to be a little more clear about the objective. What is the objective you have?
Sir, we are trying to make it a proteoglycan, but it is a ball. But the present work is interaction of the protein and glycan.
It is not an objective. What do you mean by interaction? There is always an interaction.
To check the aggregation behavior.
So I think that would have been a better objective.
Yes.
To look at the aggregation behavior of what?
One morphogenetic protein 2.
But what have you compared in your slides? What is the conclusion finally? The objective should lead to the conclusion.
Yes.
What is the conclusion you got then?
In case of the hyaluronic acid presence, the protein got aggregated, which is has much larger size and got fibrillated mostly. And in case of the sulfated one,
So is that not the objective? Sulfated and unsulfated hydrogen.
Yes, sir, but they are summed up like glycans.
So that would have been a better way of writing it.
Yes,
That would have been much more clear as an objective. This is a vague objective. Make sure that you don't do that. Okay. Slide number 3. What exactly are you saying here? The fluorescence intensity, what does it tell you? Because both appear almost same to me.
Yes.
So what is the conclusion that you draw?
Sir, maybe two conclusions can be drawn because these are the larger molecules that may cloud.
No. Between HA and SHA, you are saying they are almost similar to each other?
No, sir, the size is very different.
In the fluorescence spectral data, I am saying.
Yes.
From fluorescence wise, there is not much of a difference. That you should be telling it in that way.
Yes.
So you are comparing HA and SHA, that's all. Interaction of HA, that would have been a better title for you. Overall title. Overall title was a little vague. Got it? Because the whole work was like the HA interaction and SHA interaction. Okay. Slide 4. These are UV spectra, right?
No, sir, these are IR spectra.
Oh, these are IR spectra. Oh, okay. I can't read numbers. 4-digit numbers. Okay. So then that's why you got all these deconvolutions. Like, how did you make all these decomposition of the overall spectrum to?
I use Orissa for that. Orissa, the secondary deconvolution method, and
It's a Gaussian or a Lorentzian effect that you have done. The spectra, the symmetric spectra that you are creating, no? The structures, are they Lorentzian or Gaussian?
sir, these are Gaussian. The software.
You just only Gaussian. IRs are often Lorentzian. No? Just remember that. Okay. The peaks will not make much of a difference, but the overall the fitting may be affected because of that. Just keep that in mind. Slide 6. Yeah, okay, I got it. I was confused, like your title was not very clear, so I was confused. It's okay, it's fine. Slide. Okay.
Congorate structure upre dharana achi. Congorate ta gote ki prakar dye. Bibhinno prakarର dye achi. Kahilo di charta na.
Dye in the sense.
Prakar, classification of dye, honors re padha jaye. Malachite green की प्रकार डाई, कंगोरेट की प्रकार डाई, कंगोरेट रे फंक्शनल ग्रुप कौन अच्छी जान क्यों? NH2 डाई रे NH2 रही परिगो, ऐसे डर डाइजुटाइज हो परा N2 plus Cl minus हो, डाइजुटाइज है गले. Tetradotyl aniline is condensed with कहाँ से तो कंडेंस कले कंगोरेट हो स्ट्रक्चर धारणा अछि कि ना नहीं इरे तली कंगोरेट वाटर काहे यूज करछो एटा गोटे डाई की प्रकार डाई मो पचार एसिड बेस डाई की ट्राइफिनाइल मीथेन डाई की एजो डाई की को प्रकार रो डाई कंगोरेट इज एन एजो डाई सेठी क्रोमोफोर के ऑक्सोक्रोम के
Sir, there are benzene rings are there.
benzene ring टा कलर है वो पचार च क्रोमोफोर के ऑक्सोक्रोम के और क्रोमोजेन के
Okay, let us thank David Prasanna for his talk and invite the next speaker. Priti Josna Mahapatra from the BJB college, OP number 12. So she will be talking about optimization of fly ash water slurry rheology through the use of natural extract. Anyone is there? Oral presentation?
Anybody left?
It's the fourth one. Oh, it's the fourth one. Five is OP 12. OP 12. You know, the 5 I will turn up, 4 have turned up.
Okay.
Yes. How do you normal invited? Start. Microphone to देखो.
purpose of our work is
flow of the fly ash water slurry. So this is the introduction part. And fly ash is nothing but the byproduct of the coal ash that is produced in the coal combustion in the various thermal power plants. Normally, the total flow fly ash is 80 to 90% present in the coal ash, and bottom ash is present about 10 to 20% in the coal ash, and the bottom ash is settled at the bottom. And fly ash is the lightest form of coal ash that fly up to the exhaust shaft, and it mainly consists of light quartz and Fe2O3 etc. and a small amount of calcium oxide. And normally the fly ash has the several implementation, just like in concrete formation and backfilling of the coal mines etc. So we have to, for this purpose, it needs a proper transportation to the destination site. So, but its transportation is quite risky due to the presence of some flue particles, and as well as with some radioactive elements just like arsenic, lead, etc. So it needs a proper way of transportation, but its transportation is risky, and nowadays to solve this issue, pipeline transportation is used in the form of water slurry. The fly ash is transported through the pipeline in the form of water slurry. But that is a difficult process due to it needs various types of obstacles. Due to its the settling properties and the high viscosity of the fly ash water slurry. So our objective is to characterization of the fly ash, study of the rheology of the fly ash water slurry through the different parameters, and study of the critical micelle concentration of the surfactant, and development of the eco-friendly surface active agent for the stabilization and transportation of the high concentration of the fly ash water slurry, and to improve the flow behavior of the slurry using the natural surfactant by lowering its viscosity. Then coming into the material section, we have these are the materials we have used. We have collected the fly ash from the JSPL Angul, and we have used the natural surfactant as the Indian 3-leaf yam as the natural surfactant. And in our study, we have found that this is an eco-friendly and natural additive, by adding of which we can reduce the viscosity of the fly ash water slurry, and so that we can improve the flow behavior of the slurry. Then we have used different methods to characterize the fly ash. So this by the XRD analysis, we found that the most common material present in the fly ash is quartz and molybdenum are the most common element, and that is more confirmed by the X-ray fluorescence study. The X-ray fluorescence study, the SiO2 portion is 60.6% is present in the fly ash, and the combined percentage of quartz, FeO3 and Al2O3 is more than 70%, which confirms that this fly ash comes under the class F, that is as per the STM, and that is also analyzes the more particles present in the fly ash. And going to the next, this is the same image of the fly ash that confirms the fly ash has the smooth texture, and the particle size distribution is confirmed that this shows the fly ash is well graded form. So coming to the result section, we have studied the rheology of fly ash water slurry using different parameters. So in this case, we have used the natural surfactant as the Indian 3-leaf yam as the we have studied the apparent viscosity versus the concentration of the surfactant. When we can see here, we have seen that when with the increased concentration of the surfactant, the apparent viscosity of the slurry goes on decreasing, and at the concentration maximum 0.6 gram per ml, we have found the lowest viscosity of the fly ash water. And the second graph, in the second graph we have seen here the solid
concentration, maximum solid concentration, how much a slurry can use to make the perfect flow. So maximum slurry concentration, maximum solid concentration of fly ash we can take in the slurry is maximum 60%, or we have calculated it 64.6% to 65%, etc. And the next we have compared the bottom mass and the fly ash mixture. When we have added the bottom mass in the fly ash, that also we have verified that it has also decreases the viscosity of the fly ash water. So we have when we have added fly ash with bottom mass, its ratio when we increase the percentage, then the apparent viscosity goes on decreasing till the maximum addition of the 30%. At the 70-30 ratio, we have seen that the maximum decrease in the apparent viscosity is 130 millipascal. Then after that also goes on increasing. So,
summarize.
Sir?
Summarize. Time is up.
Sir, means this portion.
Time is off.
Okay, sir. So, going into the conclusion section, we have found in our research that the maximum concentration of the fly ash we have taken in our study. The maximum concentration we can take, the solid concentration is 64.66%, and the maximum surfactant we can use is 0.5 to 0.6 gram per ml, and we have found if we added the bottom mass as the viscosity decreaser, then that is up to the maximum ratio 70 to 30 ratio, and we can found our result. And this is the future scope that anyone can use such type of surfactant by studying the properties, other type of natural surfactant as the flow improver of the fly ash. Thank you.
So your question starts. See, the fly ash, you showed that major content is 60%, SiO2.
60.66%.
Around 60% or more. 60%. Okay, do you know what is this silicon dioxide? What is the structure of silicon dioxide?
Silicon dioxide structure is...
What is the structure of carbon dioxide? How do you write carbon dioxide? C double bond O, C double bond O on either side. So can I write Si double bond O either side? Go to your BSc knowledge. Carbon dioxide is linear molecule.
Yes, sir.
So carbon तोड़ो silicon, germanium, tin lead. तो carbon dioxide जब linear है silicon dioxide भी सेम वो Si double bond O से कहीं नहीं अरे एका ग्रुप रो कार्बन जहाँ सिलिकॉन सब एका प्रकार प्रॉपर्टी देखेगा ना तो कार्बन डाइऑक्साइड जल्दी हला linear कार्बन डाइऑक्साइड केम लिखो C double bond O राइट को double bond O लेफ्ट को तो सेम ती मु जानना स्ट्रक्चर मु लिखिबी सिलिकॉन Si double bond O सेपट को लिखिबी double bond O. Is it right or wrong?
Not right.
Why not right?
That is from the planar structure. It has
Silicon oxygen double bond, can it be created or no? Yes or no?
silicon oxygen double bond. That is almost single one.
सेटा तुम हेल्प करूची सिलिकॉन ऑक्सीजन डबल बॉन्ड हुए ना SiO पुन तळ को SiO so that structure is called, do you know, giant structure. सेतवे पड़े कार्बन डाइऑक्साइड is a gas, silicon dioxide is a solid. हैला now my question is काहे की कार्बन कार्बन डबल बॉन्ड होची ट्रिपल बॉन्ड होची ताले सिलिकॉन सहित ऑक्सीजन डबल बॉन्ड ट्रिपल बॉन्ड काहे ना हो ये फंडामेंटल क्वेश्चन बीएससी लेवल सिलिकॉन जेमति कार्बन कार्बन ओवरलैप करके डबल बॉन्ड होची गोटे सिग्मा गोटे पाई सेमति एसिटिलिन रे गोटे सिग्मा दीटा पाई ट्रिपल बॉन्ड होची तो सेमती सिलिकॉन
But
तो
the cell
होता
number is different.
से सिलिकॉन रे होता ना
So
सिलिकॉन
cell number is different, but
ना ना
the portion
सिलिकॉन
of
ऑक्सीजन डबल बॉन्ड भी होता
silicon, yes sir.
काहे को
Sir, carbon is valence.
कार्बन बैलेंस चार सिलिकॉन बैलेंस भी
But
चार
it is present in different cell. But the difference is silicon is more larger than carbon, and it's
कलाकार है तोर कौन हला उसे
there are participations are
दैट भाबो काहे की हो नहीं इट इज डिफिकल्ट टू फॉर्म इट कैन बी फॉर्म्ड से सिलाइलिन एथिलीन फॉर्म होची किंतु सिलाइलिन फॉर्म करबा डिफिकल्ट हला सो व्हाई इट इज डिफिकल्ट गो एंड टिक
Silicon dioxide is for ethan ta kon ethan ta that is a hypothetical question. That's the question. Anyway. The first question is Indian 3-leaf yam, is it your research or they are already using it and you are trying to?
No, sir, this is my research. This is also
It was
called
not,
as
no, has it been used by them?
no sir.
How do they, what kind of surfactant they are using right now for making this?
Sir, they are using normally commercial surfactants.
What kind of
CPAP, CAP, etc. Cetyl trimethyl ammonium.
They are using not just soap.
Sir?
Not just soap.
Not just soap, sir. Sir, actually, that is if we compare. Our research is to develop
Yes, sir, I
eco-friendly and
understand.
cost effective.
I understand that.
If we compare the cost, then that
That's
is.
fine. So I understand that. So this is exclusively your research.
Yes, sir.
Okay. So from this yam, how did you extract the surfactant?
Sir, we can.
Yam leaf, right? Yam leaf.
Yam leaf.
How did you?
Yam. That is
Yam itself.
Yam itself,
Okay.
not yam leaf. We can take yam 1000 gram, and we can take water 1000 gram. Then we put it in the hot water, 1000 ml of water overnight. Then after we will peel up and drop it.
Yes,
Then after one night we have smashed it. Then collect its extract. Then we can mix it with the slurry as per the different concentration we can.
Okay. It's an interesting idea. So has it been ever used as a surfactant in any other application? Let us say in villages or anywhere, people have used it as
No,
a
sir.
surfactant.
No.
Then how did this idea come to you?
Sir, actually, in a natural surfactant, that is a saponin is a substance what is present, and due to present, we have seen that where saponin is present, that will act as the flow improver. Such kind of thing, such kind of surfactant, or in Indian relief dam, saponin is present, and we have also taken one to two other things in which saponin is present. Saponin actually improve the.
Present in this?
No, actually it improved the critical micelle concentration.
I understand that. I'm asking the
Yes.
fundamental question of what kind of surfactant is there.
Yes, saponin is present here.
That's what I'm asking.
Yes,
Saponin
it's
is
present here. So that will act as the.
So first thing is this is a entirely new one that you are starting.
Yes.
These flyers that you talked about, no?
Yes, sir.
These are all inorganic stuff, right? There is nothing organic. What is that last LOI? What is that?
Sir, that is actually the last portion of the. That means the composition of the flyers. Actually, that is the residue portion of the colas.
Then next is what is the average particle size of these flyers?
Particle size you have not.
You need to do that.
Yes, sir.
You need to do that because
Sir, particle size 100.
100 micrometer.
Yes, sir. 100 to 400. The average particle size is 100. That is
So
the
up to this size, that is
percent
500, 600
Sir,
micrometer.
sir, here it is stopped, sir. Again onwards.
No. What I'm saying is, What is the average particle size?
100.
Roughly 100. With micrometer, you are able to make a surfactant out of it, and you are measuring.
No, that is the total fly ash we have taken. That is most of the size is size.
What I am saying is, this kind of fly ash, you are able to put it into that saponin whatever, and it is flowing nicely.
Yes, sir.
Viscosity you are measuring.
Yes, sir. Actually, it's viscosity going on decreasing when we.
I understand that. But it is working, right? Have you ever kept it for 5 days, 10 days, and you have seen?
Yes, sir. That is it's a static stability. We have also tested for that.
How
That
many
is
days?
maximum for 70 with the maximum concentration 64.6 of the percentage of the fly ash. We have taken it as 17 days. Maximum static stability is 17.
Is the density increasing as you go below the storage system?
No, sir.
Density remains the same.
The density, it is called a static stability. Then after the 17 days it will go down.
That's what I want. 17 days.
17 days maximum.
Then the other one is, how did you find out percentage from X-ray fluorescence? Can you tell me?
Sir, percentage for XRF.
XRF, how did you get that?
Sir, we have just given the.
You should be knowing now that this.
We have given in the lab to calculate.
So they did it for you. No, that's not enough. You need to. What is apparent viscosity? Why not? Why don't you call it viscosity? Why do you call it
Sir,
apparent
actually,
viscosity?
it is the present and the time of flow means the time of flow that is called. Or
Find out. The last one is the plot that you showed, no? The concentration and say from next onwards, remember there is a lesson for all of you. Put a slide number all the time. Otherwise, how can anyone remember which one is last? Okay. See, there is a very sudden change after 60% of fly ash concentration.
maximum viscosity.
Not maximum. It is not a straight line change.
No.
It is not a smooth change. It is a non-smooth. It's almost a straight line and then almost going up.
Sudden rise in viscosity.
Sudden rise in
Sudden rise
viscosity.
in viscosity.
How will you explain that? Why should there be a sudden rise? Why not a continuously increasing or anything, or saturating, or a straight line? Sudden rise means there is a significant chemical interaction that is happening.
Yes, sir. Actually,
See, for example, you have taken simply Indian 3-leaved yarn concentration.
Yes, sir.
Look at the apparent viscosity change. Absolutely smooth. It is decreasing in a smooth way. It is not a, increase that way. There is a break point almost.
That is a sudden rise due to that
So
breaks
there has to be some kind of aggregation, some conglomeration, some aggregation, something is happening at that. You need to find that out. Make sure that you find that out. What is actually happening? Why it is? Okay, that's all.
I have few questions. Okay, go to your table that one. So fly ash is after burning the coal, right? Whatever left out is there.
Yes.
But it cannot be so much rich in the aluminum because what is the source of aluminum? So 20% of aluminum. Go to your table, other table. There's 66% is silica and aluminum. The 19% is the aluminum. And further the K2O. It does not exist. I also just Google it because I had suspected this one. It says that it is too reactive to be existed. No oxides of the sodium or potassium will exist in this form. So you talk to a person who has provided you this composition. Because I have serious doubt this much aluminum it cannot be. It will be rich, it will be resource. It will not be waste, it will be resource.
Yeah, a lot of things are resources in this. So this data you got from the company?
Yeah.
This data you got from the company, right?
Yes, sir. Given that.
It may not exist in this form or in atmosphere. In atmosphere,
K2O is too reactive to exist in this form.
wherever there is a moisture, it will react with them.
Okay, even the aluminum, it cannot be so much rich in the aluminum. Like aluminum cannot.
Sir, actually, that is a research by SDM Managed. They have classified
You have to apply common sense also.
Actually,
Magnesium toluene sulfate.
That sulfate remains like that?
If they are not present, how will they suggest that?
Error. Somebody wrongly interpreted the result.
No, sir, I have just one question. How will they classified into two categories on the basis of three components?
Past of K2 was done like this. So how they were this?
Sir, not about K2, but about aluminium and
how do you think so much aluminum will be there?
present in the.
Then you can do an analysis of the take a coal and analyze. This cannot be this much of rich in aluminum. Even the mine aluminum bhari bandi.
But I have also question. If these are not present, then how they have classified
Check
into
it.
two
How they are,
categories?
that's what I am asking.
That category is
I can buy all like an extra
that
aluminum.
is by American
20% by
Textile.
weight,
Yeah.
this is almost by weight, that is to weight.
Yes, sir.
And the aluminum bhari will the rich hedge jode. Pausar then so much huge resource.
Okay, sir, I will.
Please check it.
Yes, sir, I will check it for.
Are they extracting aluminum from here? That's the question.
No, sir. We are not accepting. We are just mentioning it. These are the present.
You are not doing it. Are they doing it?
Okay.
The company. The company will not allow aluminum to be wasted like this.
The sulfate SO4 ହେଇକି ରହିଥିବ ସେ ନା
Let's thank her for that talk. Okay. We have sir one more but
ତମେ BCSD ର ସେଠି ଆଉ କଣ କଲି
for
evaluation. So load your slide. Okay, we have one other invited lecture. So how long you give? 20 minutes? 15 minutes. 15 minutes. Already culture end of the day.
I'll not go into detail just.
Yeah. So now next speaker is Mr. Parida from the PG Department of Chemistry, Bhubaneswar University. We will talk about the green and sustainable synthesis of functional hydrocarbons. Vibhuti.
So very good evening to all of you. I thank the organizer, OCS, and particularly Professor Acharya sir and Vidyarajah sir for giving me opportunity to share my experience, my research profile at Department of Chemistry over the reactions. So I will be talking on the green and sustainable synthesis of the functional heterocycles, tetrahedrals and biodies. As you know, before my talk, already Dr. Patel sir has given a lot of synthesis on heterocycles, and in the morning session also, Dr. Jenna from Northwest University has also given talk on the heterosynthesis. I do not go in detail by the importance of heterocycles. I will only focus on the green and sustainable approaches that apply on the synthesis of various heterocycles and viral synthesis in our lab. So as you know, the importance of heterocycles lies mostly on the drug application in the medicine, drug discovery. Apart from the other applications like solar cell, sensing and agrochemicals and all these things there. So already has been discussed, well discussed by Patel sir and before the Dr. Jenna from Northwest University. So I am not going to detail what is the importance. It is already self-explanatory. So I am going to just the approach which is using the green and sustainable approaches for synthesis of these heterocycles. And before my talk, already Professor has shown what is the non-templated synthesis of the heterocycles. Probably my talk will also few of the examples will fall in this category. Non-templated heterocycle synthesis. And as you know, the traditional synthetic chemistry we use a lot of toxic chemicals, solvent, catalyst, and that may ultimately do harmful to our nature. So they have used multi-step synthesis extra workup steps, toxic solvent, and hazardous chemicals, which we in green and sustainable synthesis we almost or we try to minimize those toxic substances, and so that we can use our synthesis a greener approach. Like we use 1% synthesis, no extra workup steps, just all together mix up in one pot and try to get atomic equivalent synthesis. So we use green catalyst, green solvent, and green energy sources. These are the uses strategies we use to make heterocycles of a different diversity. So here is one example. We are using this heterocycle, is a thiazole heterocycle. So this thiazole, we are using this the middle substrate. This is a lotion. Normally it is plenty available in the natural product like the lotion, mehendi. So we are using this molecule which is commercial available, and coupling with this glycol and this thiamide to couple in a very efficient manner using acetic acid solvent, and just at 10 minutes we get precipitates out. So this thiazole is first time reporting this thiazole appended with this lotion natural product, which is available in the we can say from mehendi. So because it has some different activities, we are expecting that lotion that available from mehendi that can extend some extra biological activity when appended with thiazole. That's why we are reporting this synthesis, and this synthesis we have reported this synthesis in gram scale also, and the synthesis is very much column chromatography. It doesn't require much time, and it requires simply a filtration, no metals using, no catalyst. Of course, we are using the acetic acid, which also not that much harmful because also you consume in the vinegar also. That's why you do not consider this very harmful. And synthesis is very much scalable. We have synthesized in gram scale, and this was under communication. We have communicated this paper recently, and we have done this synthesis with a diverse range of the heterocycles. What we have done, we changed this glycol part as well as thiamide part, and keeping the last one on the middle part constant. So accordingly, we prepared a large number of heterocycles. The yield from good to excellent yield, and just in 5 to 10 minutes you get the precipitate. So this is what we synthesized, a diverse array of heterocycle, huge heterocycle, diverse array of thiazoles with the changing variable from the glycol part as well as from the thiamide part. And the proposed pathway, we have proposed 2 pathways like glycol, when order proton is activated and then attacked by the lotion through a nominal type condensation, followed by again thiamical type addition of this thiamide, giving rise to the intermediate which undergoes a 5 exotic cyclation, which is a very classical process, giving the intermediate product intermediate 13, which upon dehydration give the product 4, which ultimately goes through other path B, where the glycol react with this thiamide first, followed by reaction with this last one. It will also give the product same product. So though we have not confirmed which pathway is going exactly, this is the proposed pathway. So we have another class of molecules synthesizing. This is a fused, it's called benzopyran. As you know, benzopyran having diverse array of activities, biological activities. So we are using, first we thought that the benzopyran, this bond, this can be obtained by a retrosynthetic plant from this hemiketal. With that, then this hemiketal can be functionalized, you can say through functional FGI retrosynthetic functional interconnected process. We can envision that this hemiketal can be obtained from that 1,3-diketone, and that 1,3-diketone could be obtained from the Michael addition, and that giving the Michael acceptor, and this Michael acceptor can be obtained from the nominal condensation of this is called alpha hydroxyaldehydes, that is called salicylate component, and the 1,3-dicarbonyl, this is the dimidone. So with this and retrospective analysis, we thought that molecule can be obtained simply by this dimidone as 2 equivalent, and this salicylate or its substitution with 1 equivalent, giving the target molecule benzopyran.
So in that objective, we planned our synthesis using a very this bicatalyst, this bicatalyst taurine, which is called beta sulfuric acid, and it has both dual activities. One is sulfonate part, the existence of deuterated substance, deuterating form. So it has act as an acidic as well as the basic role. That's why we use this deuteratic substance that is our taurine as a bicatalyst. And under ultrasonic condition, we couple this dimidone 2 equivalent and 1 equivalent this salicylic substituted at different side. And in one part, we all give ethanol and water in 1:1 volume. We get a reaction yield up to 98%. And here the reaction is scalable. We did reaction in gram scale. And moreover, we did not need any column chromatography process where normally traditional chemistry we use lot of solvent, and here we did not use any kind of column chromatography process, just we precipitate and filter and wash. That is the easy isolation process. And a little bit about taurine. Taurine is a naturally occurring in normal tissues. This is also found in large amount in the intestinal due to produced in the liver from like cysteine and methylene. That's why taurine is considered a bicatalyst. And use this bicatalyst under ultrasonication method. Ethanol and water is 1:1 that gives water just exists as a deuteratic form, and ethanol is used just solubilizing the substance. That's why it is mixture of 1:1 solvent, and we are getting very good yield up to 90% yield, and that has been showcased the method in gram scale. And this is also under communication this paper. And accordingly, we have synthesized a large array of the diversely functionalized in the aldehyde part, having the number of benzopyrene compound with the yield up to 98% yield. So this is now what about our product, and we have used the method with the recyclable way, because though the taurine is cheap, still we recycle it, because with the same reaction we recycle the catalyst and just the filter. We take the filter and added some substance so that it get multiple times, and did not use any further catalyst. So that catalyst is recycled up to, we use up to several cycles, up to 6 rounds, and it did not change any significant decrease in the activity or yield. So mechanistically, as you know, the first time, because taurine acts as a dual functionality, bifunctional, it activates the dimidone, which is a one-third dicarbonyl compound, making the inolate, and on the other way, it activates the acidic part of the taurine, the ammonium plus, that activates the aldehyde. So it is dual activation, so that it followed a Michael type, followed an aldehyde type reaction, and next we can say, and further Michael type addition, another one equivalent of the dimidone, and that follows the reaction pathway, following lastly they get the benzopyrene. And so this is what also at the end, this next slide, the third one shows the gram scale synthesis of this scaffold. So though we did not apply the gram scale with all the subject, we tested the gram scale synthesis in few examples. This is one of the examples we show here. And another one, because we are using only this presentation shows the green and sustainable approach for the synthesis. Here we are using tetraketone synthesis, where the tetraketone was again the same dimidone using, and we did not use salicylic, rather we use only aldehyde. So here we are getting tetraketone under visible light. Here it is the 30-watt LED we are using, and here also we do not use any photocatalyst. We are using the light source and getting the product just by precipitation. So we are using column chromatography, no catalyst, no metals we are using. So this is the way, and then these tetraketones which were synthesized, they are being used. They are used for different studying the various activities. At the beginning, we are using the in silico studies, but we have not yet done the in vivo studies. We are just trying the in silico studies, and we have done some molecular dynamic simulations and other approaches, theoretical analysis studies, in silico studies have done. Though we are not using now, not done the
in vitro studies. Later we'll do that one. So one of the molecule which trimethoxy substitution on this aldehyde shows the lead molecule lead tetraketone for this studies. So we have used same protocol to design lot of scaffold using this strategy, using a strategy which is good number of with good yield, and also we have applied this method using a very good we are planning to do it in vitro studies in lateral, and this shows diversely functionalized. Here for example we have nitro group, and that could be further functionalized to amino and can be later extended, and here also we have the biaryl like a lot of aryl substitutions with halogen substitution are there, because you're putting halogens, chlorine, bromine, iodine, that can be later can be used coupling with it through standard palladium catalytic cross coupling reactions can be further functional. But as my previous speakers have told, unless we do some like biological applications, we do not have that facility here, so we are restricted. That's why at the present we are doing the only synthetic part. Though we are doing synthesis, and we are also using only greener approaches. We do not using any solvent which can use which can harm to our environment. So here the proposed pathway is both a radical pathway. First it activates the aldehyde, making diradical, followed by again diradical, pick up the one hydrogen radical, making the second radical between the 1,3 diketone, and that combine and followed by again loss of the hydroxy radical. So this followed the Michael type acceptor, and here also because we have using the LED source, that followed further another radical of this alpha also to be double bond. Then this combined with the both the like Michael type addition, and you get the tetraketone and in very good yield. So again, this process we are using in gram scale. So each example, each methods we are developing, we are applying this method so that we can use it industrially. Not industrial, at least you can get in the gram scale. And this also has been recently communicated. And these are the molecular simulation studies, in silico studies like pneumonia and dengue. So we are not going to detail. So this last, this last slide. This is a coupling reaction of the aryl, heteroaryl, and boronic acid, and this is called using a lanthanum chloride palladium alkyl Suzuki coupling, and just coupling two aryl compounds. Couplings are very much popular and known. Though we here synthesize one palladium lanthanum chloride palladium nanocatalyst, which is used as coupling these two aryls, and we got the biaryl compound. And here we are again verifying the synthesis in a scale of like gram scale synthesis, very good high yield and with good substrate scopes. And the beauty of this actually is the catalyst which used can be recycled up to few cycles, so without significant loss of the activities. Though we use getting little bit less yield, but not significant decrease. This has been already published recently in the RSC Advance. This is the nanocatalyst characterization. We are not going to detail, and this is the characterization up to this table because of time restrictions, and we are not going to detail. So this is the software scope, and this is the recyclable studies. You can see 84 to 80, not that much decrease in the yield. Finally, I acknowledge my funding agencies, my university, Bhubaneswar University, for the infrastructure which is available. We work there, and for SARP, UGC, Science and Technology Department, Government of Orissa, and IJR Bhubaneswar, where we use normally characterization facilities, and Professor Himashu and IJR Bhubaneswar, we also have been some characterization samples. And these are lab mates, and my collaborator Dr. Meher, and two of our dissertation students, and here are PhD scholars. So one of the dissertation students also present here. So he also a student. He also worked this last two are dissertation students. They also worked in this project. So finally, thank the OCS and the organizer giving me the opportunity to work, present your work here. Thank you for kind attention.
So joined us and there is no question because we were running late.
Yes.
Okay. Thank you very much. Everybody waiting for the culture to be taken.
ମୋର ଆଉଟର ଷ୍ଟଡି ଅଛି
बहुत बड़ा फोटो नहीं मोर फोटो भीष्म सारे नहीं भीष्म सारे ना
कहबे
मिसिक ना
हां 10 मिनिट ଏବେ ଠିଆ
अरे आप तो पुणे लोग गोल भी जोड़े
ना दरकार नहीं चिन्ह बामनर पिता दरकार
नहीं मुझे तो एक
सीएस रो पुणे लोग
कोऑर्डिनेशन दरकार नहीं और
presented their posters and evaluation is completed, they can take out their posters. Only, as I understood, very few posters are left for evaluation, maybe within 5. So balance, you can take out your posters. Okay, you can take out also in the during dinner time.
शाम हसीन है और महफिल साथ है। फिल्म और कला का ये संगम रंग लाएगा, दिल थाम के बैठे यहाँ हर कोई छा जाएगा। A very good evening, ladies and gentlemen. Welcome to this vibrant evening of 38th Annual Conference of Orissa Chemical Society and National Conference on Advancement in Materials Chemistry.
Well, before proceeding ahead, let us introduce ourselves. I, Sushri Subhrajyoti Nanda.
And I, P. Shatabdi Patra, welcome you to this evening.
Tonight, we celebrate not only the advancement in science, but also the rich tapestry of our cultural heritage.
Tonight is not just about words, it's about emotion, rhythm, grace and passion. So let's begin this wonderful evening full of art and tradition blended with boundless creativity.
That was such an amazing start. You spoke so passionately about tradition and culture that I can't help but wonder, do you truly know as much about our tradition and culture as you make it sound?
Of course, I do. Try me.
Alright then, let's taste your knowledge. Can you name a classical dance that depicts stories of gods and has intricate mudras, which is originated from a state known for its beautiful temples and extraordinary sculptures?
Is it Bharatanatyam? Oh wait, is it Kuchipudi?
Oops, it's a no. Let me give another hint. It's all about devotion and divine storytelling through every move. It's deeply connected to Lord Jagannath and was originally performed in temples as a form of devotion.
Oh, now I got it. It's Odissi, right?
Yes, absolutely. Ladies and gentlemen, Odissi is not just a dance form. It's a poetic celebration of devotion and culture. It beautifully reflects the heritage of Orissa. It tells divine stories through graceful movements, captivating mudras and soulful expression. It's a perfect blend of devotion, art and history.
So without wasting any time, please welcome our first performer who is going to perform Mangala Charan followed by Pushpanjali, Bhumi Pranam and Trikhandi Pranam, which is a threefold salutation to the God, the Gurus and the Rashikas.
So guys, let's welcome Miss A.D. Shobnam with a huge round of applause.
applause once again to our talented performers. जज्बात रंगीन है, महफिल जवां है. जज्बात रंगीन है, महफिल जवां है. सितारों के संग ये चांदनी रात है. आज के सफर में हम साथ साथ हैं. शुरू करते हैं ये जवान नई बात है. I, Aryan Brahma, the most awaited host of this evening, welcome you once again to this beautiful event. Okay. Well, Shatabdi, are you really trying to sing something or dropping a hint to our audience?
Actually, I was dropping a hint to our audience. Our next performance is something that is purely magical. Something that is a timeless art that can connect directly to the heart and can directly speak the language of the heart. It can also connect to the soul.
Well, actually, yes, you got it right. We are now going to have a captivating melodious solo musical performance that promises to transport us to another world. उनकी आवाज की जादू दिल में उतारा करे. उनकी आवाज की जादू दिल में उतारा करे. खामोशी के शहर में एक पुकारा करे. हर लफ्ज में छुपी है एक महफिल सी लगे. हर लफ्ज में छुपी है एक महफिल सी लगे. उनकी सुरीली बात का कैसा इजहार करे.
Please welcome none other than Miss Stuti Nanda, who is known for her incredible talent and mesmerizing voice.
So let's welcome her with a huge round of applause.
A very warm evening to one and all present over here, respected dignitaries, teachers, and the audience present over here. So I'm going to sing a few songs today. I hope you all would enjoy with me.
your beautiful performance. Your voice has added a musical charm to our evening.
Now I request Professor Ajay Kumar Behra sir to kindly sing a song. Please sir.
Organic chemistry written by Akhil Bhai.
ମୁଁ ଭାବେ କମ୍ପ୍ୟୁଟିଂ ସମୟରେ ଭଲ ଗୀତ ହବନି ଆପଣମାନେ କହିପାରିବେ ବୋଲି ଏ ପ୍ରଥମ ଦେଲେ ମାନେ ଆମେ ସବୁ ପଳେଇବେ ଛାଡ଼ିକି ଟିକେ ଗୀତ ମୁଁ ଗାଏ ସେଇଟା ଟିକେ ଏମିତି ମାନେ ସେଇଟା ଗାଇଥିଲି ସିଲଭର ଜୁବଲି ଫଙ୍କସନରେ ଯେତେବେଳେ ମୁଁ ସେକ୍ରେଟାରୀ ଥିଲି ସେକେଣ୍ଡ ସୋସାଇଟି ଆଉ ଏ ଯେ ପ୍ରେସିଡେଣ୍ଟ ହେଇଛି ଗୋଟେ ୟୁନିକ୍ ଏଇଥିପାଇଁ ଗାଇ ଦେଉଛି ଗୋଟେ ଗୀତଟେ ଆଉ ଓଡ଼ିଆର ଅସୁବିଧା ସବୁ ହିନ୍ଦୀ ଗୀତ ଗାଇଲେ ଭଲ ସେ ମୁଁ ତାଙ୍କଠୁ ଖରାପ ପାଇ ହେଲା ଟିକେ ମନେ ପଡୁନି ମୋ ନାଁ ଭୁଲି ଯାଉଛି ଗୀତ मोहम्मद रफी साहब रफी साहब समाज बंद हो चेष्टा कर भूलबाल एक्सक्यूज मी मयूरी को तुम आकाश दिने मारे मेघ साजी चंद्रिका तोड़ी नाचिल तुम्हें इंद्रधनु मुआकिली मयूरी गो तुम छंदरे देवे मसुर हजाई देवी बोली भाविली एते बसारे माटी गंधरे देवे तुमको भल पाइली केउ सबुज बनर मायारे केउ सबुज बनर मायारे तुमे लुचि गल केते खोजिली मयूरी गो तुम आकाशे दिने मल्हारे मेघ साजिली चंद्रिका तोड़ी नाचिल
Up next, we have someone really special. Someone truly known as the art and excellence. An alumna of this very institution, none other than Ms. Srimati Devashmita. She is a celebrated Odissi dancer with over 21 years of experience.
She is not just a dancer but a storyteller, blending grace, rhythm and expression to leave audiences spellbound. Let's welcome the incredibly talented Ms. Srimati Devashmita with a huge round of applause. of classical dance with a poise and grace. It's amazing how such art forms are preserved and passed down through generations.
But Subra, I think maza nahi aaya. And literally, one thing is the backside people are sleeping right now. Maza nahi aaya. I don't see the energy in our audience. Come on, you can do better than this. How will you enjoy the next performance?
Exactly. You know what they say? Energy attracts energy. So let's amp it up because something electrifying is about to take over the stage. Trust me, you don't want to miss this one.
Okay, then तो शेरों की तरह दहाड़ेगा आज ये सांस, हर दिल में जला देगा संगीत का राज, तारों से चमकेगी जज्बातों की गूंज, दिलों को झंझोर देगी ये धुनों की ये धुन, हवाओं में गूंजेगी गिटार का आवाज और हर दिल कहेगा वाह क्या अंदाज, वाह क्या अंदाज, वाह क्या अंदाज.
Everyone, tighten your shoelaces and get ready because this is going to be one good rocking time. Without further ado, please put your hands together and welcome to the stage Arpeggio.
ये
Dr. Achyutananda Acharya sir to felicitate her. Please give a huge round of applause. So now we will continue the band performance of the famous RPGO group. So please be continued.
चला नहीं जाओ सीढ़ी ऊपर लगे
चेयर गोटे
And my dear friends. So this is RPGO, the Officer Music Club of Orissa University of Technical Research. So with me, myself Jasmine, and with me my teammates Tala on the beats, Alandeep on the guitar, Satpat on the keyboard, Prithvi on the vocals, and Abdul on the drums. So this is RPGO presenting in front of you some melodious song. So let's carry on.
सीटी कॉलेज सब नाम बोल
Now I want to request Professor Ajay Kumar Behra sir once again to sing a song.
Please sir, kindly please come to the stage. Guys, give a huge round of applause.
आपने ओडिशा केमिकल सोसाइटी परफॉर्म कर देते এটা সেই ওড়িয়া গীত এটা অরবিন্দ মুদালি গাইଥିଲେ বালি খেলুଥିଲେ বালি খেলুথি বালি খেলুଥିଲେ
Bali খেলুଥିଲେ
अर्ज करें।
कानों में खनकती है खूबसूरत सी बालियां, कानों में खनकती है खूबसूरत सी बालियां,
और मजा तभी आता है, और मजा तभी आता है जब महफिल में बजती है जोरदार तालियां।
आमन दुलदुली बजा अरे मन ऐसी तना बना देखले लक्सी मजा
मन ऐसी तना बना देखले लक्सी मजा। मगुर मच्छर मुंह चेकता तंगनी मच्छर कटा, मगुर मच्छर मुंह चेकता तंगनी मच्छर कटा, अरे संबलपुरी ढोल बजले मलकी जी सी आटा, मलकी जी सी आटा।
एंदा ही एखेन गुटे संबलपुरी नाचते नहीं करी आश्चन आमर बहिन माने तो देखवा चालून दर्शक बंधु।
अरे बिना फूल की थाली खाली लक्ष्मी पूजा थाली, अब बिना फूल की थाली खाली लक्ष्मी पूजा थाली, महफिल भी खाली खाली लग जाएगा।
महफिल भी खाली खाली लग जाएगा
तो मारी तो खींची की ताली। जन हमर समलपुरिया बहन माने आउ थरे गुड जोरदार करताली हे जाओ बहन मानर लागि।
In the words of Bhagavad Gita, Aham Atma Gudakesha Sarvabhutesha Yalstitaha. It means the Lord explains Arjuna that he lives in the heart of all the beings. He is the beginning, the middle, and the end of all the creations. He is the sustainer of this universe. These words remind us that everything begins and ends with the Lord. So, as we started this evening with the name of God, it's the best way to end this evening with the name of God.
Perfectly said, Sadhati. As we bring this memorable event to an end, what a better way to do than with an enchanting Odissi performance by Ms. Sai Suchishmita.
Exactly. Her art will undoubtedly be the perfect conclusion to a night filled with such a wonderful cultural brilliance. So let's welcome her to the stage with a thunderous round of applause.
So let's welcome her with a big round of applause. Sai's performance was divine. Her grace of storytelling and mastery in techniques were perfect way to round off the evening. It truly feels like a celebration of Orissa's artistic heritage. Now I request President of Orissa Chemical Society, Professor Ajay Kumar Behra sir, to give a vote of thanks.
The cultural program has come to an end. But my experience that earlier I was the coordinator of performing arts Sambapur University 3 years. So what I have observed and what I observed today, that I will comment. So they have the performers have sung good songs and good dances, fusion dances, Odissi dances, and to me, actually every department, even the anchors the best, and the performers, to me, it is fantastic and a fantabulous performance. And I have never seen, because in songs, lyrics is okay, fine, and the chemistry seminar is perfect, the deliberation of chemistry lectures are perfect, and today's chemistry in the performance is also very good, very perfect. So I congratulate all the participants of today's cultural function, and I also express my deep appreciation for their fantastic performances, and thank you on behalf of Orissa Chemical Society to all the performers of this department. Thank you all, and thank you all the spectators, because your presence also has encouraged a lot to the participants. So on behalf of the Chemical Society, also I thank all the spectators assembled here. Thank you. Please come to the dais on photograph.
As the event has come to an end, I especially thanks to all the performers and the volunteers present here for the cultural event. Special thanks goes to Ms. Srimani Devasmita Di. As you all know, she is an alumna of our university, and again the thanks goes to a famous RPGO band. Once again, I request, as per the sir's demand, I request all the performers to please kindly come up to the stage. A special thanks goes to Professor Ajay Kumar Behra sir, as he made the day of this, he made the evening. So please give a big round of applause for her.
रनिंग शॉट में हम रनिंग नहीं है हापी से भाई को उठी सारी बस पड़ी उठी सारी सांगे सांगे बस भिड़ जो भाई दूर रही नौन हम पाख यूटू हम
I request everybody to proceed for the dinner.